It's my pleasure to introduce Matthew McDermott. Matthew is an assistant professor in Columbia's Department of Biomedical Informatics, where he works on representation learning and foundation models for medical data. He previously completed his PhD in computer science at MIT and a postdoctoral fellowship at the Harvard Medical School, where he was developing high-capacity models and representation learning systems for EHR data. His work includes clinical BERT, structure-inducing pre-training, and large-scale software frameworks for machine learning over structured EHR data, such as ESGPT and MEDS. So it's my pleasure to welcome Matthew, and let's give him a round of applause.
Okay, so first off, thank you all so much for having me. I'm very excited to get to talk to you all today about meds. Now, a couple of things before we dive in. So one is, I believe there are some Wi-Fi issues currently, and throughout the slides there will be links to Colab notebooks that people can theoretically go to and look at to see sort of interactive content. Though you don't actually need to do those for this tutorial. I'll mostly be going through things in the slides. So if the Wi-Fi is still not working, don't worry. Also, the slides will all be available publicly after, so people can actually dive into things in detail. And I'll also say that I want this to be interactive as much as possible so people can actually engage with this like a tutorial. But there's only one microphone. So instead, to spare Howren's legs, I'll take some dedicated sort of question breaks throughout at various points where people can ask questions as opposed to just doing it sort of totally throughout. Yeah, so let me go ahead and dive in. Now, before let me make sure this is working great. Yeah, so before we do anything else, what I really want to do is just ground everyone on what I'm actually going to be talking about. That way, if folks are not interested in this area, because health AI is very broad, you can know that you can tune out more successfully. But what we'll be talking about is AI for structured electronic health record data. Right. Now, there's lots of different ways to think about structured EHR data. My personal favorite, and one that, as you'll see later, is very relevant to meds, is just think about it in a view like this. Where you think of this as I missed one very important thing with my logistical note, which is that this meds in general is an incredibly collaborative effort. There's been tons of people who have added a number of different, who have worked on meds in various ways. The list on the slide here are people who've actually directly contributed to the tutorial content in various ways, both in its original preparation for the KD tutorial and then its revisions for this tutorial. But the list of full contributors to meds is much, much broader, and you'll see more names at the end. There's a number of folks in the audience, I believe, who have worked with meds. So just a shout out to everyone to know that there's a lot of great people who have made this all possible. Yes, but as I was saying, we're working on artificial intelligence for structured EHR data, right? And the way I think about this is that EHR data is a timeline of complex observations that catalog patients' interactions with the health system, right? And now when we talk about structured EHR data, generally we're thinking of these observations as being structured elements like medications, diagnoses, records of transfers in the hospital or admissions, these sorts of things. Right? Of course, you can have lots of other kinds of data in electronic health record data. You could have images, you could have waveforms, you could have clinical notes. Some of those you might consider unstructured. Meds will only cover a subset of these, as we'll see more later. But you can think, for the purposes of this tutorial, mostly just restrict yourself to think about the structured data. So things that you could put in a tabular format, although I'll say why I gave that air quotes in a few moments. And what MEDS is going to do is help us give a standard for working with this in the context of high-capacity AI that's designed for the workflows that we need, as we'll see more later. Okay, so that's what we're going to be thinking about in this tutorial. And I may use terms like health AI, when what I really mean is AI over things like this, not all of health AI, right? Really, there's many more things that go on in this space. Okay, so what's actually going to happen in this tutorial? So there's some opening remarks. Those are done. But then we're going to actually talk about what is meds at a high level first and foremost. And then to walk through the rest of the semi-interactive sections of the tutorial, I'm going to introduce a fictitious problem that can help us think about how we need to work with health data, right? And then after we have that problem to frame what we're going to be talking about, we'll go through and talk about how you would proceed with that sort of full pipeline of work in the med space, going from converting your data into meds, extracting prediction tasks, and developing different kinds of models. Now, in the slides, there are links with these QR codes or the tiny URLs to various things. This one goes to these actual slides, but everything else here goes to Colab notebooks that you can run with no data access required. It is a Colab, so you need to sign in on Google. And all the parts with the Colab logo have a notebook associated with them. And we're not going to go through all of those in the time we have today because that time is limited. Instead, we're going to try and just focus on some parts that I think are most important. And we may skip around in the slides a little bit because I want the slides to be complete for you all later if you're looking at this. Okay? Yeah, so let's go ahead and dive in. Oh, actually, one more thing first, some disclaimers. So MEDS is a standard for this EHR data that I described, right? And it's, in particular, it's not a Python package or something like this. Instead, it's what I like to think of as a data as an interface standard, right? It's defining how you should think about the data in a very concrete format on disk, which we'll see more, and not defining a particular package you have to use or a particular tool you need to work with, right? So this means that there are lots of ways that you could do things in the MEDS ecosystem. Now, I'm going to present one way that you can do certain things in this tutorial, but there's others that you could use if you want. And so feel free to do things differently. Now, similarly, MEDS has been an entirely sort of academic, voluntary effort so far, which means that things may work or may not work to the, nothing's going to be perfect, right? So even though we have some great tools that have some really strong evidence of making workflows better, there may be better ways to do things. And if you think of a better way to do something, please tell us and just contribute back to the MEDS community, right? That's really the entire point of all this, to make all these things work together. Okay. So all of that said, what is MEDS and why use it? Now, MEDS is a data standard. We're going to see what that means very concretely. And data standards have tons of benefits. But the one that is most resonant with me is that there's this there's this critical problem in health AI right now, which is this reproducibility crisis, right? This is sort of old news, I think, to everyone in this room. Here are some of my favorite quotes from different papers over the years about the reproducibility crisis. Alistair Johnson had some great work in 2017 where they actually tried to manually reproduce tasks, just a task extraction from papers on publicly available data with an incredibly simple task, and found that they basically can't do it, right? The reproducibility of a published work in health AI fails at the earliest possible step. Myself and a number of colleagues did a retrospective analysis of published papers and found, how much do we meet certain reproducibility criteria, and unsurprisingly found that we don't do a very good job. One that I found more recently is this paper from 2022, which is really depressing, which says even when code is actually released, only 33% of the time is that code reproducible. Where reproducible, was not something determined by running the code. It was based on documentation, code quality, things like this that the authors manually judged. So in general, in health AI, there's this huge problem with actually making the things that we're doing reproducible across the ecosystem. Now, this has tons of implications on our ability to do effective science in this domain and how we can actually advance our understanding of AI in EHR data. I have very strong feelings about them, but that's not the talk that you all signed up for. So I won't tell those to you now, but if you're curious, you can go and see the proceedings that I published at ML4H last year on some of those points, at your leisure. But instead, what I'm going to do for this talk is let's just take for granted the notion that the reproducibility crisis is a big problem and we want to solve it. And in particular, that a vehicle to solve it is data standardization, right? If we have a widely adopted data standard, then we can all use that as our bedrock for our analyses. And in particular, if that data standard is designed well, it will lead us to develop more reproducible tools. Right? And MEDS is going to be the tool that I and many others have developed to try and be this solution. Now, you may be thinking, aren't there a bunch of other standards for EHR data that exist? Things like Odyssey OMOP, things like I2B2, PCORNet, maybe even FIRE. And you'd be absolutely correct. All these standards exist. They serve a tremendously valuable role in the ecosystem. They're very good at a variety of things they do. None of them were designed for health AI. And this is not a disparaging comment. This is just a reality of, in particular, high-capacity AI didn't really even exist in the same way as it does today when these standards are actually being developed, right? They're designed for different workflows. Now, I'm not going to say too much more on these other standards, again, for the reasons of time. There are some slides in the sort of appendix that you can look at if you're curious about this. But what I will say is, what does it mean to design something for health AI, right? Well, in the MEDS community, we've sort of identified these four key design principles for health AI that we think are important, and illustrate some of these differences from other workflows that are needed in existing standards, right? So first and foremost, the goal of MEDS at its base is to enable transportability of model training algorithms, right? The process that goes from raw data to a trained model. That's the fundamental unit that we want to generalize, or we want to reproduce first and foremost, right? Now this is different than reproducing a pre-trained model from dataset A to dataset B. Instead, we're reproducing the process that goes from dataset A to a model onto dataset B. Right? This is not to say that reproducing trained models is not important. It can be, depending on your application, it can be critical. But reproducing the code that you take to go from raw data to that model is sort of an even more fundamental step, right? Now, if I can't run your code, then reproducing your model is, probably out of reach, right? So MEDS is saying, let's start with this reproducibility of algorithms. To do that, MEDS says what we really need to do is capture the simplest possible view of the fundamental shared structure of health data. And what that structure will be, we'll see in a moment, will be very reminiscent of this timeline picture that I alluded to before. Now, simplicity has a number of benefits, conceptually and practically, that we'll see some of them sort of emerge in practice. But it's a very different choice than other existing standards have made, which focus more on data control and curation as opposed to simplicity, right? And if you think about something like the bitter lesson in AI, the importance of scalability and things like this, simplicity aligns with how AI looks at things much more than other fields. The last two are somewhat simpler and less controversial, maybe. So one is that critical in the development of these kinds of tools is open source ecosystems, right? We have this beautiful triad in many fields of ML where we have models or algorithms, data, and tools that are all sort of interchangeable. We don't really have that in health AI right now. Everything is bespoke and totally custom. We want to develop MEDS to catapult the development of this sort of an open source ecosystem. And also this recognition that we're moving towards this era of foundation models. And I don't just mean things like large language models, I mean things like custom models specifically for EHR data that have foundation model scale properties. To develop those, you have totally new engineering challenges that you need to face, and we want to reflect those in our development. So I've told you a bunch of stuff about MEDS. I haven't actually told you what MEDS is, which maybe is a little frustrating, but I promise the wait is over. We're going to actually see what MEDS looks like now. And to start with, I want to say again, this is how we're thinking about patient data, right? If we say the fundamental shared structure of EHR data, it's this picture, right? Because I haven't told you whether this is Mass General Brigham or Sick Kids in Toronto or Stanford's data or any other hospital, but we all can look at this and say, oh yeah, that's EHR data, right? No matter what your health system is, EHR data can always be viewed in this timeline perspective. So MEDS is going to try and capture this in as simple a form as possible, and it does so very directly, right? Where it says we're going to have a couple of different kinds of files, but the main one is really this one on the top left here, this data file, which, as you can see, only has 4 columns, right? It actually technically only has 3 mandatory columns, just the first 3. The numeric value is actually even optional, right? It has subject ID, time, and code. And we're saying, okay, we have a patient, the subject, we have a timestamp, when is this thing happening, and we have a code in some completely unconstrained vocabulary that's telling us what is happening at that event, right? And so in this view, we're just directly taking this timeline about this patient and sort of transcribing it in a data frame format. There's no separation by what kind of measurement this is. There's no separation on what system is it recorded in. It's just capturing the temporal order of these events. We also have these metadata files, like this codes metadata file here on the bottom left that says, what are these codes actually, what do they mean? What free text descriptions do they have, if those are available? What external ontologies do they link to, if available? But those could all be null. You might just get the code strings, and that's still allowed in the MEDS ecosystem. And then we have some other files that we'll get into more later that are things for more AI training processes, like the subject splits.parquet file, on the top right there, and this label file on the bottom right, which captures how you think about tasks. And we'll talk about these more, in particular the label file rather, we'll talk about that more later. There's also this data set metadata for sort of provenance tracking. But really the key file to think about is this data shard shown here, right? And so I want to jump into this a little bit more first, right? So I've used this term shard, and what I really mean is that we're not storing the entire data set in one file. Instead, we're taking the data set and just chunking it into groups of patients, right? So for a single patient, all of their data will live in the same shard. It'll all be contiguous by time, but the entire data set will be distributed among a variable number of files. And this lets you do parallelization very easily, so you can process things in efficient ways. This code column is unconstrained, right? We're not harmonizing this to an external vocabulary. These are not necessarily going to be ICD codes or LOINC codes or SNOMED codes. They could be random strings. They could be entirely illegible to humans, or they could be sort of fully readable as these are, right? And this is an intentional choice, which we'll talk about more in a moment. This is not to say that we're against harmonization, as we'll see. You could have these all be in a certain vocabulary, but they also could not be, right? So it's sort of up to the data set. Now, importantly about MEDS is that you can actually add any additional columns you want for your data set. Most tools will only rely on the sort of main columns, but you could add extra ones if you want, and that wouldn't violate the standard of MEDS at all. Okay. Let's see some quick examples, especially because we can't actually load the collabs now. So this is just a different view of a data shard, just some different data, right? And here you can see we have multiple patients in the same shard, right? But they're all ordered. So you can have events with no timestamp recorded, and those are considered to be static events, right? So we're not deviating the format even for events that are not in the sort of temporal ordering, right? You have duplicate timestamps. That's totally fine because lots of events can happen at the same time in EHR data, right? You can also, again, as we said, have these non-standard vocabularies, right? No real standardization in the code space here. Now, I mentioned before, but it's worth saying again, this is, what this is reflecting is that MEDS is mandating a technical standard of your data on disk as opposed to a conceptual harmonization, right? Instead, we're remaining fully agnostic to how you want to represent the data, right? And importantly, as has become apparent with the MEDS ecosystem, much of what we actually need to make tools reproducible is the technical standardization as opposed to the harmonization of codes, right? So this can make things much simpler. Now, one thing that you see in a lot of other standards is this notion of like an interval, right? Like you have a visit, right? Or you have an infusion or something. MEDS says we just have a single timeline. So how do we do these sorts of intervals? Well, what we do is we say, well, an interval starts and it ends, right? And so we'll just put those in at the right times, right? So you have an admission and a discharge. Now, this is sort of the first area where you often have to change your thinking just a little bit to use MEDS. Even in data sets that we're very familiar with, like MIMIC, for example, there's a notion of a sort of admission as a single entity, and a lot of things are associated with those intervals in many health data sets, right? But forcing you to put this like this actually benefits how you work with the data in many regards, right? A common problem that has occurred with MIMIC over the years that some of you may know about is people put things associated with the admission at the beginning of the admission when they're modeling their data, as opposed to at the end of the admission, like billing codes, for example. They say, oh, here are the diagnoses, so those happen at the start of the admission as opposed to at the discharge, even though in reality, billing codes are only assigned at discharge. Right? So by saying we don't have any intervals, we don't have anything, everything has a single timestamp, you're forced to make those choices actively. Now, you still can make the wrong choice, absolutely, but as we'll see, ideally things can be designed so that these choices are somewhat transparent, right? And then the community can sort of comment on this. Okay? Now, I want to be very forthright and not just sort of trying to hype up MEDS here. So MEDS doesn't cover everything. What is it missing? Well, there's lots of other modalities. We already talked about images, waveforms. I haven't mentioned this. MEDS actually has another optional column for text. So we do actually support notes already, although it's not very commonly used. But images, waveforms, other sorts of things, we don't support those right now. Some are pretty easy to add, and there are people thinking about this already. Anything that happens at a single point in time. Waveforms or like wearables data, that's a little trickier because it happens over a span of time. So, there's still some thoughts to be had there, but that's one big thing. Intervals we've already talked about. Harmonization we've already talked about. Okay, so here's one that's increasingly, we hope important. If you have a data set that has many hospitals in it all at once, there's no representation in the MED schema of what site something is associated with, right? So that's something where, maybe we'd want to add that in the future. Similarly, if you have provider IDs, this is very rare, but if you had those, there's no representation of this. And the last one, did it actually show up? No. Okay, there we go. And the last one is sort of subtle, but is actually kind of important. MED says that an event has a code and a single numeric value. But there are certain kinds of health events that actually have like multiple numeric values, right? Like a medication prescription. You say, oh, take 10 milligrams for 2 weeks twice a day, right? There's 3 different numbers there. How do we represent that? Right? Now, one other reason why I'm highlighting this, beyond just to be sort of forthright about the limitations, is because MEDS is open source. It's community driven, right? So how do we plan to solve these is by having all of you think about how you'd want to solve these in your work, and then the ones that actually work will be used by the community repeatedly, right? And then we can change the standard over time to adopt these, right? So there's lots of opportunities for improvements, but you can extend the schema in your own use to include different options for things like this. Okay, so I said a lot about what meds is, but I haven't actually said much about like why you should use it potentially, in terms of what can it actually buy you as opposed to just doing your own thing. Well, in reality, there is at this point a pretty active ecosystem of different tools, such as the ones shown here, and many more in the meds ecosystem to help automate or help you not need to write the same code 15 different times for your projects when you're trying to go from raw data to models. And these tools can be reliably used across various different sources of meds data. Right. So in particular, at this point, meds has been around for a year and a half to 2 years now in various forms, depending on how you count things. And it's been used. It's been used in at least 19 different institutions. At least 14 papers have used meds in some capacity. There's 17 different data sets or data formats that have publicly available or privately available ETLs for private data only, obviously. ETLs to convert into the meds format. There's a number of different model algorithms. But most importantly, when you're actually using meds, a variety of the tools in the meds ecosystem have shown that they can offer significant computational speedups, or that by using different tools, you can reduce the number of lines of code you need to write by very significant amounts. And there's a wide variety of tools being developed or already in use in the meds ecosystem today. And we'll see some of these as we go forward. Okay. So now we're not going to go through this. For some of the collabs, I might pull them up on the slides, but we're not going to do that for this one. But again, offline, you can just go through and see with some static synthetic data, what does the meds actually look like? What are the files there in an actual sort of disk environment, things like this. Yeah. All right. So very briefly, let's say sort of what sort of hypothetical problem will we be working with in the rest of the tutorial. Key disclaimer here, the problem and the data and all of these choices made for the tutorial are not made to be maximally representative of a real clinical problem, but instead because this needs to be like a publicly available tutorial with educational utility, right? So, there'll be some things here that won't map necessarily directly to what you might actually encounter in the wild, but, we're doing our best. Also, in a real modeling task with a data set of the size we're working with, you might make very different choices, things like this. But fundamentally, this problem that we'll be working with will be of the form of I apologize again, I forgot we're doing distributed question breaks because Howard doesn't want to run around. So if anybody has questions about the med schema overall, before we move on to the problem, maybe I'll take those now.
So let's assuming that this schema works perfectly and everything is exchangeable. Isn't reproducibility more important than having the data to be reproducible? Because if you have this schema but you don't have access to the data, how are you going to reproduce the model?
Yes, that's a great question. So the question was, reproducibility of your code and your tools is great, but the data is not accessible. So why do we care, right? What can we do if the data is not accessible? So absolutely a great question, and I would love for more data to be accessible, right? But there are a couple different answers to this. So one is, that's not something that we can control as individuals in the field necessarily. Now, certainly there are things that we can do and we should do to encourage more data access, and I'm a big proponent of those, right? But the lack of data access is not a good excuse for our tools and our pipelines and the things that we're doing not to be reusable on different data sets, right? Even if you don't care about the field as a whole, which of course we all do, but even if you don't, you're just wasting your own time when you move to a new data set, right? You do a project on Mimic, and then you do a project on some private data set that you get access to, and you have to write everything again from scratch. That's sort of absurd, right? So meds provides a lot of utility even just in that sense, right? The second thing, though, that I'll say that's a less pragmatic reason is that in reality, we often end up doing a lot of things in a very data set specific manner, right? Where we need a lot of local validation of a model at a data set before we could ever consider deploying it, right? And for many data sets, especially at academic medical centers, it's a very open question as to whether it would even be beneficial to train a model at a different data set first and then specialize it there as opposed to just training a model from scratch, especially given the state of health AI research and how competitive things like XGBoost are and things like this. It's like, there's a lot of work that happens on a single data set basis, right? If you think about that workflow, then the way that science adds value to that workflow is somebody reads a paper and they say, oh, can I do that same thing on my data set, right? And that's a very different question than, that question does not require the data set on which it was initially published to be available. It just requires the code to be reusable, right? There's also more practical reasons why this matters. Like I've had data sets that I've worked with where people were very uncomfortable loading publicly available or pre-trained models onto their servers because of like data provenance issues, right? Like if you have a pre-trained language model and they say, oh, I'm not sure what the copyright on this source text was, right? And I'm not a legal expert and I'm not saying that's a sensible thing to do, but it happens, right? So there's lots of reasons to care about the reusability of code, even when data is not open.
Yeah, so thank you. Just one small technical question. So how do you propose we deal with like different units for codes? Like if a heart rate can be Celsius or Fahrenheit?
Great question.
Yeah.
So this one doesn't have it. Let me see if the other one does. No, it doesn't either. Okay, so the question was, how do you deal with units? Like lab tests have different units, and these can change across sites or even within the same source, right? And so the answer often with meds, when you say, how do you deal with some categorical change to what a measurement is, and this is not an elegant answer, but this is a sort of simple, bitter, less than friendly answer, is shove it in the code, right? So you say, oh, instead of heart rate, you do heart rate / BPM. Right? Instead of temp, you do temp/F, right? Temp/C, right? Again, not an elegant answer, but in practice, it works, right? Now, there's one, I'll give some defense to the inelegance of this answer, right? Which is, you might think, oh, instead it'd be better to have temperature and then a separate column for a unit, like Fahrenheit or Celsius, right? That way you could easily convert units and align things and do things like this. But you have to ask yourself, why are some temperatures recorded in Fahrenheit and some in Celsius, right? Is there some information that's actually encoded there that could matter? And the answer often is going to be yes. Now, I'm not necessarily saying it will be for that particular example, right? But if you're working with a multi-site data set, for example, and which actual hospital the patient is being seen at is occluded from the data for privacy reasons, but the temperature unit correlates to a region, for example, which you don't have otherwise access to, then it could be a very informative aspect of the code from a predictive perspective, right? So if your goal is to make something that's maximally predictive on a given data source, then actually sort of stratifying your code space and keeping things separate can have some significant value, right? Yeah. Any other questions? Oh yeah, okay, great.
I think there are a lot of things I like here. So one is the linear timeline, which allows you to build very fast indexes for processing the data. That's great. I have two specific concerns. One is that a lot of the lab results are not necessarily numeric values, rather relationships.
Yep.
Less than 90 nanograms per milliliter, for instance, right? And you don't know what the exact numerical value is. I think harmonization is extremely important. You did say that that's not something that you're enforcing, but how do you really make a tool reproducible unless your data is harmonized to the standards in which the tool itself was developed and validated? Second is, I'm curious to understand how you're thinking about, so EHR data often encodes for practice biases and what the insurers reimburse for. And how are you thinking about some of the defenses against such things for ensuring reproducibility with this?
Yeah, so both fantastic questions. So I'm just going to repeat them, and please tell me if I'm misunderstanding. So the first one, there was a couple of pieces. So one is a lot of lab values don't have numeric values. They have like, other kinds of values, like less than this or normal or something like this, right? And similar, second or one part two or something was harmonization maybe is more important than I'm implying. So how can this be useful without harmonization, or how can tools be reproducible without harmonization? And then third is there's lots of biases in these data, and how do we think about that and how that affects reproducibility, right? Which are all good questions. So the first one, as I said, there is actually a text value that's encoded as part of the schema that I'm not showing here just for brevity purposes. You can use that for notes. You can also use that for lab results if you want. Again, for lab results that are actually categorical, like less than something, greater than something, or like pass, fail, or normal, abnormal, throw it in the code. Right? Why not have creatinine / normal or creatinine / high, something like this, right? It shifts complexity in how you're thinking about encoding data into complexity in a code vocabulary space, which is actually something that machine learning models, especially high capacity AI models, are very good at dealing with, as we've seen by large language models and text and things like this, right? So pushing a lot of categorical things into the codes is a general strategy. And then for remaining things that are non-numeric, you could include them in the text value. Or you can also ask, what do we actually do right now in the AI space, right? Like, as opposed to some, conceptual perfect world, what do we do today? Often we just ignore those, right? We just drop them. Or somebody who has made a decision in processing the data set said, I can convert these to numerics and these ones I can't. And so the ones that they can't, they get lost, right? So, we shouldn't think that we need to capture the data perfectly to still get a high level of utility out of it. Does that answer your first question? Yeah, okay, great. So the second question was about harmonization. So you said a key phrase in your question, which I want to emphasize. You said, how can a tool be reproducible if the data is not harmonized to the same standard the tool is harmonized to, or something to that effect? Is that right? Yeah. Okay, so there's an implicit assumption there, right, which is that the tool itself is harmonized to a standard. Okay. Now, we can ask ourselves, certainly there are examples of tools that need to be harmonized to a standard, right? Certainly this is true. There are also examples of tools that don't need to be harmonized to a standard, right? Like if I ask the question, what are the most frequent codes in a data set? There's no harmonization necessary to answer that question, but that's a very important question in many cases, right? If I want to filter out codes that are rare in this data set, I don't need to harmonize to do that. I just need to identify the counts of how frequently they occur and filter them out, right? If I want to train a large, high-capacity, autoregressive style foundation model that treats all these codes like tokens in a language model and goes through and does an autoregressive model, that tool does not require harmonization, right? So there's lots of tools that don't actually require harmonization, in which case they can be used regardless of the standard of the data. Right? Now, again, I'm not saying the pre-trained model will work. I'm saying the tool to produce the model will work. Right? Now, what about tools that do require a standard to be, or things to be harmonized to? Certainly are examples of this. There's sort of two categories, or it's really a continuum, right? You have to ask how much of the data does the tool actually need to be harmonized, right? As we'll see more later, if I actually want to, extract a prediction task from a data set, I don't need the entire data set to be harmonized to a standard to do this reliably. You can actually do this by harmonizing just a very small set of codes to align to the concepts you need, right? And so you can ask yourself, do I need to harmonize my entire data set to get utility out of one task definition? Now, there are tools that require basically the entire data set to be harmonized, absolutely, and for those, you should harmonize your codes. MEDS is agnostic to this. You could take a MEDS data set and go through and do an intensive effort to harmonize all of these codes to an external ontology. Or you can start with an upstream data set like OMUP, which is already harmonized, and convert that to MEDS for high-capacity AI work and still benefit from the harmonization. Both of these are things that people, the former is something people are just thinking about. The latter is something people are actively doing very commonly in the MEDS ecosystem. So, harmonization you can do as needed or rely on it upstream, but in many cases it's actually less essential than you might think. Does that answer your second question? Okay, we'll take the rest offline. Third, there's lots of biases in EHR data. Absolutely there are. And we don't know what they are. Like not just we, the MEDS community, but nobody in this room, we don't know what all the biases are. We have some sense of some of them, but not all of them, right? MEDS tries to capture the data with fidelity to the raw data source, including its biases. And then we can study those biases as a community on top of that data, right? So we're not trying to account for these biases at all, which would be a mistake because we don't know what the biases are. But they absolutely are there, and the biases will differ across data sites, and that might be a reason why tools don't reproduce as well, or a certain kind of model doesn't perform as well in one data set as it does in another. Absolutely. That's something that I'd be very excited for the community to discover once we can actually do these sorts of experiments in a reliable way. All right, where is Howren running around with a microphone? There's one up here.
Thank you. Your schema assumes that you specify the coding schema. So it's / ICD9 / ICD10. In practical terms, when you are in a situation when you need to put together a lot of different data sources which may be using different schemas, what exactly you do?
So we'll actually see some examples of this soon in the extraction step of how codes like this actually get constructed. But basically, in MEDS, because the harmonization because it's agnostic to harmonization, you can think about this as little or as much as you want to, and it will affect certain kinds of applications in various ways, right? So in particular, as we'll see, if your data source says has a diagnostic code column and then a code vocabulary column, as Mimic does, for example, then how you might construct something like this is you say code vocabulary / code element, and you just map that function across all these columns, right? So you're not actually, there's less human thought going into this than it might seem. Instead, you're taking what the data is telling you and capturing that, right? Does that answer your question? Yeah, sort of. If you have two different data sets that you want to merge together in MEDS and they're in different coding schemes, then you either are just going to need to acknowledge the fact that you're going to have two very different code vocabularies, or you'll have to manually harmonize them, right? Which again, you can absolutely do. You can convert your data sets to OMUP first and then run the MEDS on top of that. That's totally fine and gives you benefits in the high capacity AI space still. All right, and one more question, if such exists, or we'll move on to the next part. Okay, great. All right, so yes. All right, so the problem setup. So we're imagining in this problem for this tutorial that some new colleague comes to you and says, hey, I have this great data set. What model should I build for my data, right? And I like this question because I think of this as sort of the fundamental question of predictive AI on EHR data, right? Someone comes to you and says, how should I do this thing that you've been studying, right? And MEDS is very much designed to help you know how to answer this, right? Because you haven't seen this data before, so you don't know what models actually work well on it. You need to tell them, based on the literature, we might think that this kind of model, with you trained from scratch on your data, would work well, right? So in particular, for this tutorial, we're going to pretend that their data just happens to look exactly like the MIMIC4 demo data set, which is completely publicly available, right? If you're not familiar with MIMIC, it is a publicly available intensive care unit data set that's been very widely used. MIMIC4 is available to anyone, but requires some steps to get access to. They have a demo version, which is totally open. You don't need to sign in or anything to download it. That's what will be used here. And their problem, again, designed for sort of pedagogical utility, is they say, I want to identify patients who will have a long length of stay in the ICU, right? And then you're going to help them with this modeling task in this hypothetical setting, okay? All right, so the first step of this pipeline is that you need to convert whatever data they give you into MEDS. And here we're going to mostly sort of talk through how this will actually work and not sort of dive too much into the details. That way we can talk about other parts of this on the modeling side. But their input data might look something like this. This is what the actual MIMIC data looks like. Obviously, there's many more files. These are just a subset of them. And you want to know, how do I go from this diverse set of input files with their own schema into MEDS format, right? And the reality is that based on the simplicity of MEDS, you can actually do this, generally speaking, very quickly in practice. Right? And the way that you do so is you write a configuration file like the one on the right, which basically tells you how to map every row of each given input file into one or more rows in a MEDS table. Right? And we'll see some examples of this. I don't think that's actually fully readable at this view, but yeah. All right, so in particular, we sort of assume something first. We say, we have all these different input files. We're going to assume that every row in those input files contains some observations in the data, right? And all we need to do is figure out what observations they have and map them into a MEDS format, right? Now, in practice, this may require some sort of pre-MEDS work that's dataset specific, that you might need to write some custom code for. This is true, right? Like even if you need to do some joins across tables or something like this, right? But for this tutorial, we're going to imagine that that's not an issue. Okay? So in particular, if we imagine that we have an output MEDS shard that looks like this, then we might say, okay, all of these input, these first three rows, they might all come from a record in the patients.csv file. This row might come from a record in the admissions.csv file, and this next one might come from the vitals.csv file, right? So the only reason I'm highlighting this is just to show that what we're doing, if the MEDS format being this long form here, is we're taking all these other disparate sources of data and just pushing them all into one big list of observations, right? Now you can do this the other way too. You can say, suppose that my patient.csv looks like this. This is not real data, but this is the actual structure of the MIMIC file. Then you say, I could use these two to construct one observation about the patient. A static observation about their gender. And here, when we say static in MEDS, by the way, we don't mean we're conceptually asserting something as static. We're saying, in this data set, here's something that is assumed to be constant for the patient throughout their entire interaction with the data, right? We might look at these and say, I'm going to construct a date of birth event for the patient based on these. And we might say, I'm going to construct a death event for the patient based on these columns, right? So again, we're just mapping things. Right? Now, what this really means is that you can think of MEDS data extraction by just looking at a file and asking, okay, in this row for this file, there might be multiple events occurring, but for any given event, to whom is this happening, what is happening, and when is it happening? If you can answer those three questions in a programmatic way, then you've basically written your MEDS extraction. Because the format is so simple, if you can tell me how to compile this list of events, then you're basically done, right? And there's this particular tool called MEDS extract, which again, you can use other tools if you want, that can help you actually do this, right? That can give you a format to parse or to write some of these entries in place. Now, in practice, for I think basically every publicly available data set, no, not quite every, but every publicly available ICU data set that I know of has a MEDS ETL. There's a dedicated OMOP ETL that's in pretty widespread use. There's actually a FIRE ETL that's pretty recent that you can also use. So for many contexts, you probably don't need to do this, but if you work in this field, then you will encounter data in some custom strange format that someone just gives you. And for those cases, knowing this is actually useful. Now this is really hard to read, so let me actually see if we can successfully jump over to a different tab here. So just briefly, we're going to jump into one of the Colab notebooks here, just so I can show you what the actual thing looks like. So this is one of the collabs that you could run. This is actually showing the raw mimic data, the raw mimic demo data, if you were to download it. And then what this actual notebook, or what this notebook actually does, is it goes through and just shows you the raw data and talks about how you could go through and identify some of those questions. But we're going to skip past all that in the interest of time and say that what you're going to end up with is a file that will look something like this, where what you're doing is you're constructing a YAML file that says, hey, for this input patient, there's some event that I'll call gender that has, this is who it's happening to, this is what the event is, and this is when it's happening. And you're going to build a file like this just across all your input tables. And when you're done, you can use meds extract to run this and actually extract your data, right? And so here you can see an example for a variety of different things. Now you can see that actually what we've constructed here is we're implicitly adding those parts of the code, like you were asking about before, where we have now an admission type and then an admission location. We're just putting things into the code, right? And this is a strange way to think about this if you're used to more controlled standards, but it has a lot of utility on the line, right? Shove all the complexity into the code column, and then we can work with that more easily, right? Yes, and the / here is not a meds mandated convention. It's just something I'm doing because sometimes you have slashes in your other fields, so yeah. Now there are some complexities here, but that you can see if you sort of read this in depth about different ways where you can have competing observations or you might need to do some joins, but we're not going to talk about that. Instead, we're going to jump back to this. And, oh, perfect, it just works. Okay, great. So yes, so before I move on to part 4, any questions about meds extraction? And obviously I've glossed over a lot of things here, but yeah, any questions about how you might extract something to meds? It's okay to ask questions, folks. Howard needs his cardio. No, I'm joking. Howard.
So, is meds stable? So what do I do when I get like a data set in meds that has been generated by like an older ETL pipeline? Can I trust this to be?
Okay, so this was an issue for a little while, but now it's much less of, I wouldn't be concerned about this. Initially, when we were first developing meds, we had like this nested format where we had timestamps and then a list of events happening to avoid duplication. But again, bitter lesson, keep it simple. It turns out that hurt performance, not helped it, even though conceptually you might think otherwise. So at this point, I would expect meds to be very stable. And given its growing usage, if we make major changes to data formats, then we'll also produce tools to actually map those changes forward. Now, we might do things like we might add another column that you could use if you want, like another optional column, like for images, for example, right? But this doesn't require you to change anything about your old things, right? It just updates what new data sets look like. And there also is, in that dataset.json file that tracks provenance, it tracks the version of meds that something was produced with. So we know for every data set what version is it actually present with, at least if they're formatted properly. Any other questions?
Is there consideration taken into like scaling the data set? So if everything is stored in a large YAML file, maybe it's very slow to index or shuffle, or if everything is stored as a single file, we might get file count problems.
Yes, so great question. So the YAML file here is instructions. It's instructions on how to extract your data into the meds format. It's not actually storing data in the YAML file. That would be very, very bad, as you indicated, right? Instead, the data output is stored in these Parquet files in the schema we talked about before, and those are explicitly sharded into smaller chunks exactly for this issue of scalability, right? So if you want to add more patients into your data set that are a completely different set of patients, you just add more shards. You don't even need to touch your old data. If you want to do application or do workflows that are per patient, and you can parallelize this out, only limited by the size of your shard and the number of compute resources and the amount of compute resources you have. So it is designed very much with scalability in mind. There are challenges if you imagine getting more data about patients in the future, like if you have data up until 2012 and then you get 2012 to 2015, right? And you want to merge that in. That's a workflow that we don't have optimized tools for in meds right now, but it should not cause any major problems. In fact, for most data sets, these extraction pipelines are actually very fast, even as they are.
Hey, huge fan of meds. I had a question about, I guess, scalability.
About what, sorry?
Scalability.
Oh, perfect, thanks.
So the Mimic ETL, I think it takes about 165 gigs of RAM to get it running, which surprised me, naively just thinking, oh great, this solves all my problems.
Yep.
I guess one question is, why? And then the other question is, how will that scale to bigger data sets of more patients?
Yeah. So this is a great question. So the question is about scalability. So I've said that MEDS is designed for scalability, and this is true, but it doesn't mean that MEDS is not necessarily resource intensive, right? MEDS is designed to allow you to surpass any barriers that you hit as your data set size just approaches infinity, but your resources need to grow as well to maintain certain things, right? And this is an important distinction, actually, because if you write things in different ways, like for example, if you have one massive file with all your data in it, then even if you have something that at a smaller data size uses less resources, you can rapidly hit bottlenecks that where you can't continue to scale it up even with more resources, right? Or the kinds of resources you need are simply not accessible, right? Whereas this parallelization strategy means that if you can add more machines in, then you can just keep scaling indefinitely, right? So that's one sort of meta point to make clear. The second point is, why does the Mimic ETL take 165 gigs of RAM? And the answer is because Polars is really RAM intensive, and it's very challenging to limit. But there actually are faster ETLs that people have developed for MEDS. So Ethan Steinberg from Nigam Shah's group at Stanford, although he since graduated, wrote this incredibly impressive C++ backend to do certain MEDS operations incredibly quickly through this tool called MEDS Reader. But it's something that there's less, Ethan is the only one who maintains that because it's all in C++, right? So, the community is still growing, right? So I expect that we will find ways to reduce the memory footprint of some of these operations down, especially for smaller data sets. But we have actually run these on data sets that have more than, I forget what number this is, but I know that there's more observations than there are 32-bit integers, right? And the reason I know that is because Polars crashed when it tried to store them all in one table because its indices were all in 32 bits, right? And this exact same toolkit is used to do that extraction, right? And it doesn't require, a linear scale up of RAM. It uses, a couple hundred gigs of RAM, but something that's very reasonable on sort of modern compute, right? So when you think about scalability, we're really thinking at the very large end as opposed to at the small end, and that does involve some trade-offs. But we think these can all be improved too, so please, help us out. Okay, great. All right, so that's thinking about how to extract data into MEDS format. From now on, we're going to imagine we have the data in the MEDS format. We're going to talk about how do you do other things with it. Okay, great, and we're good on time. So what we're going to talk about now is how do you actually identify a prediction task on the MEDS ecosystem. Now, in our sample problem, we said that someone was interested in identifying whether a patient will have a long length of stay, right? In the tutorial notebook for this section, we actually go through and do a lot of stuff to take this question into something that's actually an operationalized task, right? Because even though many of us are probably familiar with long length of stay, this is actually not a well-defined task right now, right? What does long length of stay mean? And when are you interested in identifying these patients? And for what kinds of patients do you actually want to do this process, right? What is the action that will happen if you identify someone in this space, right? All of these are critical questions that need to be answered to make a useful task, right? MEDS, as a data standard, is not something that necessarily helps you answer those questions, right? Some of the tools are very aligned with how thinking about asking those questions in the right way, but MEDS as a data standard is not in and of itself concerned with those questions. Instead, what MEDS tells you that relates to prediction tasks is how to represent that you're trying to make a prediction at a given time with a given target label, right? So this in particular is the MEDS label schema, which I showed at the beginning as well, that shows how we think about tasks in the MEDS ecosystem. And this is actually very important because you can have all kinds of strange tasks in EHR data. You could have a task, for example, that says, I want to take all the patient's data except for this bit here in the middle, and then I want to predict something about that bit in the middle, right? MEDS label schema explicitly does not cover that kind of tasks, right? Instead, MEDS says, okay, the tasks that we are going to standardize around are tasks where you say, for this given subject, if you use all the data up to and including this prediction time, or data at that prediction time, can you predict the following label, right? Now here I'm just showing a Boolean value label. There are other columns here as well, right? I've omitted them for, you could have a numeric or a categorical or things like this. But for this tutorial, we're just going to think about things as binary classification, just to keep things simple. But fundamentally, we're saying, for this subject, up until this prediction time, let's predict a label, right? Now, the reason to omit all these other kinds of tasks is mostly, again, for simplicity, and because most of the time in the real world, when we actually want to use prediction systems for decision support, for example, we're interested in identifying some prediction about the patient in the future, right? And that's exactly what this is designed to capture. Now, I want to note one small thing here, which is a convention that's not a mandate in the med setting, but you can actually think of this prediction data frame as being meaningful even without the labels, right? You can say, oh, smart. Okay, I'm inferring from Halloran's activity that we are changing the question strategy so that people should come up to the mic if they have a question. Is that right? Okay, great. Thanks, Halloran, for your cardio exercise so far. And so this means that actually people have questions throughout. Just feel free to come up whenever. I may still stop, but please, I'm happy to answer questions whenever. So we may call a data frame with just these first two columns specified an index data frame, because this is still telling us something meaningful. It's saying, hey, I care about something for this patient at this time, right? It's identifying amidst the entire history of this patient's data, where are the points when I actually care about things? And there could be many for the same patient. There could be just one for the same patient. It really depends on what kind of task you're specifying, right? But it's important to think about storing these in this sort of a format here, this long form, because we can't recapitulate all the data about the patient that we could include in this input without duplicating all of this patient's data many times, right? So all we're doing is we're saying, where should you look? We're not extracting the data again for these inputs. And then if we include the label, then we can think of this like a prediction task, right? Where now we have a target to predict as well, okay? Now, the tool that is most often used in MED's efforts to identify labels, although again, you can use whatever tool you want, but the tool that's most often used is ACEs, an automatic cohort extraction system. Oh, I should have said what MEDS actually stands for. Medical Event Data Standard, although as with many acronyms, we had to think really hard to find one that works. But now it's just called MEDS. But so ACEs is a tool to extract prediction task cohorts, okay? Now, ACEs is actually theoretically independent from MEDS. You can use it with other data standards as well. So you might ask, why am I including it in the MEDS tutorial? And I promise the answer is not just because I'm one of the authors on ACEs. The answer is instead is because it's a great example of the kind of tool that requires some degree of harmonization, exactly as the gentleman over there asked earlier, right? Because to define a prediction task, you need to know what kind of events do you care about, right? So let's talk about what we think of as a prediction task in this space. And really what we're going to zoom in on is this middle section in this poster here, this in particular, right? Now, I like to think about things visually. Not everyone's a visual person, but apparently I am. And so much like I said for EHR data, we all have this picture of this timeline in mind. When you think of a prediction task, you might ask yourself, what picture should I have in my head there, right? And increasingly, I'm convinced that the right picture to have is something like the one on the top, right? Now, let me explain what this picture actually means so you can understand. But what I'm showing here is, imagine that this is the patient's timeline. This is their data occurring, right? Not necessarily their real timeline, right? But this is a hypothetical timeline. And what we've done here is we've identified some key points in this timeline, right? So we said, I care at point C. Point C is an admission. The patient was admitted to the hospital, right? And then what I'm doing is I'm defining relative regions of that patient's record relative to that event, right? So I say, this window B in blue ends 24 hours after that admission, right? The yellow window in D ends 48 hours after that admission. And I can say that this point at the end of E on the far right, we can say, that is a discharge or a death event. And in particular, it's the next discharge or death event that occurs for this patient. And so we can identify a window that spans all the way up until that point as well. Now, the reason to have this picture in your head for a timeline is because what you can do with this picture is you can say, what constraints do I want to impose about patients to be included or excluded from my cohort based on these relative windows? And that gives you a vehicle to think about what do I care about and what kinds of patients do I want to include and when do I want to include them, right? So in particular, we might say, I want the patient to have at least 5 events in their prior history. Right, in window B. I want to have some data I can ingest to make my prediction, right? That's a logistical prediction, right, or logistical aspect. I might also say that there's should be no discharge or death events in window D, right? I want their record to be at least 48 hours long without anything to happen, right? I want some gap window, so I avoid future data leakage, right? And I might not need to impose any constraints on window E that goes up until the discharge or death, right? But then what I can do is I can say, if you have patients who satisfy those constraints, then what I can do is I can make a prediction from the end of window B, using all that data, and predict whether or not there is a death event in window E. And what I've just defined for you is a mortality prediction task. And it's precisely a mortality prediction task that's encoded in this simple configuration file example shown below. Right? So you'll note here that I've been using terms like admission, discharge, death, but those are actually things that need to be harmonized. Right? Those are codes that could have any form in the data set. Right? So how do we do this partial harmonization? Well, you just include this little block in A defining these what we call predicates to say, here's what these codes actually look like, right? So admission might be this particular string, discharge might be this string, and discharge or death might be this, and then discharge or death is this very simple Boolean logic, right? Now, in this example, these are very simple. You could include things like regex values as well. You could have numeric value ranges, or you could have text value matches as well. But this shows that to define this mortality prediction task, which is a very simple task, all you need to harmonize are those concepts, right? And then everything else here, we've captured some meaningful constraints about the patient. We've captured a gap window, and we can define what we care about, right? Now, this is not just a hypothetical example. It's not the example we're using in this tutorial, but it's not a hypothetical example, because that quote that I showed you from Alistair's paper in 2017 that was saying we can't reproduce even the basic task extraction on Mimic3 for all these papers, what task were they trying to reproduce? This task, right? So here, we've solved that reproducibility problem. You can write it down in this config that can be shown on this one slide, and then you can deterministically extract it from any meds data set, provided you tell us those 3 codes, and that's it, right? So that's one way to think about defining these tasks. Now, in this case, the task is different. The task is interested in the patient whether they have a long length of stay, right? Now, as I said, even though this is not about the data standard, you need to think about how do I translate this into an actual meaningful task, right? I learned recently that this joke of the person looking under the streetlight because that's where the light is, even though they lost their wallet 3 blocks away, right? Apparently, this joke dates back to the 12th century. So it's been a problem for a really long time, but it is still a really big problem in health AI, right? We define tasks all the time that are very poor. In the example notebook for these slides, we'll see a way to think about going through and revising that. That's sort of orthogonal to meds, but very relevant with this view of tasks in this form, because you can ask about what are these windows and things like this. But I want to point out another benefit of having things be expressible in this sort of simple configuration file language, which is that then we can actually discuss things by as the community and collectively identify, are we actually measuring what we value, right, as opposed to valuing what we measure, right? So this is an example of a GitHub issue on a benchmarking platform in the meds ecosystem for discussing a readmission risk prediction task, okay? Now, 30-day readmission risk prediction in EHR data is very common, right? And it's often said to be useful because there's this hospital readmission risk reduction program in the United States that penalizes hospitals financially if they have high rates of 30-day readmission, right? Something I didn't know until we started having discussions like this, not exactly this discussion, but discussions like this for this task, was that in fact that hospital readmission risk reduction program has a bunch of conditions. It doesn't care about all readmissions equally. It only cares about certain kinds of readmissions for certain classes of patients, for certain kinds of hospitalizations. And basically all of those factors are things that as a community, we functionally ignored when we use this in our modeling pipelines, right? So we have not been doing a good job of measuring what we value, right? But when we have configuration files like this, it can lead to really great opportunities to discuss things as a community and fix this. Now, this is about something more technical. It's about censoring. But when I say this can be discussed, I do really mean discussed. Because this is a GitHub issue. It's that little tiny rectangle from that entire conversation shown on the right, right? So this was a very active discussion that just happened because we put a configuration file up there and said, hey, this is our readmission risk reduction. This is our readmission task. And people had lots to say, right? So I think this can be really beneficial to the community. Now, this is best illustrated with these ACES configuration files, but it actually also applies to those extraction configuration files we were seeing before, right? Having simple, semi-readable instructions for how you should do these tasks that can be transported across data sets lets us optimize them as a community much more effectively. Okay, so what actually are we doing in this? So I'm not going to go through the Colab, and I don't think you can read that on the right at all. So I'll pull up a Colab notebook so we can see an example here in more detail. But we can develop a final task for our thing. We can identify some comparisons. What I do want to do, if I can, is try and do one thing, which is there's also this benefit. Does this work? Yeah. There's also this benefit where you can actually take those ACES configuration files and programmatically construct visualizations that are sort of like the one that I showed initially. So what we can do is we can take that big configuration file that I showed before, and if I can find the mouse, then I can scroll, and we can actually run some code to produce a little plot that actually tells us about what is this timeline that we're actually producing here, right? And we can say, oh, here we have our trigger on ICU admission. We're imposing some constraints. Oh, the hover's not working. Okay, so theoretically, if you hover, it would tell you the actual constraints here. It does work normally, but I think because of the Wi-Fi issues. Oh, there we go. So we can see that this window has, again, I can't see that. has no death, and we can see that this window has no comfort measure orders or do not resuscitate orders in place. And then there are some other constraints that are imposed on the input window, right? So you can actually do things with these files as well beyond just run them. You can use them to understand tasks in a different way, right? This is obviously still something that's sort of in development, but it's a good example of opportunities here. Let me just show the actual final configuration file a little bit more. So this is the example for extracting a prediction task. Let's see the actual final one. Here we go. So it ends up being a little bit more involved, where we've added some constraints here to say we want to exclude patients who are known to be high acuity already, right? Patients who are, have CMO or DNR values. We're using regexes here to match codes as opposed to static values. We're matching to particular text values as well. We're using some of these expressions as well. But then we have a very simple logical set of constraints on these windows that are, again, just dependent on those small set of predicates that are actually the only thing you need to harmonize to apply this to a new data set, right? And I'm not going to talk about the benchmarking system too much in this, but these files can really reliably be used across many data sets very easily. Okay, so any questions about extracting prediction tasks?
Yeah, hi. One quick question is, when you're working with these kind of data sets, inevitably you will want to define some prediction task, like from your original data set, like the pre-sort of meds thing. Like, let's say you're doing it on waveform data, which isn't represented in meds.
Yeah.
You want that to be, to define some sort of index event, and then use that as sort of your index event for labeling. How well can meds sort of map back to your original data if you need to do something like that?
Yeah, so fantastic question. So the question is, and everything I'm talking about with ACEs, it's all about this logic that's within the meds space, right? But meds doesn't cover everything, and you might have colleagues working with raw data. You might have a task defined in that space that you want to study with meds. Everything I've been saying about ACEs doesn't help you do that, right? So how do we solve this? Well, again, meds is a data as interface standard, right? You don't need to use the same tool, right? So ACEs is a way to get a file like this, a file that says, here is a prediction time and a label. But meds doesn't care about how you get there. It just cares about this file, right? So you can define a set of subject IDs, a set of prediction times, and a set of labels based on your raw data and use it just fine within meds, right? Meds models, when they're predicting things, they need to take, if they're wrong in some way, shape, or form, then that may not work. And there are some strange examples where they actually rely on having a configuration file for like zero-shot prediction, where the model needs to actually know what the task is in a programmatic sense, right? But for simple things, if you have a file, that's fine, right? So it's actually completely seamless to take tasks defined from other spaces and use them in this way, right? And you can actually do one better than this, right? In some settings that I've been involved with, we don't just have tasks that we care about, we actually have prediction, we actually have splits, like held out test sets for particular tasks that do not necessarily intersect that you might need to care about, right? And so I haven't talked much about the split file that meds includes, but meds has a file that actually says for every subject, what split do they live in? And it has a dedicated training set, training split, tuning split, and held out split. But you can add more splits to that as well. So you can actually have dedicated splits for those extra tasks, store these sorts of files, and then have many meds tools just reliably only use the intersecting train set and still be able to make predictions across all these things however you'd like. So it's pretty reliably usable in that sense. Yeah. And I'll say one more explicit thing. This prediction time does not need to have any relationship to the actual data times. It does not need to match. It can be way past the end of a prediction patient's timeline. It can be before the beginning. Again, models may may make assumptions that are not met, but in general, you can use any data up to and including this time, and that's the only limitation that people should be holding in mind. Yeah. Okay, it looks like no other questions on the labeling side of things, so let's talk about actual models. Now, there's two parts to modeling that have Colab notebooks. The first one is building tabular baseline models. Meds is not designed for this, fundamentally. It's designed for high-capacity AI usage, right? This doesn't mean that you shouldn't be running tabular baselines, and this doesn't mean that Meds actually, it turns out, is actually pretty good for building tabular baseline models all the same. But that's not really the point, right? So I'm not actually going to go through this in too much detail. I'll say that there are some dedicated tools for this, like Meds Tab, and there are some nice ways to think about what a tabular model actually means on Meds data, right? In particular, to think about what code should I aggregate over what time frames, in what ways, right? If you can answer those questions, you can extract your tabular features and train a model like an XGBoost. Instead, I'm just going to leave, this will be in the slides accessible if you want to go through and see an example of this. But what I'm going to talk more about is the part that MEDS is more designed for, and I think will be more of interest to this community, which is building these high-capacity neural networks. Okay. Now, the challenge with talking about the high-capacity neural networks is that it's complicated, right? And the things that we actually need to do this effectively get very detailed very quickly. So I'm going to do my best to sort of navigate that landscape appropriately, but please come up to the mic, ask questions throughout, yeah. So when we think about modeling, I want to take us back to this picture for a moment, right? MEDS has a number of different tools you can use. We've already seen some of these. But there's really two key parts to modeling that are important for neural networks especially. First is the pre-processing of the data, which includes a lot of things to get the data in the form that the model can easily and efficiently use it on GPU resources. And the second is the actual modeling, of course. But first, on the pre-processing side, there are a number of dedicated tools that you can use. Things like MEDS Reader, that I already mentioned, has this C++ backend to actually run things incredibly quickly. MEDS Transforms is another tool. We'll see more examples of that in this tutorial. It, again, appeals to this sort of configuration file view where it's trying to define the operations you're performing on the data in a somewhat human-readable sense. We'll see more examples of that soon. And then on the modeling side, there are other libraries that, again, you can use to really accelerate your work. In particular, the two that I'll highlight here are MEDS Torch and the very related MEDS Torch data. So we'll see MEDS Torch data here in use a little bit, but basically what MEDS Torch data does, it tells you how to efficiently put the MEDS data from the Parquet format, which is great for like data pre-processing and analytics, into a form that's really great for efficient GPU use, right? We're talking about foundation model scale here. So what that really means is we want GPU utilization at 100% with basically no CPU resource overhead that's significant and no spin-up time, right? And MEDS Torch data helps you do that pretty reliably. MEDS Torch was the precursor to MEDS Torch data, but includes a bunch of other things that MEDS Torch data does not on the modeling side as well. So it's still worth knowing about. Okay, so we have a Colab notebook here that the link is included later that actually builds a simple convolutional neural network model and uses it to train a model for the particular prediction task we extract in this notebook. But I want to talk through a different example first because I think it's good to see multiple examples. In particular, this is an example that is very relevant today because it's an example of one of these foundation models that are being built on EHR data. So this is called MEDS EIC-AR. EIC-AR stands for Everything is Code and Autoregressive, and you'll see why those are used later. But as a quick recap, why are we thinking about foundation models and what does that mean? We're all familiar with language models at this point. We've all seen, ChatGPT. We've used it probably today. But language models are just taking a sequence of words and predicting what word comes next. Okay. Now, the reason I show this, even though it's very familiar to everyone here, is because, well, EHR data is sort of like a sequence, right? It's a continuous longitudinal timeline of complex observations. So what if we just take, instead of what word comes next, what observation comes next, and build a foundation model in that sense? Now, I'm not going to justify too much why this is a foundation model, but I will say that if we could do this, then we could produce possible futures for patients, right? We could auto-complete sequences, which means that I could ask a question like, for this patient's EHR data, what fraction of their possible futures would have persistent knee pain? And I might say, 2/3 of their possible futures have this, so I'm going to predict 66%, right? So in this way, you can actually make zero-shot predictions from a model like this. Okay? Again, this is not really the point for this tutorial. The point is just to see how to build this sort of state-of-the-art kind of model, but worth noting. Okay. Also worth noting, again, this is not just a sort of hypothetical point. At this point, this has been pretty widely validated in the literature from a number of papers, including some of these shown here. But more have come out since then, I believe. Okay, so last point here. When we're trying to think of this model, I say what observation comes next, and we think, I'm just going to predict just like this. But in reality, this isn't quite enough because I'm ignoring the gaps in time. And I haven't told you how I'm going to deal with the fact that there might be multiple observations at a single point in time, right? Sorry, I forgot one point. This also reveals why that simple format of MEDS is coming back to help us again, right? Because really what we're doing here is we're just predicting the next MEDS row, right? That's it. That's sort of, we've directly encapsulated how this simplicity is already coming back to benefit us. But what we're going to do to actually make this work is we're going to convert everything into this sequence of categorical entries, right? And as I said before, these categorical entries don't need to be harmonized to a particular setting. So this kind of foundation model does not require you to actually harmonize your data. We're just learning relationships between codes. So this is what we're going to do. We're going to need to do some pre-processing to first do a transformation into this sort of sequence of tokens. And then we're going to need to do some modeling to actually predict the next token. Right? And we're going to do this with this MEDS EIC AR model. This is not yet published or anything, but it is all publicly available. You can go use it. It works on any MEDS data set, by which I mean I've used it on 2 distinct data sources, and it worked on both. So we're good for sure. But it should, it's actually completely agnostic to the data format and should work reliably. Yes, does anyone have any questions on the setup before we actually talk about how we're implementing this? Yeah, you should walk to the mic though.
I have a question about unstructured data. Mm-hmm. Have you, because the paper you mentioned from EPIC, they also mostly, mostly based on structured data, but in practice, we deal more and more with the value of unstructured data. Some of the stuff there is not represented in the structured data.
Yes.
So how is it incorporated into schema?
Yes, that's a great question. It is a little bit outside the scope of the tutorial here, right? Because the answer is it's not. There's lots that we could talk about. Like, it's a great question. We could talk lots about how it could be, how it should be, what the challenges are, much of which, again, though, is outside the scope. So I'll save some of that for offline discussion. But I will say that fundamentally, this picture doesn't need these things to just be structured. You could take an entire node, tokenize it into a sequence of tokens, and just shove it right in the middle there, right? The problem becomes one of dimensionality, sequence length, this sort of thing, right? Yeah, there's lots of interesting things to talk about with that challenge, but I'll save that for an offline discussion. Yeah. Any other questions about the setup? Okay, great. So, so MEDS EIC AR, as with many MEDS tools, it can be very easily used sort of on the command line. I haven't actually showed this in any of the collabs, but basically everything we've talked about, at the end of the day, you run something like this on the terminal, and then you're done. That's all you need to do, right? So for MEDS EIC AR, you install it with pip, you pre-process your data, you run pre-training, and then you generate trajectories. And this is it, right? And again, this has been reliably used on at least 2 different MEDS data sets. No, I think 3 actually, yeah. Without, well, with some issues, but largely speaking without any issues. How does it actually work? And where are we seeing benefits? Well, let's start with one of the most important pieces of building a neural network model is the data pre-processing. Now, this is the part where we need to convert everything into tokens in MEDS, right? Now, the wonderful thing about the MEDS ecosystem is that we can actually do this for MEDS EIC AR with basically no specific code. Instead, we literally just write a YAML file like the one shown on the right, right? This YAML file is telling us a sequence of stages to run in a pre-processing pipeline, and then there's going to be a dedicated tool, MEDS Transforms, which we'll talk more about in a moment, that actually runs these, right? But these stages do things like they add those time delta tokens. Let's say we want to know how many years are between certain events. They do things like they count the number of codes, both how many subjects, how many occurrences they have. They filter measurements out that are sufficiently rare. They filter subjects out who have too little data. They fit quantiles to numeric values. And then they actually bin those numeric values into the code with these quantile fits, right? Now, the reason I'm showing this is not just because I want to emphasize the sort of value of having tools in an ecosystem, but again, none of these operations require you to harmonize your codes, right? So you can get a lot of value even just with a technical standard, right? And even more if your data is actually harmonized in advance. Right? So MEDS Transforms is the tool that actually runs this. It's designed to take YAML files like the one that we just saw or like the one on the right and run them in a again, thinking mostly about the high capacity, very large data set setting in a scalable fashion in parallel across many machines. It has similar problems to MEDS Extract and the Mimic ETL in that it is pretty memory intensive. In fact, MEDS Extract is built on the same core technology. But what it allows you to do is both run pipelines like this of stages, but also to define custom stages yourself that you want to run on your data that can then be included in these pipelines by you or by others who use your code actually down the line. Okay? So this way we don't need to reuse or we don't need to rewrite our pre-processing code 10 different times for 10 different data sets. We can do things more transported. We can do things in a more efficient manner, right? What about the actual pre-training step? What does our model look like? Well, the model actually here is very simple because, in fact, we've done a very good job in the artificial intelligence community of making modeling code very reliable and shared. You could write a convolutional network, a transformer, things like this. Here, what we're doing is we're taking a Hugging Face model, Oh no, that's not the right. We're taking a Hugging Face model and just using that to run these data through. But you could imagine replacing it with something else. Now, obviously, I've omitted some of the code here for brevity, but not too much. Mostly, I've just omitted like comments and doc tests and things like this. Now, I'm glossing over one big part here, though, which is the most important tool I really want to emphasize in this modeling section, which is in this function. Again, I don't think you can really read this on this screen, so I apologize. But what this is highlighting is there's an object being passed in that's a batch to this neural network, right? And actually, how you get your batches is really important. I told you how you did some pre-processing. I haven't told you what your PyTorch data set looks like, right? Well, it turns out that these batches actually have a nice form that you can get with yet another tool in the ecosystem, MedTorch data, right? And this one allows you to go through and actually both do some additional pre-processing on your data to get it into a tensorized form, and then very efficiently load it onto the GPU for efficient use of your resources, right? So I said it does some pre-processing itself. What does its pre-processing look like? It's just another set of stages in the Meds Transforms library, right? So you can very easily sort of look at this and interpret what it's doing in some sense, or use these in your own pipelines and extend them in certain ways. I'm not going to go through this in too much detail, but what I do want to talk about is what does this actually give you? Because MedTorch data has this wonderful property that you can use it on any Meds data set, right? Regardless of what pre-processing you've done to it in advance, as long as it's still in the Meds form, right? And what you get out is a PyTorch dataset class that you can run that will give you a set of batches that look like this. This is actually the printed output of a batch in an example setting, right? Obviously, it's not, actually giving you a text thing. That would be crazy. But this is just a sort of pretty print view of this. But it gives you these tensors for the time delta in a certain unit between the events and the data, for the code now in integer index form for an embedding layer in a PyTorch model, and for the numeric values, and a separate mask for numeric values so you know which numeric values were actually present or absent in the data, right? So you could take any Meds data set, run the MedTorch data pre-processing, and then have a PyTorch data set that you could iterate over for your custom model as long as it can process batches in this form. That's what the Colab notebook actually does here for this. Meds EICAR does some other stuff first, but fundamentally, once you have this view, you can write your model, right? Now I want to emphasize something here, which is this is a very specific kind of modeling structure, right? In particular, we're still in this continuous time, irregularly sampled space. We haven't binned everything into hourly buckets and now have a regular sequence, right? We're still telling you exactly how long there are between these events in a time delta, what the time delta is between these things. And that time delta can be 0 because events can happen at the same time. So this reflects both a limitation, like, there's lots of older styles of models that relied on things being regularly sampled, doing imputation to get rid of missing values, things like this, that Meds is sort of, doesn't, or this Meds Torch data does not support right now, but also it represents a difference in philosophy, right? Years and years ago, when we would have said that imputation and missing values are really important to deal with in processing EHR data, what that in some sense reflected is this belief that we should really think about these as regularly sampled time series under the hood, where we just have missed a bunch of labs throughout that process. Meds is saying that's actually not the right way to think about this. Meds is saying, in reality, we have no missingness here. We have a sequence of observations in time, right? Now, because you don't have an observation at a particular time doesn't mean it's missing. It means it was not chosen to be observed there, right? And now, with modeling technologies like transformers and even temporal convolutional networks to some extent, we have better tools to model these sorts of irregularly sampled objects, in theory. Right. So that's an important caveat here, is that this is a particular kind of model that represents sort of most recent approaches. Right. You can also do what Meds EICAR does, convert everything to codes, and then just ignore the time deltas, ignore the numeric values, and you just have a sequence of codes. Right. That works too. Worth noting when you do this, you get basically, depending on your settings, you can have basically perfect GPU utilization throughout training with very low CPU resource utilization, even when your data sets are quite large. There's lots of reasons for this under the hood that I'm not going to get into that involve sort of putting data into a particular tensorized form for efficient retrieval from disk. Right? Yes. Also, you can, again, really benefit from the advances we've made in other areas of AI and develop things that can actually have very smooth training curves and show really nice sort of convergence properties. This is not going to apply to all your models, right? This is more a function of the model and not the data. But by putting this in a way that allows you to reuse engineering effort across efforts, you can actually much more reliably get properties like this. So the Colab notebook for this section goes through a different modeling thing that you can explore on your own. It's a less practical model. It just goes through and builds a convolutional network on top of the mimic demo data set. But you can look at that code. You can also look at the raw code for MEDS EIC-AR and try and better understand how these models are built. They both use the same set of tools. So in the CoLab, you'll see MEDS torch data being run to preprocess your data, and then a simple convolutional network being built on top of that and trained right there in the CoLab notebook. But hopefully this gives a sense of how you could train these high-capacity neural network models on this space. Now we're almost at time, and I just have some concluding slides here, but does anyone have questions on the neural network side of things before I move on? Really, I would have guessed that section would have had the most questions, not the least, but okay, thank you. Proving my intuition right.
Yeah, just a quick question about this absent data.
Yeah.
So how you are basically training, or how the model will adapt? I think you also mentioned a little bit about transforming possibility, but how these models will adapt when the absent is basically part of the documentation approach rather than the overall standard for documenting this. So that these are not mislearning, or the models are not misleading by this type of absent.
So when you talk about absence here, you mean like missing data? You mean like data that's not measured?
Exactly, yes,
yeah.
yes, I'll measure that.
And I think you're also alluding to the fact that the patterns that we use in clinical practice about when we choose to measure certain things are potentially informative signals, but maybe biased signals in comparison with the underlying biology, for example, that we might want to learn. Is that right, or am I misunderstanding? Yeah, okay. So this is a good question. So I sort of was a little dismissive about missing this a moment ago, and I said, oh, in reality, there's nothing missing, it's just different choices are being made. And this gentleman very correctly points out that those choices can be different across institutions. And so if we learn a model on one institution, it may just be learning about those patterns and not generalize to another because of those patterns, right? This is absolutely true. It's absolutely a very good thing to be concerned about. It's really going to mostly, or I would speculate that it would most likely affect you when you're trying to transfer a pre-trained model from institution A to institution B, as opposed to when you're transferring an algorithm to produce a model from institution A to institution B. Because the algorithm can learn about institution A's choices, and it can also learn about institution B's choices when it's training from scratch, right? So we're not necessarily, because our goal is the transportability of algorithms first and foremost, it's not necessarily a showstopper that the models may have this challenge in this point, right? Moreover, what I would say as a more philosophical point, though, is that there's absolutely good questions to ask about, are we trying to learn about biology? Are we trying to learn about clinical practice? How can we separate causal effects from correlative effects? Good questions to ask that I don't know the answers to, right? And I don't think anyone really does, right? Different people have different perspectives. But what I will say is that if your goal is to make the best model you can for a prediction task on a given data generative function, right? Like I have a data set, I'm assuming my test data is just IID samples from this, I want to maximize performance in that setting, which has a lot of utility in many cases. Then I don't care in that particular context if something is about the patterns of when things are chosen to be measured, or if it's about the underlying patient's physiology. Right? I want to use both of those sources to the best degree possible to maximize predictive power, right? And so from that perspective, or said a different way, what I want to do is I want to best model the dynamic healthcare process at a per patient level as I can, which includes both choices the physicians are making and things that are changing in the patient's body, right? So from that perspective, it's not a problem that these models can pick up on these things. It's actually exactly what we're telling them to do, right? There's absolutely good research to be done on how can we separate those two things, but I would view that more as a research question to be used or not used in different cases as appropriate. Yeah.
So, have you received clinical feedback on the explainability of these models?
So that's a great question, how explainable the models are is something that is sort of outside the scope of on the med side of things. It's really just about the models themselves. MEDS has been very much built and used in the academic research space. And so there's less that has actually gone through with sort of deep interrogations about explainability. What I would say, though, honestly, is that, well, A, there are some challenges with explainability in general that I think we underappreciate in the field. And B, I think having a standard and having a canonical data view would be really helpful with explainability in general, right? Would allow us to better understand which signals are valid and which are not valid. So I suspect that this would be a boon to those efforts, but it's not something we've looked at. Yeah. Yes?
Actually, this kind of builds on that last question. So this is kind of maybe a closing 30,000-foot view question. So as an example, last night I was listening to a podcast, and one of the major societies in trauma has gotten a large amount of DoD funding to build kind of standardized definitions for even the most simple variables, like, as you talked about, length of stay in a post-surgical patient, okay? because those things are not even standardized in terms of the multi-institutional clinical trials that are being performed in our specialty. So you obviously make an argument as to how this fits into that kind of broader view. And I'm wondering, for all of the people here who are data scientists working with these groups that are trying to establish definitions for these broader terms, how do they make the argument that this is the method that we should be using to actually operationalize and standardize these qualitative discussions that these groups are coming together to now form definitions for?
Yeah, it's a fantastic question. And I think there are lots of efforts like this that are trying to do more of the sort of conceptual harmonization piece. And those are very important, not just for non-AI workflows, but in AI as well. We need to harmonize, things on a case-by-case basis, or in some applications much more holistically. Now in meds, obviously, we have these tools like ACEs that let you do this on an as-needed basis. But those, I would not necessarily say that those are really trying to solve the fundamental problem you're alluding to. They're not, in fact, your question was, if I remember correctly, was phrased, how should those people make the argument that this is the tool to use to operationalize that? I would say they shouldn't, right? This is not the tool that they should use to operationalize the question of conceptual harmonization. This is a tool that they should use in addition to how they're harmonizing their data to operationalize the technical aspects of how do they want to work with these data most effectively, right? Once the data is harmonized, that's just a change in the code column for these sources, right? Now, certainly there may be choices to be made about how do you do a code in meds for something that doesn't quite naturally fit. If somebody wants to standardize the notion of a visit, for example, or something like this, as OMOP does. And those choices are important, but they're not particularly interesting conceptually. They're technical choices we need to make and align on as a field, but they're not really the same kind of discussions as you're alluding to, I don't think. And I think, we can do the harmonization, we can do the standardization, and we can get benefits from both and then put them together seamlessly, is how I would frame it. Does that answer your question? Yeah. Great, thanks. Any remaining questions on this or on any other parts before I do some very brief closing remarks? What I do want to say that's new is one additional thing, which is all of these have been talking about different ways to use meds in the context of empowering your individual projects. There's also a question of how can meds empower us as a community? And I think that question is important, even though it's not really the question that I think people should be thinking about when they're trying to build something like a standard to help empower a field, because the field moves as individuals move, not as a collective whole. But it is really important in meds to realize that if what we're doing is we're making reproducibility of these algorithms trivial, then when we should be able to make this not just trivial in theory, but trivial like one click, and you can do the entire pipeline to reproduce an experiment on your data. Now, this is something we're trying to capture in meds dev, the meds decentralized extensible validation benchmark. As I said, we had to think about acronyms a lot here. But this does have an API that looks like this, where you can actually build public data sets, extract certain predefined tasks, and train models from scratch, just based on things like the name of those resources, if they're included in the meds dev system. And the hope is to use this to establish benchmarking results that can actually go through and tell us about, I don't have the benchmark results shown here, but that can actually tell us about how these algorithms work on real data. And so, yeah, in particular, I think encourage people who are interested in this space to come talk to me after about how we might be able to extend this into a more full, complete system. Now, I want to acknowledge Camilla, Justin, and Ethan in particular, among all the other people in the meds ecosystem who helped prepare materials, because they directly made different chunks of some of these notebooks that you might look at if you look at the slides. And I also want to acknowledge just everybody else in the meds community who has helped contribute to all of these efforts. I'm probably missing some names here because it's a large and ever-growing community, but it's really been a fantastic collaborative effort. I think Jason Fries is in the back there. Has been his group and folks have been particularly impactful in this effort, along with many others who I'm sure I'm not seeing in the crowd. But yes, this is an incredible example of the community really coming together to try and build a tool that we can all use. And with that, I'll stop. And I'll say, we have some workshop paper. We actually have a formal paper under review, so we might have a formal archival submission soon. But yeah, I'll stop there and say thank you all very much for your attention.
Hey, hello and good morning, everyone. My name is Tazmi Sarkar, and I have the privilege of serving as the Executive Director of ALI, which is the Association for Health, Learning, and Inference. And it is my pleasure to welcome you all to beautiful San Diego for the 5th Annual Machine Learning for Health Symposium. So as many of you may know, our mission at ALI is not just to host events like this, but to build and support the growth of the field at the intersection of health and AI. We try to achieve this by promoting open science, broadening access to resources, and providing direction through thoughtful leadership. This symposium is a reflection of that mission. Ollie brings together a vibrant community, interdisciplinary community of researchers, clinicians, engineers, policymakers, and innovators. And your contributions and commitment to this community is what makes gatherings like this very special. The real impact happens in conversations you'll have, the ideas you'll exchange, and the connections you'll make, and the collaborations that will take root over the next couple of days. I'm very proud of how far we've come, and I'm very deeply grateful to each of you for your contributions and your continued work and enthusiasm. I also want to take a moment to thank our sponsors. This year's presenting sponsor is the Tianqiao and Chrissy Chen Institute. The Chen Institute was founded in 2016 with a vision to improve the human experience through understanding how our brains perceive, learn, and interact with the world. Its global platform comprises 4 key facilities, and they have recently launched several initiatives to advance neuroscience research. These include the Chen Scholars Program, which supports early to mid-career scientists, the Chen Institute and Science Prize for AI Accelerated Research. Additionally, the Chen Institute produced AIAS 2025, an annual conference exploring groundbreaking AI advancements that are reshaping scientific discovery across multiple disciplines. We're also grateful for the support of our other sponsors, Microsoft, Optum, Google, Path AI, Oracle, Schmidt Sciences, ADI Lab, and Quanco for helping us expand the ML4H community this year. Their support enables us to broaden our mentorship and our travel award programs for students. And I also want to extend my gratitude to our outstanding organizing committee. They have put together a fantastic program, which our general chairs will share shortly. So whether you're here to present new research, connect with colleagues, or simply be inspired, I hope you find this gathering intellectually rewarding as well as personally energizing. So thank you again for being here, for traveling from near and far, and I hope you enjoy the next few days. Thank you.
Thank you, Tasmi. So hi, I'm Peniel. I am a senior researcher at Microsoft Research.
And my name is Hara. I'm a 5th-year PhD student at MIT.
And we're general chairs for ML4H 2025. So welcome to ML4H. So ML4H has been around since 2016. We started out as a NeurIPS workshop, and since 2021 have been our own standalone workshop. And over the years, we've seen an increase in both the number of submissions across proceedings and findings, as well as an increase in the number of accepted papers in relation to the increase in proceedings and findings. In addition, we've seen sort of trends of differences of the most popular topics, where at the beginning we were seeing more topics related to explainability and causality, whereas now we see this shift towards more similar to what we see in ML conferences of now this focus on multimodal learning, medical imaging, and LLMs and agents.
All right. So this year we had close to 300 submissions, 2/3 of which were proceedings papers. And from that we accepted 74 proceedings papers, which are fully published, fully fleshed out archival papers, and 71 findings papers, which are more half-baked experimental ideas. This year we initiated the author reviewing mandate, and as a result we had a lot more reviewers and reviews. On average, each paper had close to 4 reviews. Every paper had at least 3 reviews, and there were 2 papers that got 6 reviews, both of which got in. Let's have a round of applause for all the reviewers and area chairs who facilitated this process. Okay, so we've been doing this for a few years now, and one thing that's great we can do is to look at the trends across time. So on the x-axis here are a bunch of topics that we ask authors to categorize. The y-axis is the proportion of papers that follow that topic, and the bar is for across years. So you can see from 2023 to 2025, the topics that had the most gains in popularity include foundation models and language models, dataset release, which has fluctuated a bit, and privacy and security, which is now a burgeoning field. Topics like explainability, HCI, and fairness stay constant, whereas the fields with the biggest decrease in popularity include semi-supervised learning, supervised learning, and active learning. One more thing to do is you can look at the word cloud of the titles of these papers that have been published. So in 2023, we had more classical words like segmentation, classification, learning, prediction, supervised, and graph. Whereas now it's all language models, right? LLM, language, multimodal, time is still up there, EHR is still up there, so maybe there's some hope. Okay, so we got a very exciting program prepared for you guys today and tomorrow. We got 5 speakers, 3 perspectives, 2 panels, and a fireside chat. And Matthew just gave an excellent tutorial as well.
And beyond the traditional conference events, we also have some non-traditional events such as roundtables. So this year we have 13 research roundtables spanning from clinician AI collaboration, health AI, and patient interaction. And this year we also have a special sponsored roundtable. So Google will be sponsoring one of the roundtables, which will be on open medically fine-tuned foundation models. And then beyond that, we also have 8 demos. So during the poster session, feel free to go check those out. These are real-world deployments looking at ECG interpretation, clinical trial matching, and radiology education. And in addition, tomorrow morning, we'll have some spotlight demos. And beyond those, we had 3 mentorship programs, which we ran before the start of this conference. The first is the authorship mentorship program, which has helped for people who have never submitted to ML4H or just in general, maybe new to the field. We connect them to mentors who can help them with both writing their paper as well as getting feedback on their projects. We have a reviewer mentorship program, which connects people who have sort of beginner starting out as becoming a reviewer and giving them sort of feedback on how to improve their reviewer quality. And then we also have a career mentorship program, which connects people to those who are interested in sort of different career trajectories and get questions and get answers related to those career trajectories. And overall, for the logistics, so we have a ML4H code of conduct, which is on our website. Just overall, what it summarizes is that this is a safe and inclusive space to everyone, and we should be open and respectful in all our exchange of ideas. And if you have any issues, feel free to email us. And for those who are presenting their poster or their demo, please feel free to set that up now until any time till 3 p.m. And finally, we want to thank all our organizers. ML4H would not have happened without all of you. So thank you to all our 21 organizers, varying from program, finance, logistics, OLLI, workflow, communications, outreach, and publications. So thank you all.
Introduce Paul Liang, who's an assistant professor at the MIT Media Lab and MIT EECS. He directs the Multisensory Intelligence Research Group, which advances the foundations of multisensory AI to enhance human experience. He is a recipient of the MIT Sony Career Development Chair Professorship, Forbes 30 Under 30 in Science, CMU School of Computer Science Distinguished Dissertation Award, the Siebel Scholars Award, the Weibel Presidential Fellowship, the Facebook PhD Fellowship, the Center for Machine Learning and Health Fellowship, and the Rising Stars in Data Science Award. Outside of research, he received the Alan J. Perlis Graduate Student Teaching Award for developing new courses on multimodal machine learning. And so please give a hand to our incredible keynote speaker.
All right. Good morning, everyone. Thank you so much for having me here. It's such a delight to know that multimodal is one of the biggest increases in popularity nowadays in machine learning for health. And hopefully my talk today can serve this field justice. So I'm going to give a talk on some of our recent work in building multimodal reasoning foundation models for health. And of course, it's no surprise that there is so much interest in building multimodal systems that can holistically understand a person's health and well-being. And in our group, Multisensory Intelligence, we like to think about the convergence of various dimensions of health. We have physical health, which of course is enabled by large amounts of medical data spanning medical text, imaging, sensing, and other forms of data modalities, especially those in the doctor's office. But most people go to the doctor's office, once or twice a year. We have much more longitudinal data that we can collect from a day-to-day basis about a person's emotional well-being, involving their mood and mental health, and about a person's social interactions, how well they are flourishing and interacting with other people in social settings. And my vision is that a lot of these things will converge together. We're going to see more and more systems that are able to deal with multimodal data, not just in physical health, but how physical, emotional, and social well-being all converge together to give us a bigger and better picture of a person's health and well-being. So as a step towards that, I want to highlight some of our group's recent work towards building these multimodal foundation models in clinical settings. And again, I want to highlight most of this work has been done by my student, David Dai. So definitely reach out to David, and he'll be at NeurIPS starting tomorrow if you have more questions about this work. So I'm going to cover 2 parts in this talk. And this naturally follows along the natural progression of how we see things progressing in machine learning, right? In part 1, we typically need to build large-scale multimodal data sets that allow us to realistically train models that represent this multimodal phenomenon. So we'll cover some of our work in building these large-scale multimodal data resources. And in the second part, we're going to cover some of our work in modeling. So how do you train really powerful foundation models that can integrate text, images, and time series, make predictions, and also reason about these predictions in a way that is interpretable and explainable to doctors. So firstly, on the side of building this large-scale resource. So recently at ICML this year, we released this resource called CLIMB. So CLIMB is a very large-scale multimodal and multitask clinical resource. It contains lots of data modalities. So over here, this figure shows that it includes 1D data modalities. So these are time series data, the like that you get from EEG, ECG, and so on. It includes 2D data. So these are static images. So this includes X-rays, for example, and pathology images, 2D imaging modalities. It includes 3D imaging modalities. So that will be 2D with a time dimension. So that includes CT scans, MRI, so some form of video. It includes graphical modalities. So David had done a lot of work in looking at brain networks and how these networks can be seen as graphs. And also multimodal data. Some data sets have multimodal data that is paired together for each patient. So CLIMB is a large-scale resource that really centralizes all of these data modalities together so they can start building foundation models that are able to learn more than the sum of its parts. So this CLIMB data set involves novel tasks like COVID and other pneumonia. It involves understudied modalities like ultrasound. This involves much less data than some other modalities. And also comes from underrepresented regions, not just all from North America, but we specifically went out of our way to source data from areas like South America and Vietnam. So here's a distribution of data collection sites. Of course, most of it is still centralized in North America, but we're also starting to see more representation from other areas of the world. And one thing I like to brag about CLIMB is that it essentially allows you to load all these data sets using just a simple command line argument. So just put in the name of a data set, the modalities you're looking for, and what data format you want it to be released, and it can very quickly return you data from those modalities in that data format. So everything has been standardized, everything's in a backend, but as a user interface, you can just load everything within a couple lines of Python code. And here are just some examples of data samples. And of course, everything is publicly available over here at this GitHub link. So CLIMB is really good because it allows us to centralize and load all these data sets individually and together. And of course, that allows us to train massively multimodal and multitask models. So envision these models to take in all of these data modalities like graphs, 1D sensing data, 2D imaging data, 3D imaging plus time, have specialized encoders for each of these modalities, and allow us to fuse these data features together to make more accurate predictions. And specifically in this first part, which is more about just studying the performance of existing models on CLIMB, we focus on several research questions. One research question is this idea of multitask learning. So if you have multiple modalities and multiple tasks together, can we train some multitask model that can work consistently across all of these tasks and especially show stronger performance on those tasks that are understudied? And here is a one-sentence summary, which is that we actually can. We show that multitask pre-training is actually very beneficial and is most beneficial on tasks that are new, modalities that are understudied, and data coming from regions that are underrepresented as compared to existing data sets. So over here, we've kind of shown the performance of AUC, increases in AUC when we start training multitask models on all of the data sets in CLIMB, right? Centralized from multiple data sets. And we find that the biggest improvements are cases where there's multiple categories, where the task is new, where the modalities are understudied, and in regions where they're typically underrepresented in today's data collection. So that's a very promising finding in my opinion. The second research question we studied was that when you start training these multitask models, hopefully they do well on the tasks themselves that were within the training set. But do they also transfer to new modalities and new tasks outside of those training data sets? And we care about this especially in the settings where either your modality or your tasks have very limited data. So we find promising performance is not perfect, and I think a lot of work needs to be done in this space, but we show very promising performance on few-shot learning. In other words, if you train a model on the first 5 data sets, how well can it transfer to this 6th data set using very limited data on this 6th data set? So we show several examples on transferring to BIOT, which is an EEG classification task, ECG JPA, which is an ECG task, and also on other ECG tasks. And we find that even using 1 or 8 or 32 examples, you can very quickly start approaching performance as measured by AUC as compared to full training on that 6th new data set. And this gives us promising approaches towards training models that can very quickly generalize in a few-shot learning to these new tasks. And of course, we also show that if you start pre-training on CLIMB, which is our centralized data set, you do better than pre-training on some other standard data sets, which have much more limited coverage in the modalities and tasks that they represent. The third and final research question that we studied in evaluating models on CLIMB, which is that can you use some of these pre-trained unimodal models trained on CLIMB to effectively tackle some of these multimodal tasks that involve fusing many modalities when they're present for the same patient. And over here we find mixed results, right? So over here what we're doing is essentially we're comparing the state-of-the-art encoders. So these are encoders that were pre-trained on other previously collected text or imaging or time series data, and how well they perform when fused on this MMIC4 dataset, which contains all of these modalities paired. And we're also comparing that to our new encoders that we train on CLIMB. So our new encoders for text, for imaging, and for time series modalities that we pre-train on CLIMB. And overall, we find that pre-training on CLIMB is very beneficial. It leads to very powerful new unimodal encoders, but it's still not clear what is the best way to fuse these modalities. Whether it's a late fusion or using MLP for fusion or using more sophisticated cross-attention methods. We find that cross-attention, which is much more sophisticated, does better on things like length of stay, but it doesn't really do better on some of these other tasks on in-hospital mortality rate. So it's still a big question, once you've trained these really powerful unimodal encoders, what's the best way to start fusing them? So that's about CLIMB. Everything here is publicly available. Check out the data resource and check out all of the public models that we've released on this data set. Now, everything I've talked about so far has been on perception. So how do you take in many modalities and make a prediction on a label? In this next project, we set out to advance the capabilities from just perceiving, so just classifying a certain label, to also able to perform reasoning. So how do you actually explain your predictions in natural language like a doctor would? How do you highlight important parts of the image that were most salient in making that prediction? And how do you also cite medical evidence so that you're better justified in making that prediction? So this is a follow-up work that was also led by David, and that will be presented at NeurIPS this year as an oral, which is to train a really large model on the collected data set in part 1, which is CLIMB, right? So this is a unified multimodal and multitask model that combines data modalities involving text, vision, and time series, is able to combine them and make predictions and also reason about those predictions. So in other words, give explanations, highlight parts of the image, and justify why that model came to that final prediction. So the inputs here are a sequence of text, 2D and 3D images, and time series. These are projected by individual encoders in those data modalities, and they could be possibly interleaved. So sometimes you might have data reports, You might then take some imaging. They might then be admitted to the ICU, in which you see multiple series of ICU sensors. So these data modalities can be interleaved in arbitrary ways, and the model can still handle that. And this goes into this model, which we call QOQ-MED, which takes in interleaved text, imaging, and time series. All of this is projected into a large language model, which can then output multiple things. It can output free text reasoning, so explaining and interpreting the data, looking at what it is, visual reasoning, so that would be bounding boxes highlighting salient parts of the image and also salient parts of the time series, and the final diagnosis, the clinical diagnosis that the model made using those data modalities. So specifically, how is this model trained? So it is trained first on the data that I showed in the first part. So the CLIMB dataset enables us to centralize lots of data from imaging, text, and time series. And what this model does is that in stage 1, the biggest bottleneck here is time series. So we have lots of good vision language models that is able to interpret text and also interpret images, right? We have lots of good vision language models. The biggest bottleneck is in time series. So the first step is to align time series data through some time series encoder into the input of these vision language models. So this model can then subsequently take in both vision, text, and time series through this projected encoder. So that's stage 1. Stage 2 is to train this model with mixtures of data from these different domains that we've seen in CLIMB. So this model, because it is a vision language model, so that has a vision encoder, and it also takes in text. The other bottleneck that I mentioned was to also enable this model to take in time series through some time series encoder that is projected into this model. And this model is then trained to predict the outputs, so what the diagnosis and also the reasoning and also visual highlights of the images and also the final clinical diagnosis. One thing that I want to highlight here is that this model is trained in a partial way. So we never see data sets that have time series and imaging and text, right? It's very rare to have all of those data modalities available for the same patient. Oftentimes you see only text, or sometimes text and images, and sometimes text and time series, right? So we see only these partial data modalities. So you can see the paper for more details, but we essentially developed a way in which you could train this model partially using only partial data sets, right? Depending on which data modalities are present for each data point. So of course, one big challenge here is that in almost all of these data sets, we have the final diagnosis, so length of stay, disease, mortality rate, but we never have these annotations of which salient regions were important for the diagnosis, and we don't ever have reasoning, so explanations of which data modalities and how they were used to make a prediction. And that's where the reasoning comes in, right? Of course, most of you have seen some of this latest exciting advances in large language model reasoning, where you might have a final annotation of the task. For example, this answer is correct, or this is the diagnosis, but you never see the intermediate chain of reasoning that led the model to make that decision. And reinforcement learning is a way of essentially incentivizing a model to come up with that intermediate chain of reasoning without observing it that best maximizes the likelihood of getting the final answer. So we take a similar approach. We also apply some of these reinforcement learning methods in training this model. But to do that, you have to define the rewards, right? What constitutes a really good final answer for the model, and what also constitutes this intermediate chain of reasoning that led to the final answer. So we investigated several forms of rewards in this paper. This is what we eventually settled with. The one important reward is, of course, accuracy, right? Whether the model got the final classification decision correct, right? So some decisions could be has tumor or does not have a tumor. Some of the decisions could be length of stay, in the period of days. So one important key reward is just whether it got that final prediction, classification accuracy correct. Another very important reward that we found was in the visual domain, the overlap, in this case measured by intersection over union, IOU, between the ground truth segmentation when it was available and the segmentation of the image that was inferred by our model, right? So that essentially rewards our model for segmenting parts of the image correctly and using that in its final diagnosis. So that is a visual reward. And finally, we also provide a length reward, which is again commonly used in training these large language models to incentivize reasoning, which is to reward up to 1 if the model's reasoning is at least 100 tokens, but not rewarding at more than 100 tokens, so that you can essentially incentivize the model to give pretty comprehensive and at a reasonable length explanations for why it came up to that decision. And this was also something that you could tune. These are hyperparameters. We found that a scale of 0.6 to the accuracy reward and 0.2 to the visual alignment reward and 0.2 to the length reward was what led to the best performance. One final thing that we also found to be really important was that if you start defining these rewards and training this model on all of the data sets on Climb, you had this issue of mismatch, right? You had some data sets in this large Climb centralized resource, which were much easier, with tasks that were easier, questions that were easier, and also data modalities that were more frequent, and this would dominate training. And the model would just converge and learn on these simpler tasks without really learning and challenging itself on the more difficult tasks. So one thing that we found was that it was really helpful to essentially weight, either upweight the tasks that were more difficult or downweight the tasks that were more easy or more frequent so that we got better training across the diversity of these very heterogeneous and very different tasks. So that's what we did, right? We found that tasks like X-ray imaging and diagnosing whether there was a tumor from X-rays were relatively easier. Problem of object detection, and there was lots of data available in Climb, so you should downscale this. And other tasks, in this case on ultrasound, and also the fact that it was a video, so you have much less data, and the task was also much more difficult. In analyzing this video, you should upscale it so that you can actually learn much more frequently or with higher rewards if you solve this task correctly. Specific details are in the paper, but essentially how we do this in some unsupervised way was to essentially look at every training step, the distribution of rewards that the model was learning across different modalities and tasks when it was doing this centralized training, right? And by looking at this distribution of rewards, you could then start clustering it. You found a certain cluster of tasks with higher rewards and a certain cluster of tasks with lower rewards, right? And naturally, this was a proxy for how you could determine whether a task was more easy with higher rewards or more difficult with lower rewards. And then we could then upweight or modify the reward function to account for this imbalance in difficulty. So overall, all of these tricks, the large centralized data set that we saw in Climb, this modeling architecture that combines text and imaging and time series, and the modification of these rewards so that we can incentivize the model to train in a more balanced way across the heterogeneous data sets and tasks, led to this QOQ-MED multimodal reasoning model. So we released this model in both 7 billion and 32 billion parameter configurations, which depends on the underlying base language model that you start with. And in our knowledge, it is the first medical reasoning model that is able to pretty effectively reason across these 3 data modalities that are very central to medical problems, 2D and 3D images, videos, time series, and text. Over here, we show again a plot of performance where this is accuracy difference or accuracy improvements. And we again see that it is those novel tasks, understudied modalities, and underrepresented regions that show the biggest boost in performance using this large-scale model. And this plot shows that if you start comparing this model to both open and closed source models, this involves things like MED-R1, LavaMed, which is open source, and also your OpenAI models like 4o Mini and GPT-4o, you see pretty substantial improvements in performance, especially on the ECG domain, right? ECG, these models can't even take in ECG data, so you see lots of improvements. But also cases like MRI, pathology, CT scans, and mammography, we see pretty large improvements using this unified model. One key ablation we compared was this idea of DRPO. We call this domain policy optimization. This is better than group relative policy optimization, which is a classic way of doing RL for LLMs without really accounting for the fact that different data from different domains and modalities and tasks can have very different distributions of rewards, right? So this idea of clustering and upweighting tasks which have lower rewards and downweighting tasks which have already gotten high rewards is especially useful overall in terms of performance, right? We see overall much better improvements in both accuracy and F1. Finally, to conclude the talk, I want to show some examples of this model. Of course, one method of evaluating a model is just through overall accuracy. And we've seen multiple evaluations and comparisons on accuracy. We also took an extra step to evaluate whether the reasoning steps that these models outputted were accurate. So what we did here was that we collaborated with clinicians. These are clinicians from Harvard Medical School and Johns Hopkins Medical School. And we asked these clinicians to annotate for each example, given the image and time series and the reasoning and the final answer output by the model, whether these reasoning traces were really high relevant to your diagnosis, low relevance to diagnosis, or not relevant at all, or perhaps even incorrect in misguiding the diagnosis. So you find that overall, 45.3% of the reasoning is rated as highly relevant by these clinicians on the sample that we showed them. And of 100% of the sample, so for every data point that this model made inference on, there was at least one sentence that was highly relevant to his reasoning. Of course, there were also other sentences that may be lower relevant or not relevant to his reasoning. So over here, for example, this is a more clear case. This is the MRI, and the question is, is there a tumor? The ground truth is that there is a tumor, and the model is that the model that we trained also gets the correct answer, and also shows high relevance of diagnosis, that it's a round, work circumscribed lesion, and tumors often characterized as having a distinct, often irregular boundary, and it shows that a tumor is clearly distinct from the surrounding brain tissue. So that's an example of a highly relevant reasoning trace that these clinicians annotated. So these are tasks where it involves both imaging and time series data, and again, it shows highly relevant reasoning. In this case, there's the imaging and time series. The goal is to predict the length of a stay. The model guesses correct, that the patient will probably stay in the hospital in the ICU for 0 to 4 days. And the highly relevant diagnosis was that these are X-ray images showing no obvious acute pathology in the lungs, which could be indicative of a stable condition. And the ECG also appears to be unremarkable, that there's no immediate signs of acute heart failure or other critical conditions on the ECG. Here's an example of the model reasoning over imaging and time series when there is actually a severe issue with the patient, that they're probably going to stay in the ICU for more than 12 days. So again, the model guesses correct. And what the model is able to output as reasoning is that the patient has been on medical ventilation for 96 hours, which is a pretty long duration. The ECG and other lab results do not show any critical immediate issues, but the patient's hematocrit and hemoglobin levels are low, which could be a sign of anemia or other underlying conditions that require treatment. So that's an example of the model reasoning correctly over both the imaging modality and also the sensing modality. We also find that a model is able to reason very well over textures, right? This is a classic example of challenges which only appear in vision, but is very hard to express in text, right? So in this case, the model predicts basal cell carcinoma correctly and identifies that it's not a dark mole, that is slightly raised, pinkish, and has a slightly elevated area. And it does all of this just by looking at the 2D image. And the lesions have a rough, scaly surface, which is more consistent with the texture in this image. But of course, not all examples were really good. There were still examples where the model starts hallucinating or making up information. So over here, given this X-ray, the image, the ground truth is that there were some support devices in the lung, but the model is not able to identify this, including making up diagnosis that was not really relevant to the right answer. And of course, all of the reasoning traces of the models that we've trained are publicly available. And I'm almost out of time, so I'd like to conclude by really summarizing everything that I've said here. So I personally think that multimodal is the next frontier for training AI for health systems. And in this work, we've contributed 2 key ideas, right? Firstly, how do you centralize these large-scale multimodal clinical resources? We've shown that we can do it through CLIMB, which allows one click, several lines of code you can release and train any model in any subset of data sets within Climb. And in part 2, we showed how you could train these large-scale models on the union of all of these data sets that are highly multimodal and highly multitask in nature to train models that are very generalizable and can transfer to different downstream tasks. GitHub link is here. We provide not just the training pipelines for this model, but also the RL training pipelines for a large set of models that is able to reason over imaging, text. We have some more work in audio and visual learning done in our group. And again, this is a work in progress, so feel free to report any bugs to GitHub. And finally, I want to end with several key future directions. Right? We've shown that there's big promise in using RL to train models for medical reasoning. Of course, it's not perfect. We see much more work in better incentivizing robust and faithful reasoning. We've discussed some of our work in multimodal fusion, but it's still being done with pretty simple projection layers, where you have vision language models, vision is projected into LLMs and time series. We also project it into large language models. How can you build better fusion methods that can actually better combine discrete and continuous signals? It's going to be a big challenge in multimodal AI for health. A lot of the models that we've proposed are also at the 7B and 32 billion scale, which gives you really good performance and really good reasoning, but they're not efficient for real-time usage. So how do you better compress and apply these models in real time? And of course, we don't see these models as working autonomously. They have to work in the loop with doctors still providing the agency and the final diagnosis. So a lot of the work in our group is also thinking about how do you better enable this form of human-AI collaboration and what technical challenges in AI have to be accomplished for much more seamless collaboration. All right, so contact myself, and of course David was the student who led all of this work. If you have follow-up questions, and also happy to take any questions right now. Thanks, everyone.
I have 2 questions. Did you include healthy patients in this data set? And the other one is, did you try like differential diagnosis task? Like say, for example, pneumonia versus a lung tumor?
Yes, so we did include healthy patients. So over here was an example of a healthy patient, that the ground truth is that only stays 0 to 4 days in a hospital. So we did include that. And we tried to keep the data set as balanced as possible with respect to healthy versus unhealthy, but also seeing a coverage over diseases. For differential diagnosis, very good question. So David, the star student who's leading all of this work, is currently working on it. And again, we see new potentials for applying modifications of RL methods, right? RL that is based on counterfactual reasoning. So given this person's age, if they were older, this might be a different diagnosis. If they also show something else in this other sensor reading, they should have some other diagnosis. So we see a very complementary way of including differential diagnosis with these RL methods. But of course, the RL method itself has to be modified differently.
Thanks for the great talk. So in many of these RL-VR papers, there's some kind of external reasoning data that comes in as SFT before the reinforcement learning happens, either from experts or by using some kind of like heuristics, like adding the weight token, like these kinds of things. And this has been shown to be really important in a lot of settings for getting more performance out of RL-VR. Can you say a bit more about, did you use that kind of data? Are you thinking about using it? How do you see that problem?
Yeah, great question. So a lot of the work that I'm showing here builds on top of several pre-trained vision language models, after which we adapt the time series. But some of these pre-trained vision language models include MedGemma, Qwen3VL, and so on. So MedGemma has, of course, been trained using SFT on some of these data sets with these reasoning traces that you talk about. I'm pretty sure for a lot of these vision language models, they've also been pre-trained using SFT on data sets such as medical textbooks on the internet that contains ground truth reasoning traces. And of course, we attribute a big part of why we can get really good performance to a lot of these base models.
Got it. Thanks.
I think you kind of answered one question, but just wanted to confirm, like the way you project from the different modalities, is it based on pre-trained models that you don't adapt further, or you also train the weights of those models, those blocks that project the different modalities into the LLM layer?
Yeah, great question. So we keep the text frozen, but so I'll show you here. So we keep the text frozen, the text model frozen, but we do fine-tune the vision encoders and time series encoders. And again, no surprise here, which is that we have really powerful text models. These vision models are usually trained on natural images. So the vision model itself, I think there's a lot of work to be done. But in this case, we continue fine-tuning it. One thing that was a little bit counterintuitive was that whether you should take all of these imaging modalities from X-ray, fundus, pathology, CT scans, and use the same vision encoder or use separate vision encoders, right? So in this case, we decided to use the same vision encoder, just so we can share information. But I think it also makes sense to have separate vision encoders that look at different resolutions and different time scales. So time series encoders too, there isn't really a de facto best time series encoder, much less one trained on medical data. So we also continue fine-tuning them.
Makes sense. A related question is when you have data that is aligned potentially, like there's ECG, there's imaging, and there's textual data, there's also a longitudinal aspect of that data per patient. Do you also try to, I couldn't get that from this view, whether you're also trying to model, here are multiple data points for a single patient, where at each data point you have different modalities in play.
Yes, absolutely. So in this case, we do have this method of interleaving this data. So you see text at a certain time step, and the time step is encoded using the positional embeddings, and maybe afterwards you see both imaging and time series together, and you then use the same position embedding that was after the text. So you can essentially interleave any combination of text, imaging, and time series through the position embeddings so that the model can take that in.
Thank you.
So thank you so much, Paul. Let's give Paul a great round of applause. Next up, we have our first perspective speaker, Dr. Gabriel Brat. Dr. Brat is a trauma surgeon, surgical intensivist, and assistant professor of surgery at the Beth Israel Deaconess Medical Center. He's also an assistant professor in biomedical informatics at Harvard Medical School. As the director of the Surgical Informatics Lab, Dr. Brat has a broad research focus on informatics tools to improve surgical outcomes. His interests include decision support to optimize surgical opioid prescribing, computer vision of open surgical videos for performance analysis and feedback, and leveraging large-scale database and machine learning models to inform surgical planning and improve outcomes. As the co-founder of a recently acquired machine learning and computer vision company, he now teaches health IT innovation courses at the medical school and mentors several digital health startups. Dr. Brat has an undergrad degree in bioengineering and a graduate degree in public health and biostatistics from the London School of Hygiene and Tropical Medicine. He completed his medical training at Stanford and his surgical residency at Johns Hopkins. So with that, let's welcome Dr. Brat. Yep.
So there are two things that are not looking good for this talk. The first is that I'm between you and food, so that's a big problem. And the second is when the statistics for the talk were put up, this talk may feel very 2022 because it's about human-computer interaction and things of those sorts. Thank you for the chance to speak today. My name is Gabriel Brat. As mentioned, I'm a surgeon at BI. A lot of this work was written up with Jason Marwaha, who's one of my fellows and is now a surgeon at University of Michigan. I have no important disclosures and nothing that I'll be talking about is related specifically to the work that I'm going to describe. I'm going to do something that is actually a little bit different than what I normally do. To be perfectly honest, I've never given a talk like this. So this talk isn't really about my work. It's just about some thoughts that I have and some things that I see as fundamental to this entire conversation. And so I'm going to talk a little bit about some examples that address this issue of this predictive dissonance question. I'm going to give you a little bit of a definition as to what it looks like and what the neuroscience literature has really talked about this. And then I'm going to talk about some of the solutions that exist. But I'm going to be perfectly honest and say that I don't have a perfect answer to how to address this concern. So as many people have talked about, Garry Kasparov in the late 90s played against Deep Blue over the course of 3 games. He lost. He went into a very deep depression, spent months trying to beat the machine. and ultimately realized that he actually didn't need to beat the machine. He could actually start working with it to build a more creative type of chess. He wrote a book in 2018 that specifically talks about this and about the creativity that he feels can come out of this. But one of the things that was really fascinating about this is he talks about this idea, which feeds into one of my topic, which is this idea of that a weak human, he calls it Kasparov's law, is that a weak human plus a machine plus a better process can outperform a strong human plus a machine with an inferior process. Now, if you focus on this point for a second, you have to ask yourself the question, people have asked this in many different domains, why, for example, would a internal medicine physician who gets an assistance from an AI to do a radiology task potentially outperform a radiology expert who's working with the same AI and the process of working with that tool is inferior? Because our processes, especially in healthcare, are pretty much the same, whether you're an expert or you're a novice, really this just means that there are scenarios where the weak human, and what weak in this sense is in terms of expertise, plus an AI assistant is actually better than a strong human or a strong expert with that same assistant. Now, you have to ask yourself the question, that is actually counterintuitive, and yet there have been many examples of this throughout the literature that have suggested that experts working with these tools sometimes perform worse than non-experts working with the same tools. So I'm going to give you some examples in the literature. I'm going to use an example from radiology, an example from medicine, an example from surgery that basically speak to this point. So this was a paper that was published a few years ago as part of in the economics literature. And in this project, what they did was they had radiologists organize themselves and read through radiographs in a bunch of different ways. And then they evaluated the performance of the radiologist with and without the access to an AI tool. And what they did, which was pretty clever, is they then had the data, which is the black dot, and then they created a bunch of simulations in terms of how the human may have actually interacted with the AI algorithm to see which version of their performance best described what they actually saw in the data. And their overall finding, among others, was that the radiologist exhibited automation neglect. And what automation neglect is the exact opposite of automation bias. It's the idea that when the experts interacted with the AI, they actually interacted with it as an adversary. In other words, they acted relative to it, not with it. And then even more strangely, which when you think about it is quite a strange thing, is they looked at their prediction as independent from what the AI was predicting, even though clearly they were not independent because they were based on the same data and using similar data sets. And so this idea of this automation neglect, right? Why would a radiologist work in contrast to an AI as opposed to in collaboration with it? Another example, so this is a project where they were looking at pre-surgical risk prediction. It's already been shown that that algorithms in general outperform humans as it relates to post-surgical risk prediction in that pre-surgical period. In this study, what they did is they gave physicians an initial risk assessment. They told them what the risk would be based on the data at their hospital system. And they allowed them to interact with a tool that gave them this information in a very explainable fashion. And then, after having the data, they then asked them to reevaluate, reassess what their prediction was. And it turns out that for the most part, they didn't change their predictions at all. In a couple of places, when it came to predicting the likelihood of ICU care or AKI, they did make some substantial differences. But for a lot of other things that were actually very relevant, like mortality, sepsis, or cardiovascular complications, the physicians, despite having an AI tool accessible to them at the point of care that was explainable and based on their healthcare system's data, did not change their perspective, okay? So the question is why? right? If everybody knows that the tool works better than they do, why would they not change their opinion? And when you look at it, they actually did a follow-up thing where they actually surveyed the physicians. They said, would you use this tool? This isn't divided by the people who changed their mind or not, but overall, and this is a small group of feedback because they had only about 20 physicians, and these are from the free text responses. They basically have a variety of perspectives that say, you know what, yeah, this was pretty good, but a lot of people said it wasn't that great, not really that useful, okay? So I'll give a final example, all right? So this is a paper that got a ton of attention. This is the JAMA Network Open paper by Chen and Rodman, where they did a clinical trial simulation of physicians with and without access to LLMs to help them actually answer simulated clinical scenarios. Okay, and what it showed, the part that got so much attention was that in general, the LLM working on itself actually outperformed the clinicians. That was the finding, that was the headline that got into the New York Times and everything else. But there was another piece of information that to me was actually relevant to this point, which was that if you look, access to the LLM essentially made no difference, okay? And so you would expect that if there was data that supported that these tools were performant, and now you have someone who has access to these tools, and by the way, these residents already use these tools all the time for lots of other things, why would an LLM that is being explicitly used in simulation to help assist them to make better decisions and better diagnoses, why would it not change their behavior? Why? So to me, the answer is really clear. And it comes down to this idea that the first and most obvious point is that when we look at the data, there's only one place where predictive algorithms, like the one that we're describing, have value. They don't really have value when the AI and the human agree. So if the AI tells me something I already know, not really that valuable, okay? And if the AI and the human are both wrong, in other words, the AI is telling me something I don't know, and the AI doesn't know it either, that has no real value either. And so the only really valuable place for these tools is when the human is wrong and the tool is right. This is literally, this discordant space is the most important part and is the entire marginal value of adding these tools into the workflow, is that it's going to help you make a decision that would be different than what you'd make at your baseline. So that's the first premise, okay? So it only is valuable, or it's primarily valuable in this scenario. And I am definitely gonna go over time, because if that's 5 minutes, then I'm definitely gonna go over time. But at the same time, we have this thing called predictive coding, and there's been a ton of literature in the neuroscience literature around this, where we continuously build mental models, and we expect, and we build those mental models around what we expect will happen. And when the world relates to what our mental models were, we get a dopamine hit, okay? And it's validated. This is why people talk about this idea of predictive coding. Why is it that when you're driving in the car and you're singing and a song comes on that you recognize, why is that a pleasant feeling? Like, why do you enjoy that? The reason why you enjoy it is because that song that you recognize is coming to you in a way that really is present and is significantly familiar. And that familiarity is a dopamine hit, and when it's not familiar, it's not. This is an example from my daughter. This is my 4-year-old last week. She was super excited because she needed to recharge her iPad, and she got really sad when after recharging her iPad, the iPad wouldn't turn on. As you can see there, she knew that if you took the lightning adapter and connected it to the iPad that it should charge, but she didn't know, because she's only 4 years old and she's learning, that you need to actually connect it to the power cable in order for it to actually recharge the iPad. And so this is that exact point in a really kind of silly way, but is the point that she had a really clear mental model of what the world was going to be like, and it was possibly true, but it just wasn't completely true. And so what is this predictive dissonance? The dissonance is simply that conflict arises when the model outperforms the user. And we don't like to be wrong. And because we don't like to be wrong, we will often reject unwelcome recommendations. Okay, so there are lots of caveats to this. There are many additional reasons why we do what we do. And if we're not invested in a decision, like it's not a high-risk decision, then we don't necessarily invest our own sense of self or value in that decision. And so those are the kinds of decisions that are kind of the sweet spot for these tools. And obviously, if you have a really short feedback loop where the AI is giving feedback and you have that feedback back to the user, that changes everything. And to be clear, a lot of the studies don't have that, and this is probably one of the reasons why they fail. So I'm just going to talk about a couple of solutions. Okay, so the first is that we need to, one of the ways to look at this is we have to personalize this explainable AI. People call this in the HCI literature, this would be transparency of some kind, or, these things are kind of overlapping. That potentially one way to address this is to develop essentially different type of triage protocols. And in some of the papers actually that were written that I mentioned, they actually suggested versions of this. And the third is to change the psychology of the users. If you change the psychology, then you'll be more open to getting a conflicting response to your presentation. So here's this idea of personalized explainability. This was actually, I think, a pretty interesting paper. This was just published actually in Nature Digital Medicine. What this was is this group of researchers, so I'm a surgeon and this is the space that I'm really interested in, they published 2 papers of the last 4 years. And in the first paper, they had a bunch of people do annotation of certain parts of the anatomy from a surgical video of the anatomy of the inner ear. And they showed that in users who were less experienced, they performed actually better with the assistance of the AI than people who were more experienced in this. And then in the second paper, they did this essentially the same task, but they did it with neurosurgery, and they showed that the experts did better than the people who were less trained. And they were like, how is that possible? We literally wrote 2 papers that are essentially the same paper, but they have 2 different outcomes. How is it that that happened? And they posit that the likelihood is because of the way that they presented the data to the physicians. And that in one scenario, they presented the data in a way that made it much easier for people who were less experienced to feel comfortable using the data. And in the other way, because of the complexity of the information, it actually made it much more easy for an experienced person to use this data to actually change their beliefs. And so what this suggests is, again, there is a sense of conflict, and unless you actively find a way to reduce that conflict, you will often get people who will essentially refuse the recommendation, because at the end of the day, it is a clinician who needs to make this decision. Okay. A second option, which I think is really interesting, is this idea of an AI delegator, which is, essentially there are lots of scenarios where you actually don't need a human to make this decision. And if the idea is that in those places, the human may actually make mistakes and reduce the performance of the overall system by actually making that decision, then maybe we can have a scenario where you're not having an investment in the process because the human isn't actually having to conflict with the AI in any given way at all. One example of this that we're doing and working with some collaborators at MIT is this idea of algorithmic equivalence, where overall the algorithms tend to do better than the radiologist, but there are clearly scenarios where the radiologist, if you have access to certain types of data, actually outperform the models significantly. And so the question is, could we essentially create a delegation system where the humans are only seeing the questions where they have the most value and where they're likely to conflict with the AI in a way that is actually positive for the human and not positive for the AI? The final possibility is obviously to change the psychology. And I thought this was pretty impressive that ChatGPT 5.1 could generate this last night. Essentially, this is now the man, instead of singing in his car, he has an instruction manual that he is addressing. And that's exactly the point. If you have a scenario now where people are primed appropriately to work with this data in a way that doesn't make them essentially conflict, but it allows them to understand that there isn't a belief destruction that is occurring, then maybe there's a scenario where people will actually be able to work more effectively with these tools. But obviously, there are questions of education, there are questions of the way in which you actually train people to be accepting this type of data. So in conclusion, this is what I do. And in a scenario like this, for there to be an AI to provide an assistance, it has to be incredibly robust, and it has to be generated in a way that allows me to be accepting of these technologies, because every move that occurs in that operating room, I am extremely invested in that. And no matter how good the AI is going to be, if I am not primed in a way to be able to accept that technology, there is no way that I'm going to do something that could cause injury to a patient or to the surgical procedure. And so in order to build models that actually work for the types of scenarios that we're describing, we need to address the simple fact that if we're building tools that are contradicting what humans already believe, and they have a strong belief in those things, then we need to address that in a way that meaningfully allows them to make decisions that make them feel comfortable while at the same time doing the right thing. So thank you so much for giving me the opportunity to give this perspective. And I'm happy, I don't know if we have any questions, but feel free to reach out with any questions or if you want to discuss this further. Thank you.
Yeah, I think you summarized that very well, the interaction between AI and human. And, obviously AI, can you hear me okay? Yeah. Yeah, AI can make things worse when you don't accept the right solution. But as AI gets better and better, it may also make things worse when you do accept wrong decisions. And so I think another counterintuitive, it's another paper that I think you didn't cite, but you cited the main ones. It's also been found that the more junior staff do not benefit more than the senior staff. There's no sign, and they actually need more help. So that's another counterintuitive. So my question to you is, how do we alter the training of physicians, which is in Go's paper, for example, that was his main conclusion. We have to train people to use AI. How do we alter training so that you don't get this positive dopamine hit from confirmation? You start to get it from help.
Yeah, so I'll say that I don't have a perfect answer. What I think is, in some bizarre way, this is counterintuitive to everything that people have trained us to believe. But in some ways, the most effective way to actually allow this to happen is for us to invest ourselves less in the decisions that we make. And so if you look at some of the most effective places where AI has actually assisted physicians, or machine learning models and prediction have assisted physicians, is where people don't invest their own sense of self in the decisions that they're making, which is actually obviously a really difficult thing to do in an effective way in medicine without actually causing all these secondary effects that are very negative. And so if you actually so the alternative to that, and this is, I think, a really important point, is if you have a colleague, the only model that is effective to the point that you're saying is if I have a colleague who is with me, and my colleague, my partner, the person who I respect, comes to me and says, here's a different perspective on how you might do it, okay? You are wrong in the way that you're thinking about this. I might accept that perspective because I have respect for that colleague and for their experience. And so obviously some version of this is what needs to happen. We have to essentially respect these tools as essentially effective colleagues in this process. Because it's either we have to reduce our own sense of involvement in the decisions that we make, or we have to increase the faith and the valuation of the models and the tools that we're using. Those are essentially the only two ways that I see that this can be effective.
My name is Sarah Jabor. I'm a PhD student at the University of Michigan. If you're wondering about that Ohio State game, all I can say is it was snowing the entire time and there was limited visibility. All right, so I'm excited to announce our next keynote speaker. Professor Serena Yeung-Levy is an assistant professor of biomedical data science and, by courtesy, of computer science and electrical engineering at Stanford University. Her group develops deep learning methods, particularly focused on visual and multimodal modeling for analyzing visual biomedical data across scales, ranging from subcellular to tissue and whole human level, and including 3D and video in addition to image data. Serena serves as Associate Director of Data Science for the Stanford Center for Artificial Intelligence in Medicine and Imaging, and is affiliated with the Stanford Clinical Excellence Research Center, and is a Chan Zuckerberg BioHub San Francisco investigator. Prior to joining the Stanford faculty in 2019, Serena was a Technology for Equitable and Accessible Medicine postdoctoral fellow at Harvard University. She received her PhD from Stanford University and spent time at Facebook AI Research and Google Cloud AI. So please, let's give a round of applause and welcome Serena.
Okay, thank you very much, Sarah, for the introduction. I just want to make sure whether I can control this. Okay, great. Okay, so today I'm going to talk about some of our lab's ongoing work on multimodal generative models for science. And in particular, the modality that we'll be focusing on is imaging, as well as imaging plus X, in this case, imaging and language for the most part. So just to start with a little bit of context, there are really many different types of imaging techniques producing all different kinds of imaging data ranging across scales. Here we can see from tissues, cells, organelles, molecules, and of course I haven't even mentioned organs and human body systems and others. And all of this data is really heterogeneous and scattered across many different sources and formats. And so you can see here different imaging repositories and databases. We also have scientific papers and literature. And so across all of these, there is a challenge of both putting together this data and then being able to link and connect and reason over them. So one of the major goals of my group's research is to try to harness all of this vast heterogeneous sources of data together to reason jointly over them and to extract insight from these. And in particular, today what I'll be focusing on is trying to extract insights that are particularly relevant for scientific reasoning and personalized therapeutics and drug discovery. And so here's a couple of examples. We'll be talking about vision language models, in this case, visual question answering models that can help aid in scientific investigation, trying to understand disease mechanisms, learning from many different sources of multimodal visual and language data that's out there. And then we'll also briefly talk about virtual cell models, which is a different type of generative model, now trying to produce images that can visually simulate the effect of drugs. Okay, so we'll start with looking at VQA models. And so, if we're, just make sure I have the time here. So for us to be able to develop these VQA models that try and advance multimodal scientific reasoning as much as possible, first we have to be able to do a good job of measuring these capabilities. And so here looking at capabilities that can perform really researcher level scientific research and inquiry. And so being able to support basic science researchers in their day-to-day research workflows. So I'll talk about this work, MicroVQA, which is a multimodal reasoning benchmark for microscopy-based scientific research. This is work that is led by my lab members, James Burgess, Jeff Nerschel, and Laura Bravo. James and Laura are actually on the job market this year, and Jeff is now an assistant professor at University of Wisconsin-Madison. And so here our goal was to say, how can we really assess these types of advanced reasoning capabilities where a lot of the information isn't in typical exam-based benchmarks and data sets. What we really want is this brain dump of what biologist researchers are thinking and the types of questions that they would like assistance from AI models to be able to help with. And so we really came at it from this type of sort of human biologist research-centered perspective, where we started off with just having discussions with a group of biologists and trying to broadly understand use cases, brainstorm them, and thinking in particular about use cases that are both importantly, provide value, that are of the type of more advanced reasoning of acting like some type of a smart colleague. And because our focus here is on multimodal, using images and involving some reasoning here. And one of the reasons we have, have this theme of multimodal and imaging throughout is because I think there's a lot of untapped potential still in these types of imaging data that are more challenging to make sense of, where there's still a lot of need for advancements, whether in data or on algorithms and models, compared to, let's say, just text-based and language reasoning. And so this is our focus here. And from this, we came up with a taxonomy that spans these categories of expert visual understanding, hypothesis generation, and experimental proposal. So all of these parts of the workflow. You can see here, drilling down a little bit further with expert visual understanding, looking at, one thing we found was of a lot of interest was how do you compare image sets? So how is one image different from another? What's, abnormal about something? So that's the second case, identifying what's abnormal, why might it be abnormal? So the second category here, hypothesis generation, looking at what are potential causal mechanisms or functional implications. And then finally, experimental proposal, suggesting new experiments. And one thing we also found was, interestingly, of a lot of value was how might we actually adjust our techniques to image this potential phenomenon better, or what type of experiment might I perform next in this regard. So from here we got essentially then crowdsource this across a group of biologist experts across many different domains and expertise, and in total got over 1,000 VQA questions that were curated by these researchers. And so here we're, and the goal was to get this kind of brain dump of scientific reasoning questions. You can see here that total over 1,000 images, some multi-image questions. Each one did take quite a while for them to write them. They were oftentimes came from their own research and or their own way of thinking about problems. And so this is now this benchmark data set that we can work with. We took a very careful process of how to turn expert-generated content into multiple choice questions, which are easy to work with, useful type of benchmark. And so you can see that what we allowed the experts to do was to provide information in these sorts of long, unstructured ways, in particular because it is difficult to calibrate across different scientists. We also have many factors involved in converting things into multiple choice questions, so we didn't want to start with that from the get-go. And so given all of these types of questions, then we had this process of taking a raw database of questions, then first taking a step of turning them into multiple choice questions. This was using a combination of prompt optimization and trying to use and incorporate some medical exam best practices to format them appropriately in terms of the types of negative answers that are also provided. But given this, it's still oftentimes not sufficient. And in particular, you can imagine with multimodal question answering, you might also have different types of shortcuts. So language shortcuts, you might have appearance cues in the question, you might have silly distractors or other types of bias. And so we used this agent-based refinement pipeline where we would have basically models that would reflect on the question being generated, try and identify problems with it, try and rewrite the questions, and use that to obtain the final benchmark data set. Here you can just see a transformation of going through raw question and answer to then turning it into multiple choice question, but we still have some problems in terms of distractors and things being vague, and then finally getting the full final question at the end. Okay, so given this benchmark, we evaluated in a semi-automated fashion these types of Bloom's taxonomy levels of reasoning here, and basically what this benchmark data set provides is significantly more cognitively challenging questions with these higher levels of analysis and evaluation compared to existing benchmarks, which is representative of its research level focus. And so looking at current state-of-the-art models, this is from the time of publication. It's still quite difficult for many state-of-the-art models, and so I think there's a lot of room to improve on and work on these types of problems. As we've continued to evaluate more recent models, we do see that improved reasoning capabilities with some of these reasoning models do lead to more progress on here. So it's kind of correlating with what we would hope and expect, but there's certainly a lot of continued room to go. Okay, and so if you're interested, here's a link. Everything is publicly available, and we certainly encourage people to work with and try out your models at this link here. All right, so this was one of our first steps in trying to measure, or to have the capabilities to measure how well do current models perform on these types of scientific reasoning capabilities. Now, as we try and tackle this problem, one of the first questions that comes up is, do we have enough data, and where can we access the types of data that we need for improving these types of multimodal scientific reasoning capabilities? And so this was something that we tackled in this work, Biomedica, which was led by PhD students Alejandro Lozano, Minwoo Sun, and James Burgess. I saw Min here earlier just now. And so this work was really centered around trying to say, can we find a large resource of data that can help support these types of models, and importantly, make this open access and available and kind of AI ready to support training and development based on this. So this work was based on the premise of scientific articles being, as we all know, a very rich source of multimodal data. We have both text information, we have scientific images and diagrams, captions for the images, many inline references as well, right? So we have a lot of weakly associated images and text. And PubMed Central, open access, is in particular a very good resource of 6 million open access scientific articles. And so there's been various projects that over time have worked with this data set, sometimes in part, sometimes in full. And so here, as I mentioned earlier, we worked on making this data set and really the data here openly accessible and as useful as possible for AI training. And so you can see just some examples of the type of broad representation across different data types here that is in these articles. And so what we did was really go through this pipeline of first trying to extract all of the information from here, extracting these articles, importantly also associating metadata and both full text, captions, as much as we could get just from scraping all of this data. Then we also annotated this. So this is in a semi-automated annotation fashion, trying to label and attach tags to this data set so that they can be filtered and used in different ways. And then finally, making it very easily accessible versus a streaming interface available through Hugging Face. So as you can see here, these are some of those different types of categories that you can see at a glance from this data set. And what we did was basically extract Dino V2 features from across all of the images here, and then perform some semi-automated clustering and labeling of clusters, and use this to be able to propagate some loose tags across all of this at both more global and local taxonomies. And so given this, you can filter and use it in different ways. We've done some preliminary work on trying to train models based on different subsets of this data. Looking at across just models, first clip models trained on all of Biomedica, we're able to see that training on these resources is able to improve over previous clip-based models. We also have trained a question answering autoregressive models. And so here you can just see an example of that that we are also have made available. And then finally, we have demonstrated some examples of using Biomedica Index that was built from this data resource, using it for RAG systems, for example, in this case for biomedical guidelines question answering, and being able to add value in that sort of a way. And so all of these are publicly available resources. So you can see here the information about data access and the link to how to access the data, how to use it. And so we hope that this will be a useful resource that people can work with in various ways for their own mechanisms. Okay, so this I talked about data, and then just briefly as well, we are also working on different types of methods for improving training models using this. So I won't talk about this really today, but this is a work that is will be coming out relatively soon from our group, looking at building environments and performing RLVR-based training for question answering over scientific papers. Okay, so I've shown some of this series of works on looking at how do we compile information from across scientific literature resources to be able to perform question answering. And our goals with this are broad, both in terms of kind of our main use case here, which is towards understanding disease mechanisms from the micro-VQA benchmark. I'll talk later about some other generative models as well. But we think it's also very broadly useful across, of course, the whole spectrum of different types of biomedical imaging data. I wanted to just highlight one work that is a little bit of a, it's not this kind of microscopy data that I was mentioning, but I thought it might be of interest to some people in this room, so I wanted to mention it on trying to evaluate large vision language models for surgical artificial intelligence. This is work that was led by my former postdoc Anita Rao, who's now at Intuitive. And I think I often personally really enjoy seeing really how do current state-of-the-art VLMs work across different domains and tasks. What capabilities do we have out of the box, whether it's zero shot, few shot, how much more do we need to go? And so this is something that we tried to do here for in the surgical AI domain, and to really look at this diverse group of surgical AI tasks and applications. So here we took some of the major kind of recognized use cases of surgical AI across for training, for op notes generation, for workflow optimization, as well as for augmentation, kind of visual field augmentation. And across these then, broke these down into atomic tasks from recognizing tools, hands anatomy, phases, actions, gestures, or more higher level understanding of risk and safety, skills and errors, and so on. And so we performed this evaluation that spans both contrastive and autoregressive models to formulate many of these tasks into a format that can be tested using these models. And then as we understand how they perform on some of these basic atomic tasks, then getting some sense of how far or close are we to the ultimate applications that I mentioned here. I won't actually go into the evaluation here, so I hope that for those of you who are interested, you can check out this paper. It is on arXiv. But we looked across surgical scene comprehension-based tasks, found that a lot of generalist models, even not trained on surgical video data, are already are able to do something here and performing reasonably in some cases, even though surgical data is in general harder to obtain and to be able to incorporate into training. But as you might expect, as we get into more and more surgery-specific tasks, looking at some surgical progression understanding, and then finally getting to risk and safety and skill, that even the more specialized surgical models, although trained on less data, do start to do better. And so although we've got some similar patterns, expected patterns here, I think there is, to me, it was very interesting to look into a lot of the nuances of how current models are working out of the box. What exactly are they able to perform to what degree, and how much gap there is remaining. Here's just some examples of how these questions and answers are looking as they're formatted for evaluating these models. And then we also looked at out-of-domain generalization capabilities, which is also actually an area where the generalist models start to be shining. So although some of the surgery-specific task domain models, so these are supervised state-of-the-art models for specific tasks, are still outperform a lot of these broad foundation models as we start to look at different sites, different hospital sites, different data sets, the generalist models, so the GPT types of models and Geminis, they actually start to have a lot of strengths and to perform better. So if you're interested, you can check out more at this link here. So we've talked all about these vision and language generative models, looking at generating text as output. And in the last part of this talk, I want to just briefly mention a different type of generative model now for generating image data. And so these are virtual cell models now for generating images that simulate the effect of, of screening for cell morphology changes based on drug perturbations. And this is work that's led by my student, now postdoc Yu-Hui Zhang, who's on the faculty job market this year, as well as Yu Cheng Su, a former intern who's now a PhD student at Harvard. So this idea of trying to build these virtual cells that can simulate and model the effect of different perturbations, this can be drug perturbations, genetic perturbations. I think this has been this kind of long-standing, exciting goal and challenge across a lot of AI and biology research. There's been a lot of work in particular also focused on transcriptomics based virtual cell modeling. And so here in this work, what we wanted to do was really bring in the image generative modeling aspect of things. Looking at cell morphology and this image-based screening is also a critical perspective here, in particular because a lot of the when we're developing these drugs, we would like to affect certain types of physical and structural changes on the cell, many of which can be visually observed. And so this type of image-based screening can perform this kind of first understanding of whether we are able to achieve these physical effects that we'd like, and then to be able to perform further study here. And so, what we have had in recent years is just a emerging amount of data to be able to work with for these types of problems. There's a lot of high content microscopy screening, producing large data sets. But one challenge that we often have to deal with is these real-world batch effects, right? Where this data is collected in different experimental batches, all of which have some slight, variations in whether it's some, intensity or other, variations that are essentially biases across for each of these batches. And so this is something that makes the data a little bit hard to work with in disentangling what's a true perturbation effect versus what is a batch effect. And so this is something that we tried to model and take into account in this setting, where our goal is we'd like to be able to learn how some types of control cells, which are typically always part of these wells, to be able to help understand batch effects, right? So experimentally, control cells are there for this purpose. And so in our machine learning modeling, we would also like to be able to incorporate and understand, use that to help disentangle our batch effects. So we'd like to map from these distributions of control cell images to perturbed cell images. And so in this approach that we called CellFlex, we basically formulated the problem as this distribution to distribution mapping problem where, where we actually becomes a natural fit for flow matching, which is at its base a distribution to distribution mapping type of technique. And so we formulated in this fashion, where you can see here wanting to learn the effects of different perturbations, right, across from a control distribution. And so the approach here, using flow matching, is that we'd like to be able to learn this velocity field that can match and that can map and transform a control image into what it looks like after perturbation. Right? So you can see that this linear flow field here is trying to map and gradually transform this control into a into a perturbed image. And so our goal is then to model this using a neural network to learn the parameters of this, and then at inference time, we can then apply this flow field to take input control images and morph them into their transformed images. And this is conditioned on the perturbations that we have. So what we found given this is that we were able to significantly improve upon previous methods for this task. And then this is just showing both for chemical perturbations as well as genetic perturbations. You can see some just qualitative examples here of control images at the top, and then what we look like with using cell flow and true ground truth perturbed images at the bottom. And one nice thing about this flow matching based perspective is that we can really try and simulate and try and model morphological change trajectories. So how we can go from, how the transformation, at least from the machine learning model perspective, is changing from one to the other. And so this gives us ways to now think about also studying dynamics, understand what's going on, to also study reverse dynamics. You could see at the bottom going the other direction in a way that you don't get with the, when you think about a typical noise to target distribution mapping. And so although, of course, this needs to be biologically validated, we've done some work on now trying to see and get, we have some promising signals on the types of actual trajectories you're seeing and whether they can be useful, but I think there's a lot of room for further investigation here. Okay, and so with that, I think I'm pretty much out of time. So we've talked today about these different types of multimodal generative models that we're working on in our group, both for producing text and natural language as output, as well as for simulating images as output across these different, both scientific sort of day-to-day research, as well as sort of drug perturbation modeling and drug discovery applications. We have continued to build on some of these works in posters that are presented at ML4H findings. And so up top, you can see there's work looking at sequential fine-tuning of medical VLMs, as well as looking at leveraging long context in training vision language models using Biomedica. And then on the bottom here, we also have a couple of posters looking at extending self-flex, both taking the work I just talked about and scaling it to foundation scale with many large data sets. And then secondly, looking at multimodal modeling of now looking at transcriptomics and images being jointly modeled together. And so I hope if some of you are interested, you can check out these posters in these sessions here. With that, I'd like to thank all of the members of my group that have helped to drive this research, and happy to take a question or two if there's time.
Thank you so much. We don't have time for questions, unfortunately. I'm very excited to introduce our panel on building health AI products next. And so we'll have three panelists. The first will be Ruchika Fernandopoulos. Ruchika is a practicing primary care physician who was co-founder and CEO of Iora Health, an early tech-enabled chain of primary care practices that sold eventually to Amazon. He's now CEO of Liza Health, which is trying to use AI to enable this sort of advanced primary care. Next on the panel is Anita Kannan. She is a founding team member and vice president of AI at CureAI Health. CureAI provides high-quality, just-in-time, and affordable virtual primary care for everyone. Previously, Anita was a senior research scientist at Facebook AI Research and Microsoft Research. She holds a PhD from the University of Toronto. Our third panelist is going to be Raghav Mani. He is the director of digital health at NVIDIA. He's focused on building agentic AI products and platforms for providers, payers, and pharma. Prior to NVIDIA, Raghav worked at Epic, where he led different product and engineering teams, including their deep learning team and their patient engagement platform called MyChart. He holds a bachelor's degree from the Indian Institute of Technology in Madras and has a master's degree from Texas A&M University. Moderating this panel is going to be Nathan Silberman. He is the CEO of Artura and has worked on launching AI and digital pathology-based tests that predict cancer risk and therapeutic response. Nathan's previous experience in healthcare includes leading the development of real-time AI tools for ultrasound at Butterfly Network and developing software infrastructure at Google Health. So let's give a round of applause for our panel. And everyone.
How's that? Sound good? Great. Cool. Well, thank you so much. This is very exciting to have such great panelists with us. I wanted to start out maybe talking very broadly. You know, I think everyone is aware of how much AI is in the news and is obviously on all of our minds and a lot of other people's minds as well. This is obviously making a huge impact outside of healthcare, and there's a ton of excitement, I think, from everyone here about how much AI can impact healthcare. That being said, we have heard this story a little bit before throughout the years about how AI is going to revolutionize healthcare. So maybe let's start by asking what is different about right now?
So maybe I'll start if I happen to have the mic. It's great to be here. I mean, so this has been going on for a long time. Back in the 1960s, we had Elias, the first chatbots. We had internets in the 70s. We had DXplain in the 80s. And they were all heralding a revolution in AI and healthcare. Of course, it hasn't happened. So what's different? Really, I think 3 or 4 things. So one is obviously the models have gotten much better. These are a lot smarter than all the other Bayesian models that we talked about before. But maybe more importantly, I think that the problems have gotten worse, right? And in general, healthcare sucks. The experience is awful for patients, it's awful for doctors. And the big problem we have is the supply-demand mismatch. We're all getting older and sicker. The need for healthcare is going up. Healthcare is getting more and more complex. And on the flip side, the supply of the human beings to do the job, whether it's doctors or nurses or fill in their blank, are going down, right? That fewer people are going into it. The people who are going into it tend to be, this generation. I have a daughter who's in medical school. They think people like us are crazy how many hours we worked. They have no desire to work this. We have this huge supply-demand mismatch. I think that's driving a lot of this opportunity.
I think the other thing would be patients want this more. I think people now want to talk to AI more than they want to talk to the doctors. This is mainly because I think part of that is with 2 reasons. One, Rishika already said, AI models are getting way better. The second is just that the scarcity of doctors right now. I mean, at Curai, we run a virtual primary care practice. Like for $35, you have unlimited access to primary care physicians. But I think we find, even if we give the choice to them, hey, do you want to talk to the doctor directly, or do you want to talk to the AI first? They seem to like to do the AI first before they go and see the doctor. And we're seeing this consistently, even when given a choice. So there is more room for people, more things that people want, and they want to be able to discuss it much more deeply. And I think the human is probably not helping them the way they could be helped. And I think that's like the big change as well. You want to add to that?
I mean, from a technology perspective, I think just looking back at my own past building AI, it used to be painful to collect all the data, to make a case that, hey, this is a particular use case that we should go after, and to validate that the model that we build is performant enough that it'll actually be meaningfully usable by a provider. Now, many of those use cases that traditionally you would have had to have a data science team build models, now you could actually use the foundation models and principally focus on it as an engineering problem. How can I take these foundation models and apply them to this particular solution? So I think there's a fundamental switch in many use cases where what used to be traditionally data science first and then engineering to just directly being an engineering problem. And that means that I think many, many more people can immediately start applying AI to many different use cases. So when I look across digital health, the amazing growth of people applying AI now compared to a few years back, I feel like one fundamental reason is that. It's just foundation models are ready to use out of the box for many use cases, not all, but for many, many use cases. And so that's more of a technology perspective.
Great, so there seems to be consensus. This is absolutely a different time. This is the right moment for us to be working on AI in healthcare. So let's say we're doing exactly that, and we really want to, yes, work on research, but have an eye towards creating a product that's actually going to affect patients. How do you actually think about who you are selling to? Who is a customer here? Is it the clinician who is using it? Is it the patient who's benefiting? Is it the hospital finance department who's doing the purchasing? Maybe let's start with the clinician.
So the answer is it depends. clinicians, and this is what makes it so hard. So while this is a huge opportunity, it's still really, really difficult. And probably the most difficult thing in healthcare is often the person who benefits from or wants this, the patient, often is not the person who is paying for it for a whole variety of reasons, with a few exceptions. Cura is one of the few exceptions. But in general, the vast majority of healthcare companies are built using some version of third-party payer. So it may be the patient who's using it or the clinician using it, but they don't pay for it. Neither patients nor clinicians are very good at paying for anything. And so you end up going to someone else, whether it's the health system or the health plan or the employer or the government or fill in the blank. And this is where it gets tricky, because often those interests don't necessarily coincide. And sometimes they actually oppose one another. So again, I think the hard part in healthcare is not building better mousetraps. The current mousetrap doesn't work. The hard part is getting someone to pay you for said mousetrap.
Actually, I want to change the question slightly differently, right? You have to ask, whom are you building for? What problem are you trying to solve? If you're doing it for payers, you're probably working on billing codes, and if you're looking for clinicians, you're probably making their clinical workflow better. And if you're building for patients, you're probably leading up to better outcomes. So you want to ask, what is the right thing to build here for, maybe? And the right thing always is about outcomes, because at the end of the day, as Rishika was saying, the person who needs to benefit the most is probably, or not even probably, is the patient, people who had care. So when we look at the problem that way, we can also start to think about how should we chip away AI into any of these workflows, but rather do it with the intentionality of improving people's lives.
Can I ask a question about that? You mentioned we all want to improve better outcomes. Do the outcomes always align with what is going to be paid for?
Yeah, I think this is where the real thing comes from what the people want, right? If patients want something, I think the hospitals will agree to it, and then the payers will agree to it. I think we have to flip this model of starting from payer all the way to patient, but rather starting from what the patient is. I mean, the easiest analogy I can give this to is for autonomous driving. 10 years ago, we were sitting here, you would say, there's no way people are going to be on an Waymo car. And today in San Francisco, I think parents prefer the teenagers to go in Waymo rather than a human-driven Uber, right? When technology starts delivering and you start to see people starting to use it, I think the entire field will shift a lot more. And it's probably looking a little optimistic, but rather I think our history has time and again shown that. So we should probably shoot always for the real thing we want to, and then work backwards from that.
And I think the problem, this is maybe more details people want, the current way that we get paid for healthcare is fee for service. There's a fee schedule, you get paid X amount for doing X thing, right? Again, putting patient retail aside, but in medicine, we get paid a fee schedule. The problem with the fee schedule is it's really about humans doing things, and it's sort of piecemeal. So right now, there really aren't fee codes for AI to do things. Now, here's what's going to be interesting, is as AI starts replacing a lot of stuff humans doing, people are going to want to put a fee code onto it. But the problem with fee schedules is they were designed in the mode of scarcity. There are a finite number of doctors and finite number of hours in the doctor's day. The thing about AI is it's infinite, right? It's abundance, it's plenty. So you can't put a fee schedule on it. So what's going to happen, and it's happening already, but slowly, is a transition away from fee-for-service into these value-based payment models, where instead of paying for things you do, you pay for results, i.e. improving outcomes. If you do that, now all of a sudden, there's a great business model for AI. You can just do the better outcomes at lower cost. Again, the company I started before, Iora Health, that's what we did. We said, we're not going to wait for the payment model, right? The unimaginative thing to do is try to design in the current payment model. The really cool thing is, what if you change the payment model so it actually aligns with doing the right thing for patients? So we were moving into what's called full risk models, where we said, tell you what, we're so confident by doing healthcare better, we're going to make costs go down and people's outcomes get better. So why don't you just pay us for that and not for each thing we do? And now we can be creative in how we actually deliver the care. That movement is happening. It's maybe not as fast as everyone thought, but maybe AI will actually push it along quicker.
I'll again add a tech optimist perspective here. Going back to my past in running MyChart, and this used to be the challenge. Like, we want to turn on capabilities for patients, but that meant potentially adding some burden to the physician. Open up messaging to patients means that you have a huge inbox overload for physicians. And I think technology finally has solved it. Like, now you have within the EHR workflows automatically pre-populating responses to patient messages so that the physician doesn't have to spend as much time responding back to the patient. Another example would be like an abridged ambient documentation in general. You have one stakeholder, which is the physician in a hospital, and then the other stakeholder could be the IT team or the finance team. You have a solution like an ambient documentation that both addresses the physician burnout aspect as well as improves efficiency and addresses the bottom line aspect as well. So I feel like technology, yes, you do have multiple stakeholders in in a number of situations, and the tech optimist in me is like, you potentially can address in a number of these situations simultaneously the different things that motivate those different stakeholders.
Okay, so let's say you are one of the machine learning researchers here. You have an idea in mind. You've identified effectively the one or multiple customers. What clinical questions should you encourage them to answer first before they actually start building anything?
I think start with the problem and the end in mind. What's the problem that you want to solve first? I think I'm going to take the technology view all the time, so I would want you folks to talk through the end user workflows. But again, going back to my past work, you can have the best technology in the world, but unless it's seamlessly built into the workflow of the clinician, it's not going to move the needle. It just won't. And so then you have to think about what is the cognitive burden that your solution adds to the physician when they actually use your technology. The less cognitive burden that you add to them, the more in their flow it is, the more likelihood that technology will get adopted. So I guess start with the end problem that you're trying to solve in mind and work backwards from it. And I think deep integration with the clinical workflow so that you are not adding yet another thing that the physician has to go look at. I think that is critical for success.
I think I will take a slightly different viewpoint, also as a researcher, but I think the main thing here is one of the advantages we have as a researcher is to think really, really big. And when we start thinking about problems from existing workflows, sorry, I'm going to be against this, is that we start to look at very suboptimal ways of solving a problem. Right? We will take the existing clinical flow and say, oh, I could build my technology here, a little piece here, it will save like 2 seconds of, or maybe 2 minutes of a doctor's time. Right? Seems like a success, but it doesn't really solve the problem. As researchers, I think you can go beyond that. I mean, really 50% of the world population don't have access to a doctor. And most people visit a doctor maybe at most twice a year, maybe just once, hopefully. And when we start to think about where is AI today, where can AI be in the future, and how can you actually go and change lives of 8 billion people, you move away from constricted view of what today's doctor's office is, I think. And you can start to think about where could be healthcare as a birthright of someone can be. Right? We need to look at the transition, and researchers are extremely well equipped to do that. The challenge we always have is that we also constrain ourselves to our own data sets and our own evaluation paradigm. And we start to think, oh, it has to be 100% perfect before we launch something. The reality is that you don't need to be 100% perfect. You should have an eye towards it. But you should always leverage beyond AI. How is the UX experience going to look like? How is the design going to look like? You can start thinking about holistically and what are the guardrails I need to set for me to make that baby step. So 2 things for researchers. One is, are you solving a problem that is worth solving for a very large population? And will it actually lead to any sort of disruption? Number 1. The second thing is, how can I take the crux of that and start to do something simple first and expand? But having enough guardrails so you don't sacrifice patient safety, right? So those are my 2 things.
I actually don't think you disagreed. I 100% agree with you. I think the user experience is what I was referring to as well. And I also take your point that the solution is not just to build a faster horse all the time, right? To reimagine what the automobile would be. So it's not always, you shouldn't be constrained by whatever is the way it's done today. But still, ultimately, there's the data science and building an AI, but there's an actual end user experience that you have to think about, and the end user experience is critical. I want to add one more thing to what you said, which is when you deploy a POC, and there's a death by 1,000 POCs, right? When you deploy a POC, that's great. I would strongly recommend people building AI products in healthcare to think about also deploying a data flywheel, a methodology to continuously improve. Like even in the course of a POC, if you can show that you can make it better, that's really compelling, I think, because it's making the case that this is the worst this capability is going to be. It's only going to get better. So I don't see that all the time, and even in my past life, I didn't necessarily build in the plumbing to make a system automatically start getting better, as even in the POC stage. But that's what I would suggest for people building new products. When you put out a POC, have the instrumentation built in so that you can collect data and continuously make it better, even during the course of the POC.
Yeah, totally agree. That's what I meant by start with the crux and go build it out.
Yes, again, agree. We need the technology work. We need data flywheels. We need to make sure the workflow works. We have to figure out how to get paid for this, which again is really, really hard in healthcare, because it isn't enough to do the right thing. You need to do the right thing and have someone pay you for it. And unfortunately, the obvious way to go, what almost every company does, they try to sell to the people who have the money, no duh, which are often the health systems or the health plans. And if any of you have tried to work with health systems or health plans, they're a pain in the neck to work with. You get caught in endless meetings with endless numbers of people. Neum Gandhi, the CFO of Mount Sinai at one point said, the problem is your Series A doesn't long enough for my sales cycle, right? It can take years to do this. And then you've got this operative risk of you spent all this time trying to build a relationship with the one buyer who's going to do it. We were working with the head of United's Medicare Advantage plan in New Hampshire. We spent a year negotiating a deal. We met for lunch, shook hands. He said, I'll send you the contract when I get back to my office. Didn't send it to me. Next day, didn't send it to me. I call up. Turns out he died in a car accident on the way home, which was awful for him, but awful for us because we had to start over with a new person, right? This stuff happens over and over again. So again, trying to get this. And so then the problem is, I think what's easier now is to get pilots going, right? So the obvious path then is a lot of these groups have innovation groups, so you can actually sign up with the innovation group to do a pilot. The problem, of course, there is you can have the pilot, but even if the pilot isn't successful, you obviously won't go anywhere. The problem is if the pilot is successful, where most companies have a huge problem, is going from pilot to actually going into production and going across the whole institution, because it's a whole nother set of people you have to convince, right? And I think the key to this is, no matter how well it works, are you high enough in the priority list of the problems they're trying to solve? Because even if this works well, but it's a low priority problem, no one's going to spend all the time and effort, because they've also got 10 other people or 1,000 other people banging down their doors to do pilots or to put things in production. So again, I think the key to start with, and you said, is you've got to start with solving an important problem for people. If it's not an important problem, it's not going to go anywhere.
So this is a great way to transition from, I think we started with building proof of concepts, now we're getting a little bit into building products. And I think we heard somebody mention death by 1,000 POCs. I think it was a very apt term. What do folks who are interested in doing exactly that, what do folks need to know about how to actually make that breakout out of, say, one institution? What sort of hurdles do you run into? We just heard a couple. What are other things that people should keep in mind with an eye to not just having, say, a POC running in one institution, but ultimately spreading to more?
I mean, trust is such a huge thing in healthcare, and I think one of the things that's really important, particularly when building in this space or in any space, is to make the right promises and keep them. And I think it's very easy to oversell. Oh, this never hallucinates. This works 100% of the time, right? And that just may not be true. And I get why one wants to oversell things to sell it, but that will come back and bite you in the end, right? So I think just be very careful about the promises you're making. Make sure you can back them up Once you built that track record, that's important. Your number two is this is an insider sales game, and I think it's very hard as a complete outsider to come in. And I think this is about building teams, by the way, and having people who are, yes, you need really smart AI, ML folks, but you also need people who actually know the industry and actually know the people in the industry. That makes things 1,000 times easier. Our first sales, we partnered with a broker, a group, Mercer Health and Benefits. They sold into employers. They had a 100-year history of a company. They could get us in places, right? And yes, they took their pound of flesh when they would sell us. They were reselling what we did, but I think that's important in the beginning.
From a technology perspective, I want to highlight a couple of examples where I've seen like a hockey stick growth in adoption. And I think one thing that both these companies did well is reducing the friction in scaling from POC to an enterprise-wide usage. Not all situations will match this, but if you can, as you build your product, if from a technology perspective, if you can minimize the friction, minimize the IT support needed to get your problem to scale across the enterprise, the easier it is to do that. So a bridge as an example, their solution, hockey puck growth, individual physicians can decide whether they want to use it or not. It's not, once you have it going, individual IT departments don't need to intervene as much. The another one example is open evidence, where IT doesn't even come into picture. It's just a chat GPT for doctors that they can just go and use. Not all solutions that you build will fit this mold, but the more you can make it easy, purely from a mechanics perspective, to scale from POC to enterprise-wide adoption by building appropriate technology tools, I think that's another way you can make it go faster. You still need the stakeholder buy-in. You still need someone for whom this is important enough that they say, yes, go enterprise-wide. But you can still sometimes get stuck in implementation slowdowns because you're now dependent on the IT team to do it, and the IT team is overburdened with so many other things to do.
Yeah, one thing I may add to that, two things. One is when you go in for these pilots, make sure the pilots are worth your time also. A lot of the times it may look nice to have a pilot because every pilot leads to more work. And sometimes it takes away from the goal that you're setting yourself for, because you have to know where you're heading and then how is this pilot serving you versus is a distraction. So it's okay, and that's why I think there is a little bit of that pilot issue. There's also this marketing thing, right? There's a lot of marketing happening because of these pilots, but do they all translate into like real promise or real promise towards your goal? So being a little bit more thoughtful there in which pilots you're signing up and why you're signing up and what would be the upside for spending that time is useful. Not saying you should never do it, but I think pilots is not equal to like business problem. Yeah, I agree. So that's one. And then the second thing is that we don't have to be always an expert in everything. And to your point around like people insider and so on, as you start building a technology, you can start bringing along people that are expert at the things that we are not good at and sort of build it out. So I think when we start building companies, we think that we have to be expert in everything, and you don't need to be. You can be expert in one thing, but still be able to bring along other people who are expert at that. And that's another thing that we miss out also, I think.
So one thing we talked about a little bit is the data flywheel. I think a major transition that often happens from POC to building a product and certainly to building a company, as we'll get to in a second, is really getting access to data and real-world data in particular. What should folks know about the difficulties of getting data and how to actually get their hands on data, which often institutions are holding on to very tightly? How should folks think about that problem?
So I have two answers to that question. So when we first started Curai in 2017, where most people didn't know about AI other than if you're coming for one of these NeurIPS conferences all the time. So at that time, I think we even had to have a slide set on what AI is when we went for our first Series A. So at that time, we realized that just getting access to any EHR data or a hospital system may not do the job that we need it for, because we are trying to build primary care from the get-go, where AI is doing most of the work, and the doctors are doing the final decision-making within the constraints of regulatory stuff. So we started to build our own clinic right? That's how we started, so that we can actually test. This involved us building our own electronic health record system as well, because then we can put the kind of ML framework we need. We can get to that as well. What does it mean for doctors to use AI? There was a really nice perspective talk earlier today. So that's one part of the puzzle, right? Where can you use it? But I think the field has changed from 2017 to now. I think most of the general purpose models does a lot of the good heavy lifting. And the personalization or the domain level EHR can be done much more efficiently now than in 2017. So I think the old problems around having access to a lot of EHR data from different hospital systems, those problems are not present yet, because as you're saying, like as we build our own flywheels, as we start collecting our own data, you can improve the systems. But I think the key now has moved to how do you set up this ML problem in a way where you can get either implicit or explicit feedback all the time, right? And if you did get that data, what are you going to do as a next step? All that has to be laid out. So it's not just it's an engineering plus a research problem too, because I think as new ways of RL post-training is coming along, how we're thinking about reward systems to build for these, you can also start to collect that kind of a data in your platform to do it. So it's still an open problem for researchers, I think. And so it's actually an interesting time to be being a researcher and being in industry to build these things.
So there are many applications where you do want to get people's past medical history, right? So again, as powerful as these new models are, that they're more powerful in context and having people's data. Now, no offense to your prior friends at Epic, the people who own the data, despite what the laws and the rules say, are not very happy about letting you have that data. Part of that is, they think it's proprietary. They did spend a lot of money and effort in getting it. They're tired of people taking their data and then monetizing their data, et cetera. So whether it's the EHR company, the health systems, the health plans. And then, so lots of problems. So one is, despite, in theory, a lot of standards, FHIR and SMART, et cetera, these things are not quite as good as you think they are. There's frameworks. They're not, unlike a lot of other fields, they're still pretty open. Number two is, like I said, the people who own the data typically don't like you to have it. And three, the data, even if you do get it, it's imperfect. People have stuff filed in the wrong place. This is very messy data, right? So what's the way around it? I think the best, there are a bunch of companies now, whether it's Health Gorilla or, go down the list, Zeus, who in theory, this is what they do for a living. They're data aggregators. They're all imperfect. They're expensive, et cetera. Another avenue is there's pretty clear laws now about that health data belongs to the patient, with the period at the end of that sentence. And this administration actually believes really strongly in that. There are huge fines, actually, for people who are doing information blocking. So you can actually, on the patient's behalf, go and get their data, right, with their permission. And there are a lot of people who tried to block that, and they've typically lost. Epic lost a case fairly recently where patients were trying to get their own data. They said, no, the patient should be able to get it, and another company on behalf of the patient can do it, right? So I think, again, it's very important to get good data. Health data is notoriously finicky in a variety of ways, but there are ways around it.
So again, I'll have the techno-optimist take on this one, which is, I think health data is very messy, and especially the general principle is that medical imaging data can also be messy, but machine-generated data tends to be messy in a relatively predictable manner, whereas human-generated data is messy in an unpredictable manner. So one good thing in my mind with all the latest Gen AI tools and LLMs is that you can clean that messy data, the long tail of messiness, using these foundation models. It actually is quite powerful. It's almost impossible to programmatically capture every one of those edge cases and say, here's how you should do when the data is like this. But the latest foundation models are actually pretty good, pretty robust in handling that long tail of use cases. So at least there is an optimistic take that technology can come to the rescue if you have access to the data, even if it's messy. Now, if you don't have access to the data, I'm going to do 2 plugs for 2 open source projects that we are involved in. One is called FLAIR. It's a federated learning SDK. So there are ways where you can set up an arrangement with a hospital system where you get access in a private manner so as to do your model building, but you don't get access to the full data. But you are able to train a model in that process in a federated manner. So we are part of an open source project called FLAIR, but there are other open source initiatives of that type. The second one, again, a little bit of a plug is, this is another open source project called Nemo Data Designer. But the general principle, even if you don't use that particular product, but the general principle is that synthetic data generation using as seed data, actual patient data. So maybe you don't have access to go use that data all by yourself from a hospital, but you can set up an arrangement where you can use it to simulate some synthetic data that have the similar statistical properties as the source data. And then you use that data to train your own model. So I think there are some, now each of these have some other friction points with them. They are not a panacea by any measure, but I think those are interesting tools in your toolkit. In situations, if you can train a model in a federated manner, there are tools for that. If you can generate synthetic data, again, using some seed data that is real data, that's another a technical approach that you can bring.
Okay, so let's say, we've gone through proof of concept, we've built a product, and there's a fit here. How does one go from there to actually starting a company? There are obviously a lot of components to the answer to that question, so maybe let's try to narrow it down. Who do you need to hire? What roles? What sort of folks succeed in healthcare?
I'll give it to you.
Yeah, no. So it takes a village, right? These require building a team, and I think a mistake a lot of early founders do is they build a team of a lot of people who look like them with their set of expertise. And that's all well and good, and it's very comfortable, but what you need to do is build a team with people who are not like you, who can fill out the set of skills that you want to do, right? And I think one starts small and builds, and as you figure out what you need, you find those people. So I think maybe the most important thing about successful companies is building the first 5 or 6 people. That allows you to build the first 50 or 60. That allows you to build the next 500, et cetera. So I think being very careful about who the people you bring on are, what their set of skills are, and then obviously that they work together well, right? Those are key.
Actually, I'm curious if we can stay with you for a second, just given your experience. I think a lot of healthcare companies are often made up of a village of, as you said, of people with very different backgrounds and areas of expertise. Can you add a little bit onto that in terms of what sort of people do you need to go and hire? You alluded to before, you need to hire some insiders. What kind?
Yeah, so I think about the team. We're building an early stage startup, Liza Health. Pyle is a proud member of our team, and so I'm a physician. Have been building these primary care practices for a while. We have a technologist, Andy Palmer, who's a data guy, who's built a couple of data companies. We've got people like Pyle who are in the AI space. We've got a few other clinicians. We've got some engineers. Designers are very key, right? So much of this is about human-centric design that almost all of these things have to interact with both patients and clinicians, and getting those interactions right is actually a huge part of the issues. You get some of those. You need some finance folks. You need some, the business folks who can help, with raising money, right? So it really does, it's sort of a small set of people. We've got about 8 or 9 people on the team right now, which is probably the right size to get going.
One interesting thing that I'm seeing on the technology side is that the distinction between a product and engineering is blurring, especially as the ability to be able to build, engineer products is the barrier to entry, the barrier to doing those things are dropping. So in some sense, I'm not taking away anything that you just said, but one other attribute could be like the ability to learn new tools and wear different hats. It's almost like AI is giving you the ability to become a polymath, like that you can do more than what, just one particular skill. And so I see a little bit, at least in certain domains, a blurring of the traditional boundaries of product design and engineering. It is possible in my mind with these new tools that a single person can actually learn all of these do all of these different things by taking advantage of these the latest tools. Subject matter expertise is still key. I think that one, having someone in your team that has the subject matter expertise is without doubt important. But at least on the technical product and design side, I can see a little bit of blending where there could be one person that could wear all of those hats pretty well, especially in the early stages.
Yeah, maybe to Shika's point, I think one thing that a lot of startups do forget, especially in healthcare, is to have strong research team as well. Because especially now, because I think that, AI has solved all the problems. Because you're looking at problems 10 years ago and you're saying they're all solved today, but you just don't know what the next set of problems are. So if you want to build a company that is actually going to solve the real problems, which you haven't still uncovered, I think, because we haven't even gotten into preventive care yet, right? We're still trying to work through people are already having health issues, and now we're opening doors for a lot of preventive care. So there's lots of work that needs to happen. So from the get-go, it's important. Researchers play a very important role. I think the researchers, not just only doing machine learning, researchers who can also work very well with the UX folks, right, with the design folks. Because then you actually start to build an AI product as a thing, so where you can actually collect the data and collect the kinds of data you want to answer research questions that will open doors in the next 3, 4, 5 years. So that's very important as well when you're building the product.
Okay, so let's say you have indeed gone out. You may have a small research team. You have some folks from clinical, maybe commercial. Obviously, we need to pay all these folks. How do you all go about actually raising money? Is it possible to bootstrap yourself? Who do you go out and raise money from, and how?
So it depends. So it takes a lot less money than it used to start these companies, right? Because of all these tools, because you don't need to have huge engineering teams, because you don't need to outsource a lot of stuff, right? So I think you could, you don't need as much money as you needed to, but you still need money, right? You need to pay most people. People need to eat. Often in healthcare, you get paid, these pilots don't pay very much. I think it's really important to get people to pay you early on, but you're not going to get rich off pilots. You need to, figure stuff out. You'll make mistakes, et cetera. So in general, you will have to raise money. There's a whole usual set of things. By the way, no one will give you loans, really. There's some grant money out there, ARPA-H and SBA grants and the like. So there's a bunch of money that's non-dilutive you could try to get. Obviously, a lot of people go to friends and family. These days, if you have a good AI healthcare idea, there's plenty of venture capital out there for you, right? Now, to me, the key is being really careful about who you take the money from, because you're going to be stuck with these people for a very long time. When we started our prior company, we had our 11 years from we took money and to the time we exited. 11 years, that's longer than most people are going to be married, right? So you better like these people, you better share the same values, you better make sure. So it's not just about who's going to write you the check, who's going to give you the biggest valuation, it's who's going to be the best partner for the long haul. And that takes, and then the problem, of course, is you went into this because you want to solve these cool problems. And you could spend your whole life fundraising, right? And the typical fundraising cycle is typically 18 months or so. And then it takes you about, by then 6 months to raise the money. So you're a little like running for Congress, where people running for Congress are always running for Congress. At some point, you end up always raising money. So again, the key is it is important. You have to raise it. There are lots of flavors. But I think the key is being really, really picky about who you raise it from. And a caveat, it's easy to take money from tech investors. The problem with the straight tech investors is they don't understand how painfully slow healthcare is. And so they're used to these sort of Oculus Rift in 18 months became a $1 billion company. You can't get your first contract in healthcare in 18 months, right? So again, I think you want to make sure that the such thing is taking, but you want to make sure there are enough people who you're taking money from who understand that you're doing something in healthcare, and you can't move fast and break things, and things take a little longer than you think.
So is the answer don't go to tech investors, just go to healthcare investors?
No, I think it's good to get a mix of those folks. We had Vinod Khosla, who was father of your CEO, was one of our investors, of tech investors on Microsystems. He was a great investor, right? So I think you just need to get sort of the right people on board and a good mix.
I haven't built a company, so I can't speak to it. But we do, just for the folks that are building startups, a quick plug would be that we have a Inception program, which is an accelerator program, and we can make introductions, and we can also find you subsidized hardware as well. So if you are a startup building stuff, reach out to me.
All right, so assuming you've managed to raise some funds, you have a product, how do you actually get hospitals to notice you? And how do you get them to ultimately trust that you're building something good?
I think I always go back to the basics. The basics is that will people, so it really depends on what you're building, right? If you're building for clinical workflow, definitely the hospital system, I will leave it to someone else. But if you're building for patients or users, I think direct to consumers is the right strategy a lot of the times, because you get to quickly learn from users what they want. So at Curai, we do run a primary virtual practice. Just a little plug on that. And so a real virtual practice, but for less than your coffee, maybe $35 a month, you have unlimited access to primary care practice. It's mostly AI run, and and every patient goes through the doctor, but the work is done, most of the work is done by AI, right? And with enough guardrails. So sometimes it's about like, what is the problem you're tackling is important, and again, you need to have really strong investors who also believe in it, to give you the time and the space for you to work through this. So I haven't answered your question, because that one is a hard question. How do you get hospitals to notice? But I really think that it doesn't have to be always a hospital notice. It may be that the patients are bringing the thing to the hospital, and then the doctors are starting to notice it, and that can have an influence as well. You may have a better answer.
No, so it's hard, right? I think the good news is you only need to have one, right? And I think the thing not to do is to try cold calling hospitals. That's an absolute waste of time, right? So you need to find the ones who are just the true believers, who really care. And it's almost always through some version of personal relationship with someone that you know or someone you know knows. And again, you just need one, and you say, let's just build this together, right? And maybe you'll give them a little bit of equity, and you figure this out together. Because once you have a successful thing going in one, it gets so much easier for them to, again, go talk to their friends and say, look at what they're doing here. And then you're in, right? So the hard part is getting the N equals 1. By the way, a big plug for getting an N equals 2. The problem in healthcare is you've seen one hospital, you've seen one hospital, you've seen one health plan, you've seen one health plan. And it's very easy if you only build with one partner that you do quirky stuff that doesn't generalize, right? So the key is if you get two. So when we first built, we worked with 2 different places. We built a practice in Hanover, New Hampshire with Dartmouth College. We built one with the Las Vegas casino workers. They're completely different, but it allowed us to learn what is it that's generalizable, and what do you need to sort of make different when you do it in different places? Because you will have to do a little customization, but you'll never learn that if you do it in one place. So just find 1 or 2 and do whatever it takes, and then don't worry about scaling. I think a problem a lot of people make is they try to scale before they know what the hell they're scaling, right? So focus on what you're building. Once you figure it out, then you can scale, and it'll be easier, but make sure you know what you're doing and find the first couple.
Okay, last question, because I know we're going to take a pause for Q&A. I want to piggyback on what you just said in terms of scale. I think all industries deal with certain scale problems. Is there anything else in particular to healthcare which is an obstacle to scaling?
Well, there are all sorts of barriers in healthcare to scaling. So one of them is state-based regulation of healthcare, right? So if you're trying to run a virtual primary care practice and you're having physicians, the physician has to be licensed in the state where the patient happens to be that you're serving, which means if you're doing something on the App Store, you need to have physicians licensed in 50 different states and route that problem to the, right, it's a pain in the, and then by the way, then there are people who try to keep up multiple licenses. You don't have 50 different people. But then the problem is each state has quirky little CME regulations and different laws and whatever. So there's a lot of regulatory crap that healthcare has that most other places don't. You know, I think this whole the tolerance for you making mistakes is very low. I mean, on the one hand, it's the litigious environment, And I think, obviously move fast and break things. If you did what, a lot of other tech companies do, you couldn't get away with that in healthcare. So it makes it a lot trickier. So why on earth are we doing this in healthcare, right? Why we should be going and we're going to do this in tech? Because it's such a huge need. And because I think, it's a huge human need, and it's a huge opportunity. We spend $5 trillion with a T dollars on healthcare in this country. We know for a fact that at least a third of it is waste. And if we could do it better, that's what, $1.5 trillion a year. All of the tech companies were built on the global advertising market is about $400 billion, right? This dwarfs what Facebook and Google were built on, multi-trillion-dollar companies, right? So I think there's just this huge opportunity if we do it right, but it's really hard.
All right, well, thank you so much. Well, let's take a pause here, and we'll go to Q&A.
I have a question. Basically, we have created a good idea, especially to optimize the cost for all the genetic tests for prostate cancer. This is basically a project that we have been created over the last 6 months. This is basically so we are thinking to go to the next phase, which is clinical trials. This is something that we are basically contributing with the University of Illinois. What in this position, maybe it's a really direct question to you and maybe a bold question, but what would you do in this step? So how would you engage maybe investors or somebody that back up this plan and will say, hey, I would like to move forward to optimize the cost on prostate cancer clinical trials for genetic tests. How exactly will you address this situation? What recommendation will you give us? Thanks.
Yeah, by the way, we didn't even add the whole FDA layer on top of this, right? So if you want these AI applications to be autonomous in any way, right? So if you're just building tools for doctors to look at and sign off on, you're in pretty good shape. But if you want patients to directly do this without the doctor involved, there's a whole nother set of things about going through FDA approvals you have to go through, right? Which takes all sorts of trials and tens or hundreds of millions of dollars eventually, right? And I think the problem is the FDA is just trying to figure out how on earth to, other than the vision stuff, right? So they've had a long track record of certifying radiology applications, pathology applications, but these sort of other sort of knowledge-based things, they're still trying to figure out, right? So we don't know. So I think the key is the two things you need, other than the team and the idea and the product, is a place where you can test it. So trying to find a place, a health system or a physician practice or even an advocacy group for prostate cancer survivors or someone who's going to help you get patients to try this on. And number two is funding. And I would start with the people who care about this problem, right? That's the only way to go is who cares about this problem? Are there people who have had prostate cancer in their family, et cetera? Have them sort of seed this early on, and then the more traction you get, the more you can then go to more institutional folks.
Hey, just a quick. When the engine was created, before having like modern cars and taking full advantage of the technology, we had these horseless carriages, which is like the new technology, but just mimicking the previous things. In healthcare, there's also this like resistance on adapting to the new things. So what's your perspective here? Like, can the horseless carriage stage be skipped? Or is it like a necessary step because of the resistance that exists?
Yeah, very great question. It also relates to some of the perspectives that was shared in the morning session. I think we're at the crux right now where we still think AI as supporting the doctors. And I actually think that is not the case. We may be able to skip. except for FDA and regulations. So we really need to figure out how to work. I wouldn't want to even use the word collaboratively. How to do the job in a way where when AI is good at it, you allow the AI to do it. And the way AI is impoverished, fall back on the physician. We really need to figure this out properly, I think. And so unless we figure that out, I don't know if we can really skip the step because of regulatory reasons. And
No, so I think we have to, right? So I often frame it, so I don't know if I'm from Boston, Massachusetts, and if you've been in Boston, we have these ungodly roads that sort of meander around everywhere. Because what we had is we had cows in the 1600s that were wandering around the Boston Common. And when we built roads, we just paved where the cow went. As opposed to saying, wait a second, maybe now that we have these car thingies, we can skip the cow thing and go straight line, right? We never had a fire in Boston like Chicago or San Francisco to burn it all down and rebuild, right? So we've never had a fire. And so we stuck with the cow paths. And so I agree with you. I think the vast majority of companies today are paving the cow path with AI. They are simply taking the current process and AIifying it. So not to pick on our friends at Hippocratic, right? So the way we do disease management is we have a nurse call people at dinner time and ask them to check up on them. That's wholly ineffective, by the way. So having an AI agent do what the nurse did, doing something ineffective with AI is also ineffective. Might be a cheaper ineffective thing, but it still doesn't work, right? As opposed to saying, what's the right way to manage people's blood pressure? And maybe it doesn't involve nurses calling them or an AI nurse calling them, right? Now, why are they doing that? Because the stupid payment model pays you hourly for the nurse calling the person. So again, this is what's hard, is what we need to do is sort of start from scratch and say, what's the need? The need is, how do we improve people's health and keep them out of trouble? And how do we build models that serve that? But that often requires doing things differently. What's interesting is some of this innovation might happen in other countries, right? Because just like they skipped the landline phase and they can do cell phones. So there's some really cool stuff that a friend of mine, Rob Kozel's doing in Kenya, right? Because they can. You can do anything in Kenya, right? And doing some cool A model, because there's no FDA, there's none of that stuff. And then the payment model is self-pay, so you can do whatever you want. So I agree with you. The way to really make an impact in AI is stop paving the cow path.
So, I live in Boston too, so I hear what you mean. Though I've been told that that's an urban legend, that the cows meandering being the reason for the roads. I too had the same thought of leapfrogging in a different context, like in developing countries. And the classic example is the cell phone. Like, in India, I'm from India, and, cell phone adoption is pretty much universal. You skipped the desktop and the computer revolution and just jumped over to the cell phone. So I do think that there are, if you look outside of the US and the restrictions that you may face in the US and other places, you may have an ability to reinvent or come up with a new business model more easily, just because there isn't a structure that is resisting what you're trying to do potentially, because it's just, at an earlier stage in its development.
I'll add one thing onto that, which is, it's not just the regulatory bodies have a hand in this as far as the FDA, et cetera. There are a whole bunch of federal compliance regulations. There are state level regulations. There are interests who don't want things to change maybe as rapidly. So it's hard to imagine a world in which we have a wholesale change. What that fire would look like that would allow us to rebuild from scratch is hard to imagine. Maybe none of us really want that to happen. But it's hard to imagine things not really changing with some amount of incremental change. That being said, I do think there are companies like Curai and others who are really trying to move the needle far forward, really trying to directly go to consumers and have them effectively vote with their feet instead of calling the representatives and demanding change. I think the trick here ultimately is really making sure that if you have an idea for a technology, that you're able to figure out how to get paid along the way, such that when finally payments and insurers change that direction, your company is still alive. That is really the hardest piece of this. I think we have one more question.
So you mentioned the funding cycles being around a year and a half or so. In my experience, I worked in biotech, and now I work in Oracle Health, so kind of seen sort of two different sides of healthcare. In both sides, it seems healthcare is a slow industry. Everything takes time to kind of go into effect. But the funding cycles, particularly if you're building a startup, are pretty small. So it seems like there's really not enough time to basically pursue the big, bold, long-term ideas that many of which are being pursued in academia, but there's just neither the time nor sort of the incentive for multiple companies to pull together, create joint resources. There are some examples like the Chan-Zuckerberg initiative, what they've done to kind of create pooled resources, but that's a nonprofit, and there's not that many examples of similar things. So I was wondering, if you see a way to kind of bridge the disconnect between some of the really cool work that's happening in academia to sort of the type of work that is happening in industry, just because there's sort of a lack of just different time scale of operation.
Yeah, I mean, so Bill Gates said it well. He said we overestimate what we can do in a year, but we underestimate what we can do in a decade, right? The stuff we're working on is going to take a decade, and we need to be able to fund in the typical funding cycle. So we were able to, we built a company where we were funded over a decade, took 11 years from our Series A to when we exited. Our investors did well, but who did we find, right? So there are people out there who are willing to do long-term thinking. Then they're few and far between. They're not the private equity funds in general. So a couple categories. One is family offices. There are a number of family offices where there are people who've made a lot of money, and they are long-term thinking, they're mission aligned, and they're willing to actually put money to work for. They're not in a hurry. We raised some money from, there are strategics, right? You mentioned Epic. There are a lot of strategics who are willing to potentially fund things over a long period of time. Eventually, we get big enough. Our biggest investor was Temasek, the sovereign wealth fund from Singapore, right? And by the way, other countries, Temasek talks about 50-year time horizons. We're investing for our grandchildren, and so there are people like that out there. They're hard to find, but like I said, but you are right. For us to make progress, that's the sort of time horizon we need.
I'd add one thing to that, which is also, assuming you can't find the right set of strategic or not partners who are willing to write, the $1 billion check, I think you can still hold on to that very big, long-term ambitious goal. The trick is really how to break that large ambitious goal into small parts, each of which make you money along the way. Very easy conceptually, obviously really hard to do in practice, but that's where I think the differentiator has been for a lot of companies that have succeeded in healthcare with some very big ambitious goals, really breaking it down. And I would say also similarly, when I was at Butterfly, the company was founded in 2011 with one idea, pivoted, eventually going public in 2000 with a handheld ultrasound that hooks up to your iPhone. And they really had a good understanding of how to be careful with your burn, but also how to make money along the way. Right. Cool. And with that, I think we'll thank our panelists.
Thank you.
All right, so next up we have Dr. Pierre Elias. He is an assistant professor in the Division of Cardiology and the Department of Biomedical Informatics at Columbia University, where he practices as a general cardiologist. He's also the medical director for artificial intelligence at New York Presbyterian. He runs CRADLE, the Center for Cardiovascular and Radiologic Deep Learning, which develops AI technologies for medical imaging to improve the detection and management of cardiovascular disease. CRADLE has screened over 1 million patients for cardiovascular disease using AI in nearly a dozen clinical trials and programs. Dr. Elias has received his medical degree at Duke University School of Medicine in North Carolina. He completed his residency in internal medicine and fellowship in cardiology at NYP Columbia University through the clinician scientist pathway. He's been named a Stat News Wonderkind and received the Emerging Generation Award from the American Society of Clinical Investigation and the Katz Prize for Cardiovascular Research. He was previously a data scientist at Lumiata, helping develop Google's knowledge graph for health. So let's give a warm welcome to Dr. Elias.
Hello, thank you all for being here. I've only got one goal, which is for this talk to not be boring. It can be controversial, you can yell at me, all of that is perfectly fine. But as long as you guys are entertained, especially post-lunch, I'll be happy. These are my disclosures. So my story started around 7 years ago. I'm a cardiologist. I was staffing the cardiac ICU overnight, and I got a phone call from an outside emergency department. They had a patient, and that patient was very sick, and they wanted to emergently transfer them to us. So the situation was this gentleman in his 60s had shown up 3 months prior to the same emergency department with chest tightness and shortness of breath. And they examined him, they ruled him out for a heart attack, and they said, listen, you're not having a heart attack. We hear a murmur when we listen to your heart. You should go see your primary care doctor, but you can go home. And so he went home. He made an appointment with his primary care doctor, and he was waiting for it. And then he got that same episode of chest tightness and shortness of breath 3 months later, and he showed up at that same emergency department. This time, though, he was having trouble breathing, and they had to put him on a ventilator, and they had to immediately send him up to their ICU. They ended up doing an ultrasound of his heart, an echocardiogram, and they saw that he had something called critical aortic stenosis, which is a form of valve disease. So we have valves in our heart, and just like the plumbing at home, they can get leaky or rusty, and if they get too leaky or too rusty, it's life-threatening. And Columbia, where I practice, is a world-leading center in valvular heart disease. So they were calling me in the middle of the night saying, this guy's really sick, we need to send him. They sent him over to me, and I spent the rest of the night working on him. But unfortunately, by the morning, he was critically ill, he was in multi-organ failure, and there was nothing we could do, and he passed away later that week. And I remember sitting there with his partner and telling him that I was so sorry that there was nothing I could do for him. And the frustrating part about all of this was that if we had just known about this disease, he could have gotten a same-day outpatient procedure, and I think he'd be alive today. The second frustrating thing about that was there was no step that had been missed. It's not like someone wasn't adhering to some guideline. We just don't have a screening test for most forms of cardiovascular disease. We have colonoscopies and mammograms, but we have no equivalent for the most common cause of death in the world. It's this strange reality that we live in right now. And what it fundamentally taught me is you can't treat the patient you don't know about. And where we're headed, both as a country and as the world, is we have fewer doctors and patients who are getting older and sicker, and a care paradigm that hasn't been working all that well today. And so we really have to fundamentally understand what are the things we're going to change about the way we take care of people and the way we provide that care that is going to use the technologies that are existing and emerging today to fundamentally change this care paradigm, because I want to do better than what happened for that patient. So what I'm going to talk about today is how we discover diseases, how we diagnose diseases, and the clinical impact of building the largest cardiovascular AI screening program in the country. And I want to take you on that journey and tell you where are we today and where do we think we're going to head. So the first thing is, I don't need to tell people in this room, I think machine learning is clearly going to make a significant difference. When I think of modern machine learning and deep learning, I think the places it can really make a difference are in imaging and complex language. So I think the revolution that we're experiencing right now is really based off of the fact that there are specific domains in healthcare where all we've had is human interpretation. And human interpretation is amazing, but it's also flawed. And all I have to do to prove that's true to you is tell you this picture on the right-hand side, all the gray lines are parallel to one another, even though your brain is telling you they're not. So you have this amazing pattern recognition device, but it's really good at picking up certain patterns and is flawed. And for the first time in human history, we have a very sophisticated, very complex pattern recognition device that isn't the human visual cortex. We also know that where we have this huge amount of data that's being left on the table and underutilized, there's amazing opportunities. So one of the first projects that we ever did was in honor of that patient, which was looking for valvular heart disease. So the idea here is that valvular heart disease, particularly critical valvular heart disease, is very often missed. And the reason for that is because it's diagnosed with an echocardiogram, which is an ultrasound of a patient's heart. The problem is that echoes are very expensive. It costs around $2,000 to $3,000. And so because of the cost, it's really symptom driven. And so we're waiting until patients have symptoms, which happens very late in most disease courses, before we say, oh, we should get an echocardiogram on this patient. So oftentimes we miss things, or it takes a long time for patients to get diagnosed, and then we end up in a situation where it's really quite difficult for us to take care of those patients. Now, electrocardiograms, which are these little squiggly lines that you see in the bottom left corner, are done 400 million times a year across the world. If you've watched any medical drama, it's the little squiggly lines that you see in the background. And these are cheap and ubiquitous, right? You know, many of you in the room are wearing an Apple Watch. You can do a 1-lead electrocardiogram on your watch today. Now, the problem here is I, as a cardiologist, from the day I was in medical school, was taught I can't detect valvular heart disease from an electrocardiogram. But we asked ourselves, could an AI model do exactly that? And in order to answer that question, we had to build out a lot of infrastructure. And this kind of really started our journey. So the first thing we did is we built the country's largest cardiovascular imaging database, which includes over 12 million electrocardiograms, 1.5 million echocardiograms, 8 hospitals that all function independently of one another. And all this data has been sanitized and tokenized, clinically validated, and now harmonized so that, you know, whether we're talking about electrocardiographic waveforms or echocardiographic video clips, we have access to all of this data, and we've created it into a single place and repository that's easily accessible for all the researchers who do work with this. And now we're up to around, I think, 30 or 35 principal investigators who all use this data for a variety of research and clinical trials. So we ultimately published this paper. It was one of our first landmark papers in JACC, which we showed you can detect valvular heart disease from an electrocardiogram. And at the time, this was you know, a breakthrough. But everyone in this room knows, okay, well, there's a million different ways that this model could have cheated. There's a bunch of things about machine learning we don't know. Is it really going to work prospectively? And so we had built this model that worked retrospectively, but we knew that the only thing that was really going to convince us was to go out there and prospectively test it, and then ultimately determine, is this a technology that can go out and exist in the real world? And are there patients out there who actually could be helped? So we wanted to start these clinical trials. So this is right outside of my office. There's many people here who I think are from Columbia, DBMI. They probably remember these elevator banks with horror. But right outside of the elevators, you've got all of these pieces of paper. And literally, this is still how we recruit for clinical trials in 2025, right? Hey, are you above the age of 18? No recent x-rays. I'll pay you $20 if you join our research study. This is not a particularly scalable or equitable way to conduct clinical trials. And so we said, we really have to transform the way we're going to find these patients. And turns out the patients who most need our help may not be the ones showing up on the 20th floor in the Department of Biomedical Informatics between the hours of 9 and 5. So we had to create a full real-time recruitment system. So where we're at now at New York Presbyterian, which is 8 hospitals and 190 clinics in the greater New York area, which includes Columbia, Cornell, and then Brooklyn Methodist, Queens, really one of the most ethnically and racially diverse populations in the United States, is as soon as any data is clinically generated, in particular like any cardiovascular data such as electrocardiograms, echocardiograms, cardiac catheterizations, regardless of vendor, regardless of where it's being generated, we automatically make a research copy. One copy goes into the compute environment. We can pre-process it. And then we have a host of different AI models that are run on the data. And then we're able to distribute that information in a bunch of different ways. When we first started, this was held together with rubber bands and gum. You know, we didn't wait to say, oh, we have to have a perfect Epic implementation. The very first version of this was an emailed spreadsheet that went out to clinical trial coordinators. Because we realized if we waited for 2 years to build some perfect version of this, we were going to miss out on all of the learning of, are there actually patients out there who need our help? And what are the things we don't know today? Over time, we've gotten much more sophisticated. We now have, I think, our 10th, 11th, and 12th clinical trial running on this platform. We have Epic integration, we have direct communications with physicians, direct communications with clinical trial coordinators, all those sorts of things. But the point that I would take away from this is just go out there and build it. Find the problem that matters and build a version 1.0 of it. It's okay if it's clunky, it's okay if it's imperfect. If you're answering a meaningful problem, the sooner you know that, the better. This is the most important slide of my talk today. this is a great paper written by Bob Wachter, a mentor of mine. He's the chair of medicine at UCSF, and then Eric Brynjolfsson. He was at MIT for a number of years. Now he's at Stanford. He's an economist. Eric has spent his career studying this thing called the IT paradox. So there'll be some industry, and it's due for a technological revolution. And they're updating the software, they're doing all this, they're making these huge investments in technology. And then everyone thinks that this is gonna massively boost productivity in that industry. And then sometimes it does, and sometimes it doesn't. And Eric has spent his career studying why is that the case. And he's come up with this fundamental idea called the two-key hypothesis, which is there are two keys that are necessary in order to unlock massive productivity gains in an industry when new technology comes about. The first is that this new technology must be sufficiently better than what we do today. And I can confidently say that in specific domains, AI is sufficiently better than what we do in healthcare today. It is the second key that is the stumbling block. We must be willing to reimagine the work itself. We must be willing to reimagine what it means to be a doctor, a nurse, a healthcare administrator. And if we think about software engineering, what it means to be a software engineer 20 years ago, 10 years ago versus now has massively changed. And because of that, we do see these massive productivity gains. But then there are industries where that doesn't happen. And this impacts you and me. The industries where we have not seen these significant productivity gains with IT are healthcare, education, and housing. And if you think about what the average American spends more than 50% of their paycheck on today, it's healthcare, education, and housing. If we don't solve this problem, it becomes a crisis for the country. This is really important. And the challenge here is it's very uncomfortable to reimagine what it means to be a physician. And so the most uncomfortable part of my job, and the challenge I have for myself, is reimagining what it means to be a cardiologist. I practice cardiology in a way that makes myself and some of my colleagues feel uncomfortable because my job is to test the boundaries and say, how can we create AI technologies that allow us to take better care of patients, screen for them in an entirely new way, and measure the impact of it. And if we don't do that, the problem is only going to get worse. So this is the question I became obsessed with. Of all the people with the cheap test, who needs the expensive test? How do we build a fundamental screening technology for the most common cause of death in the world? And what this led to was the creation of this AI model called EchoNext. And it's relatively straightforward. It looks at an electrocardiographic waveform, and it tells us if any form of structural heart disease is detected. So basically, these are all the things we diagnose with an echocardiogram. And the question was, could we build a single model that could actually provide us meaningful insights about each and every one of these questions? We'd seen a lot of single decision models. We'd seen models that were trying to work towards this. But what we wanted to do is say, can we actually build a unified model? And then can we go out there and prospectively test it? And this ended up being our landmark paper in Nature this year. So the first thing we did is we validated at 11 hospitals, 4 health systems in 2 countries. We saw excellent performance. We saw performance was consistent across these institutions, and there's no variation for race, ethnicity, or gender. We then followed 85,000 patients who were getting new electrocardiograms and had no prior echocardiogram. So these are all these patients who we think are potentially at risk for having undiagnosed structural heart disease. And we followed them all for a year. So we run the AI model at the moment they get the EKG, and then we follow them for the course of the year. So we saw 2 really interesting things. So the first is 9% of the patients are predicted as high risk. About half of those patients go on to get echocardiograms, and the positive predictive value was around 74%. So the positive predictive value was already twice as high as what we normally see for all first-time echoes in our health system. But the real smoking gun evidence was half of the patients that the AI model thought were high risk were not going on to get echocardiograms. So we were missing potentially up to half of all new structural heart disease diagnoses that were showing up in our health system. This was shocking to us. We then ran a prospective clinical trial. We brought in 100 of these patients, and we saw very good performance in the model, and we found that indeed the model performed equally well in these patients who had been undiagnosed and were not previously planned to undergo echocardiogram. And then lastly, we had 13 cardiologists from around the country read 3,000 EKGs with and without the AI model. And we just asked them a yes/no question. Do you think this patient has structural heart disease? Now, again, this is something we're taught in med school and cardiology fellowship is not possible. You can't detect heart failure or valve disease from an electrocardiogram. So we didn't particularly think I as a cardiologist did not think I would do particularly well on this, nor did any of the other cardiologists. But we said, okay, you're gonna do this and we'll see how you do, and then we'll see how you do with the AI. So the cardiologists alone, 64%. With AI, 68%. AI alone, 78%. So I think pretty much everyone in this room is not a cardiologist. You would all do better than I would because you would just listen to what AI told you. What was really fascinating here, right, is this is a yes/no question, so random chance is 50%. So the cardiologists are as far away from random chance as they are from the AI model. So we're now starting to see these AI models exceed human expert performance in specific use cases. Okay, maybe it's just, look at this, Shreyas, you're in the audience, and I still have your picture up here on the slide. Maybe it's just the cardiologists. The radiologists are, slightly less arrogant than cardiologists are. So let's see how they do. So we built an AI model that was supposed to look at chest X-rays, and here, a very similar paradigm, which is we diagnose heart failure once it's symptomatic, but before that, the heart thickens and dilates. And so we asked ourselves, could we detect that thickening and dilation from a chest X-ray? And so we built this model, we validated it at Stanford, and then we asked 15 radiologists to go head-to-head against the AI model. And we found that the AI model outperformed all 15 of the radiologists. And so, again, we were seeing the same concept here, which is these AI models have the ability to outperform clinicians at specific tasks that we think are meaningful. So, okay, great. We've detected these patients, we've gotten them to their diagnosis, right? Everything is hunky-dory now, the medical system will work magically, and we'll have no more problems, right? Well, I had a patient come to me, and I said, you need an echocardiogram. And they said, Doc, don't worry, I just got one done like 4 weeks ago at another hospital. I'll bring you the report. And this is the report that they brought me. Now, I know no one in here probably reads echocardiograms for a living, but I posted this on Twitter, and Mark Tuttle is an interventional cardiologist in Virginia. I think he put it perfectly. There is a huge variance in the quality of the interpretations of these of these reports. And we have this same issue, right? We have human interpretation, and the quality of that human interpretation is highly variable. So what do we do about that? Well, we asked ourselves, could AI help? And so we built an AI model that looked at echocardiogram video clips. And we gave it the single hardest task that we as cardiologists do, which is the assessment of valvular heart disease, and specifically valvular regurgitation. So when the valves are leaky, we call that regurgitation. And this is inherently a very technically challenging task for a number of different reasons. You have to get the ultrasound probe directly in line with the jet, and it turns out everyone's heart is shaped a little different and is in their chest a little differently. And by the way, the thing is beating, and so it's constantly moving. So you're basically wrestling to try and get this perfect picture. It's a very challenging thing, and the interpretation of those pictures is similarly really challenging. So we asked ourselves, could an AI model actually do this? And so we built this model at Columbia, we validated it at Cornell. We saw 96% agreement with academic labs, which are the kind of highest quality standard. And then the 4% of the time that it disagreed, half of those, the AI model was right, and the original interpretation was incorrect. And so we said, okay, this is actually quite surprising. And published this work in Circulation, European Heart Journal. And we said, was there something we can do about this? And we said, I think there really is. And we said, let's put this question to the test. What that really led to, though, was this understanding of how do we find the needle in the haystack? And how do we get patients to accurate diagnoses? And that ultimately led us to another disease, which was cardiac amyloidosis. So this is a cause of heart failure that's often missed. And it's something we care a lot about at Columbia because we invented the first non-invasive way to scan for this disease. We wrote the first New England Journal paper of a medication that actually helps these patients because normal heart failure medications don't work for them. And we think there are a number of patients out there who remain undiagnosed with the disease. In fact, we think more than half of the patients with the disease remain undiagnosed today. So we built an AI model. I think sitting right next to Shreyas is Tony. I had no idea either of them were going to be here. Tony built this model when I was working with him. I was a postdoc. He was a PhD student. He was 10 times smarter than me. But we built this AI model which looks at ECGs and echocardiograms to try and find undiagnosed cardiac amyloidosis. And again, hooray, it works in a retrospective data set. But is this really going to work prospectively? Is this going to help people? And while we were doing this, Matt, one of my mentors, Matt Maurer, he's a world-leading expert in this disease. He said, listen, I know that this disease has a preponderance in Black and Caribbean Hispanic patients, but my clinic is filled with white people from upstate New York and Jersey. What's going on? I was like, well, that's very interesting. Let me look at that for you. And we saw something that was very interesting. So we looked at who are the patients who just show up in our health system. And so if you look at who's showing up, about 46% are white, 17% Black, 38% Hispanic. You look at who gets a cheap test like an electrocardiogram, very similar. You look at who gets the slightly more expensive test, the echocardiogram, it comes about 50% white. And then you look at who's getting the pyrophosphate scan, which is the way we diagnose cardiac amyloidosis, and it jumps to 80% white. So the upshot here was that the people we were sending for advanced diagnostic testing were twice as white as the general population we cared for. And I think this was unintentional, but something that we wanted to fix. And so we asked our AI model, well, who do you think is undiagnosed for the disease amongst a high-risk population that hasn't gone for testing? And lo and behold, if we look at our current PYP referrals, it was 80% white. We looked at who the AI model thought was undiagnosed with the disease. It was 54% white, 16% Black, 31% Hispanic. And so people talk about the ways that AI can be biased, and it absolutely can. And I think particularly with large language models and all these things that we've created in the last couple of years, there's very real risks of these things going awry. But we can't forget things are imperfect today. We have to do better than the current standard. We have to measure what we are doing. But there is huge opportunity to use these technologies to correct systemic issues that exist today. And the nice thing about being someone who builds these technologies and is also a physician is I get to kind of call both sides out on one another and say, guys, clinical care today is far from perfect. So what are we aiming for? What is the standard here? So now I want to talk a little bit about the impact. I think a lot of people do research in the room. I think a lot of people have faced innumerable challenges trying to get that research out into the real world. And you're probably used to people telling you no. And you're probably used to administrators saying you can't have access to this data, or people saying, I don't think this can work, and all of these sorts of challenges. But I want you to take this part from the talk and say, there is a way to find clinically meaningful problems that we can make a meaningful difference in and show people that there is huge clinical impact waiting on the other side of this. It is hard, it is painful, and there's probably easier things you can do for recognition. But if what you care about and the reason you're in this room is about taking the most emerging technology and actually showing the clinical impact, I'm here to say it's possible. And I'm here to taunt you all and the people back at your institutions and say, well, hey, New York Presbyterian's doing it, Columbia's doing it, why aren't we doing it? We don't want to fall behind them. So I want to start with the cardiac amyloidosis work. So we conducted the cardiac amyloidosis discovery trial. We just presented these results 3 weeks ago as a late-breaking clinical trial at the American Heart Association. This was a single-arm, multi-site trial. We looked at all the patients that the model flagged as being at high risk, who are above the age of 50, who had the kind of criteria necessary to be considered appropriate for diagnosis as well as treatment. So really the goal here was to say, were there patients who were otherwise being missed in our health system who had undiagnosed and treatable disease? And so our primary outcome was cardiac amyloid diagnoses. And we were going to compare it to two things. We were going to compare it to a historical control, which was the number of patients we diagnosed the year prior and the rate of positivity in general care, as well as contemporary controls to kind of rule out any possibility that we had just gotten better at understanding this disease over time, and thus that's why there was any significant difference. So the first thing I want to point out is we had about 1,500 patients who were flagged as positive by the AI model. A number of these patients we had to remove because they either had prior diagnosis or testing for amyloidosis, dementia or nursing home residency where they wouldn't be good candidates, or cancer or other life-limiting diseases. We were left with 256 patients we wanted to put in the scanner. Ultimately, only 50 of those patients got into the scanner. And what were the reasons that these other 206 patients were excluded? Physicians just never responded to multiple forms of outreach. And in our institution, we're not allowed to directly reach out to patients unless we have their physician's consent. Physician declined. Patients declined. They said, wait, this is based off of AI, or I don't want to be a guinea pig, or what do you mean this includes radiation? Real and understandable risks where we were trying to help patients navigate through this. And then a number of times we were unable to reach the patient, or they were pending recruitment for the secondary portion of the trial. So there are very real challenges in, one, being able to do direct outreach to patients, two, convincing doctors that this is worth their time, and three, convincing patients it's worth their time. So now I want to show you the results. So first, the historical and contemporary controls. So when I, as a cardiologist, refer a patient for cardiac amyloidosis testing, on average, about 15 to 17% of the time, those patients are positive. So amongst the patients who are otherwise not being considered for cardiac amyloidosis testing and were recruited by the AI model, 48% were positive. So 3 times the positive predictive value of cardiologists. This also led to a 18.6% increase in year 1 in cardiac amyloid diagnoses in our health system. And we're estimating it'll probably be of a 35 to 40% increase in cardiac amyloid diagnoses in one of the world's busiest centers in year 2. Of those patients, 88% were started on treatment within 3 months. And interestingly enough, when we looked at when the AI model first flagged the patients as positive and when they got into the scanner, it would have diagnosed patients 345 days sooner prior to scanning. So this was a profound impact. And when we presented this at AHA, we had never really seen results like this before. So for this diagnosis, we saw an immense impact in both the rate of positivity and the number of patients diagnosed with the technology. So earlier on, I had talked about Echo Next, which was our technology of all the patients with an ECG and don't have an echo, who needs an echocardiogram. This has led us to initiate the Cactus trial, which is going to be starting in January. This is a NIH-sponsored $5 million clinical trial, and it's going to take every electrocardiogram that happens in our emergency departments. So all patients and clinicians have full waiver of informed consent. So every ECG in the emergency department gets evaluated. And then if the patient has a high risk AI score and no prior echocardiogram, first we notify the physician taking care of the patient. And then when they ignore the alert, like all clinicians, myself included, do, it then comes to our care coordination team. And we make a determination should the patient get an echo. The first thing that you probably all notice is this is super complicated. And we said, oh my God, we have no idea how we're going to actually pull this trial off. So we spent a year doing the Cactus pilot, and we just finished the Cactus pilot. And we presented these results at TCT 5 weeks ago. So the first thing is we said, we have no idea how to order echocardiograms at 8 different hospitals. I have no idea how to do outreach to these patients. There was a bunch of questions we didn't have the answer to, but we knew this was the important thing to figure out. So we spent a year running this pilot trial. And basically every EKG that was flagged as high risk came to our team. We made a determination if it was appropriate to get an echo, and then we ordered an echocardiogram on the patient. And we covered the cost of all these echocardiograms to ensure there was no financial toxicity. So I'll keep it really simple here, but 3,500 patients with high-risk EKGs were assessed. 2,300 were excluded due to echo within the past 2 years, or prior diagnosis, or quality of life issues. We then called 1,152 patients. 317 had underwent echo due to AI intervention, and another 87 underwent echo due to routine clinical care. And then amongst AI interventions, half were positive for new structural heart disease diagnosis, and half of those had a class 1 or 2A change in clinical management. So I'm going to simplify this and give you context. I, as a singular cardiologist, ordered more echoes than any single provider in my entire health system over a span of 6 to 9 months. I instantaneously had the highest rate of positivity for any provider at New York Presbyterian. I became the equivalent of the 5 highest RVU generating cardiologists in the entire system as far as number of new diagnoses and referrals. I never met any of the patients before ordering the echo. But this also led to a number of findings. The first is opportunistic screening is really hard, and the yield can drop very quickly due to all the resistance to patient outreach and all the other challenges that usual clinical care has. Getting patients plugged into care after diagnosis is just as difficult as getting them to diagnosis and has to be a part of the care plan. But despite this, there was a huge burden of undiagnosed disease that left us confident for the initiation of this randomized control trial that we're going to be running over the next 12 months. And it led to a number of AI world firsts. So that disease that the patient died from at the beginning of my story, we had the world's first case of AI analysis of EKG leading to a detection of severe aortic stenosis in a patient, and that led to the aortic valve replacement that other patient needed. We had the world's first case of mitral valve replacement due to AI, and then we just found out about this 3 weeks ago. The world's first case of AI-detected heart failure leading to a heart transplant in a 45-year-old man who gets to be at home with his wife and kid today because of this technology. So we have a long way to go, but what I would say is that AI-based opportunistic screening is going to fundamentally change the way medicine is practiced. But we have to be willing to reimagine the work. And I think the development and validation of these technologies is happening today. The question is only how quickly and how willing are we as a community to push it forward. Thank you so much.
We have time for 1 or 2 questions. Yes.
Thank you so much for that talk. My question is about screening in the ED setting. I know at Boston Children's Hospital, we're doing a lot more point-of-care ultrasounds, and I'm curious what you think about the potential for that imaging. You mentioned how hard it is to get a good image with echoes, and with this in this setting, you know, there's so much more noise and the image quality is so much lower, but I'm curious where it sits compared to an ECG and an echo in terms of the diagnostic value you might think it has with AI.
There's definitely a place for it. So, you know, point of care ultrasound is basically like there are these cheaper ultrasound probes. They're more portable. You can use it. We actually just finished this trial called Previews, $10 million trial. It was really interesting where we recruited 3,000 Americans aged 65 to 85 at pharmacies, and we did an EKG and an echo at their home. Dave Cohen just presented those things. And so now we're doing the AI analysis of that data. And the reason this data is so valuable is because now we can actually look at the natural prevalence of disease. And you need to know the natural prevalence to start answering fundamental questions like, should we screen all older Americans with AI to find undiagnosed valvular structural heart disease? So there's this huge opportunity. The flip side is, I think with point of care, there's like 2 challenges. So the first is you're gonna have even more image quality and variability issues. And at the end of the day, these AI models, like they're only as good as the data that you feed into them, right? Now, there are a lot of companies that are working on saying, like, can we take someone who's less skilled and improve the quality of acquisition, right? You know, like a sonographer is really hard to find and they're really expensive. And so could we, you know, take someone who has less skill and kind of upskill them using AI? You know, Butterfly Health, Caption Health, there's a number of companies working on that. I think we're still a decent way away from it. And so I think everything helps, but it's like, all right, how do we get patients to the echocardiogram and how do we make like the traditional echocardiographic yield better? I do think there's also huge opportunities in the developing world where you have even more limitations as to who can get to the echocardiogram to use these sorts of technologies. So it all helps. I would say, like, you know, you want to start from a place where in the ideal circumstances, it works, right? So, okay, they had an EKG, they have an echo. Prove that that works, and then you have more latitude to say, okay, well, we know this already works, we know this paradigm works, now can we make it easier, cheaper to get the echocardiogram?
Great, we have one more question.
Thanks for a great talk. I'm wondering about that set of patients. It was like 70 patients who had declined to get screened. I'm wondering if you know anything about like the demographic makeup of those patients compared to those who did agree for intervention.
Yeah, so all the patients are old because we're talking about cardiac amyloidosis, which is the disease of the elderly. I will tell you, so like, you know, I practice in Washington Heights, which is like Little Dominicana. You know, my cardiac Spanish is like top tier. The rest of my Spanish is pretty garbage. But there was no doubt that patients who declined were more likely to be from ethnic and racial minorities. One thing we were super proud of is we had a 20% increase in new diagnosis in racial and ethnic minorities in comparison. And like I talk about Francisco, one of our trial coordinators, he's an MD from the Dominican Republic. He had to talk with 7 children for one family member, and he had to go and convince every single kid that mom should go and get this scan. And she ended up getting the scan, and she ended up getting diagnosed, and she ended up getting treated. And by the way, when you put these patients on treatment, they live 4 years longer than not being on treatment. Like this is genuine, life-saving treatment that we're talking about. So there's always going to be a gap in the understanding, and you have to do all of the classic things, right? Which is you have to have study coordinators and people who are able to kind of bridge that gap from a cultural perspective or a socioeconomic perspective. But at the end of the day, I think there's real commitment from health systems and other groups to try and bridge that divide. But what do they need? They need a list. They have to take the chaos of everything that's happening in a health system and convert it into a list of, if we miss the mark on 10 people today, or there's 10 people who need a little bit extra TLC in order to get across that finish line to diagnosis and treatment, who are those patients, right? So I think there's actually a lot of teams out there that want to do this work, but they need to start with a list of like, who are the people who are actionable, or where is it where an extra 15 or 20 minutes with this patient may make the difference between diagnosis or not. And I think that's the core lesson we learned from this whole process.
Great. Thank you so much once again for the great talk.
Thank you all.
We will now transition to our spotlight talks. We'd like to welcome the first speaker up to the stage. We'll have 4 talks today, each 5 minutes in length. We'll save questions until the poster session that will immediately follow the spotlight talks.
All right. Hey, everyone. My name is Akshay Purichuri, and I'm going to be presenting What's Up, Doc, our paper, which is about analyzing how users seek health information in large-scale conversational data sets. So one thing I think everyone in this room is aware of is a lot of different people are seeking health information from LLMs today. So, this is like up to 31% of US adults are now turning to generative AI for a variety of different, healthcare-related requests. In some cases, it can be something as simple as understanding what's happening to them, for example, with a skin rash. It could be something very specific about something their clinician might have said to them. And then despite this surge of use, most of the sort of current data sets out there kind of evaluating this kind of conversations in the wild are sort of single-turn data sets that are generated with specific questions, or these kind of like multi-choice sort of sets of questions related to some health information seeking task. So what this work tries to address is this more sort of open-ended, sort of ambiguous nature of sort of lay, non-expert users seeking health information from LLMs in some way. And this is something that's captured in a lot of real-world data sets. So, there's these sort of collections of conversations around countless different sort of unconstrained topics in these data sets, such as LMSys or wall chat. So these are like, millions, or each data set is like 1 million conversations, and they can have some number of turns. It could be single turn, it could be 5 turns, it could be whatever the distribution of turns is. And some of these questions are very, lay user, unconstrained questions, right? The first message they have might have nothing to do with health, for example. It could be, who are you, who created you, for example. And then they might start diving into something that actually constitutes the health information. And they might also make mistakes, right? They might have messages that don't make any sense. For example, you can't be 20 months pregnant, for example. And there's kind of generally this sort of theme of messy conversations that are hard to tease out details from. So what we tried to do in order to study this a bit better is we came up with this, we worked with some clinicians at Duke University and came up with this sort of healthcare taxonomy where we try and categorize each of these user messages inside these conversations that were scraped from these large public data sets. And then we went through this whole sort of pipeline where we try and curate and annotate that data set. So what we mean by curate is we only want conversations that have something to do with healthcare information seeking, so what we care about in this case. And we want to annotate them with respect to these conversation level kind of category annotations, as well as this message level sort of annotation of what different subcategory or taxonomy codes could be associated with this. And that ultimately is what generates this health chat 11K data set, where we also then worked on sort of some small scale sort of empirical analyses in terms of user interactions. When might they end a conversation? What kind of how might they induce sycophancy in the model, for example? Different sorts of behaviors that are undesirable in most cases when seeking health information. And then that annotation or that creation and annotation process yielded a pretty useful data set in terms of size. So there's 11K conversations, many of them, over a little under half of them actually are multi-turn conversations, so they have more than one turn. There's numerous conversations that also span, 20 plus turns or something extreme like that, for example. And there's a nice distribution of, specialties that are covered in this data set. So some of it might be about general health information, some of it might be more about mental health, for example. Some of it may be very specific to things like oncology or nephrology. And you also have these other distributions of codes. I just talked about specialties, but you also have these other distributions where some of this might be in terms of like, what is the distribution of context provision someone provides? So that first blue column here. Or, the majority sort of behavior we notice is, people are just seeking information consistently, right? So they already have something they want to ask about, and they might just seek information about different treatments, for example. And that yielded these case studies. Some of these have to do with seeking seeking diagnosis with partial information, or an example of incomplete context where someone might omit some information that's really important for the model to give them a correct answer about. Some of it's more emotional interactions where someone might get angry at the model and cut off the conversation, or they might be very happy with the model or might request clarification from it. So there's kind of like different interaction management case studies, which is more information in the paper about this. And then the other very important thing that many people are curious about, of course, is this notion of inducing model sycophancy, or we frame it as leading question seeking treatment, where in order to seek treatment for some ailment, someone might initially provide a medication they care about, for example, or they really wanted an answer for. And I went over that. So in summary, this health chat work kind of was driven by this clinician-driven taxonomy for how users interact with LLMs when seeking healthcare information. And the sort of artifact of this work was that curated and annotated data set, which we think might be useful for the community in a few different ways. And then in the paper, there's also some more information about case studies, which might be interesting to some of you in terms of user behaviors, such as inducing model sycophancy. And this could lead to some interesting things, such as specialty-specific conversational AI, better understanding how people interact with these models and kind of patterns of behavior or trajectories of behavior, as well as maybe using some of the case studies to create new benchmarks and tools of interest. And that's all I have. And there's a poster session with more details and paper links if anyone is curious to scan those. Thank you.
Hello everyone, my name is Manuel Berger and I'm from the Biomedical Informatics Group at ETH Zurich with Professor Gunnar Retsch. And today I'm going to talk about, so I'm excited to talk about our foundation model for intensive care, where we aim towards unlocking generalization across tasks and domains at scale. So the domain here is intensive care, where the most severely ill patients are monitored very closely. And we continuously collect a lot of data. It's probably the part in the hospital where we have the densest amount of data over time from each patient. Today, I just brought a sketch for you to essentially highlight the three core data types that we encounter here. So we have a collection of continuous measurements from different vital sensors, so blood pressure, heart rate, oxygen saturation, and so on. Another core type are sparse measurements. These are mostly lab tests that are measured irregularly as needed and ordered by the physicians. And then we have a large collection of different types of sparse interventions. These can be different types of treatments, in bolus form, injections, but also treatment administration via infusion pumps in intensive care, ventilation devices, continuous renal replacement therapy, and so on. So, and in the setting, usually downstream, what we're interested in is to perform early event prediction. So we want to detect deterioration events in the patients. And if you're looking at machine learning, what we do is we process the time series data, and we want to use machine learning models to perform this early event prediction. However, what often is found in the literature so far is essentially that while these models can have strong performances in their training hospital, they struggle when deployed outside their training support in a different hospital across the world. To better study this phenomena and to work towards more robust models, we started collecting data that is available for academic research from Europe, Asia, and the US. And we created a large collection of data sets, and we harmonized it. And so we also found that in this setting where we want to really draw from the value of external data, it is essential and crucial to spend time harmonizing the data to really see the benefit of it in the local set, in a held out target hospital. And if you visualize that data collection, essentially we can nicely visualize that challenge. So the data then, the largest axis of variation in that data essentially clusters the data by hospitals by source origin and not by patient variation. And so I might no longer have to convince you so hard that it's going to be hard to transfer a predictor trained on one of these clusters to another cluster. In the foundation model idea, we are going to hold out one of these data sets, and we try to train one single model, compressing the data and the information in all of the other data sets into this unified model. In our case, we developed iCare-FM, our intensive care foundation model, and it draws and is inspired by an objective that draws from survival analysis and time series forecasting. So we learn time to event distributions where events are defined as threshold crossings across all the channels. So iCare-FM is then in the end capable of predicting time to event for any variable, any threshold, any horizon. And this gives us the predictive power to perform zero-shot predictions for different types of early event prediction downstream tasks, where already now we see that given the data that we have, we can essentially we can reasonably outperform clinical scores, and we believe so iCare-FM could serve as a drop-in replacement for clinical scores. The evaluation here does not use any local training data and does not use any specifics about the downstream applied task. And if we then use the model as an initialization point to further adapt and tune to the local setting, we see that it essentially has the worth of having tens of thousands of local patients available for a single model, for a local model. We can further scale the training data set, and we observe a scaling law where essentially external data, if you have 2 times more local data, we might as well collect 5 times more external data, and we see that we improve in performance transferring to new data sets when scaling the pre-training data set. And I would like to thank all my co-authors, and especially also you can meet Fedor here, top row in the middle, who has another poster here, poster 50. You can also meet him and talk about this. And also all the other collaborators on this project and other ICU-related projects that I worked on. Yeah, thank you.
Hi, everyone. My name is Xiaobing Shen. I'm from CMU, and then today I'm presenting our work that is about interpretable computing risks modeling. This is a joint work with my advisor, George Chen. To begin with, let's first define the problem. We focus on computing risks in survival analysis. As a running example, imagine there is some patient with some disease history. Several things could happen to them. First of all, they might experience some cardiovascular disease and die as a result, or they may also die from other reasons. And the key challenge here is we want to know which critical event will happen the earliest and when. To answer this, people have been trying to estimate what is called cumulative incidence function, or CIF, which is denoted by risk over time, and you can think of it as a probability of certain event have happened by some future horizon t. Different methods have been developed, like classic methods, including Allen-Johansen estimator or fine-grained models. Those are models that are highly interpretable and then trusted by doctors, but then they are usually too rigid to model complex patient data. On the other hand, modern methods like DeepHeat, they have got great performance, but they are usually black box or only provide post hoc explanation. So our solution is called Deep Kernel Allen-Johansen Estimator, or DKAJ. We try to bridge this gap by making the classic trusted Allen-Johansen estimator to be flexible and deep. So here's how DKAJ works. There's a raw feature space and an embedding space with clusters identified on it. And then for each cluster, we can estimate the CIF curves using Allen-Johansen estimator for them. And then now giving a new patient, instead of predicting their risk directly, we're going to map it to the embedding space using some encoder. And then the network will also identify who are the clusters this new patient is similar to. For example, here our new patient lands very close to the red cluster, followed by the blue, green, purple, and yellow ones. And then the final prediction is easy. We just take a weighted average of the Allen-Johansen estimator from those nearby clusters. This makes the prediction to be transparent, as we can always trace back to see what are the certain subgroups that contribute to my prediction. As a special case here, if the shaded bar area only contains one cluster, then the prediction would just fall back to the plain Allen-Johansen estimator restricted to the training data in that one cluster. Such architecture allows for a powerful interpretation. We apply this to a Framingham study dataset with two critical events: CVD death, or people who died from cardiovascular disease, versus non-CVD death. Meaning here, the model will automatically identify different clusters during training. So let's here focus on the 5 largest ones with the most training patients assigned to them. Here, different columns represent a different cluster, and then different rows represent different raw features. The intensity value on the heat map denote what is a fraction of people in a cluster having a specific raw feature values. For example, we got people who has hypertension history, heart disease history, their blood pressure, and how frequent they smoke, and so on. For different clusters identified, we can estimate the CIFs, or the risk over time within them. For example, for the first cluster here, we have patients who are having a history of heart disease, and then we can see indeed this patient are the people who has a very high possibility of experiencing CVD death very early on. Versus for the second cluster, the green cluster here, those are the patients who don't really have heart disease, but then as a result, they have much delayed risk of experiencing CVD death, but a much higher rate of experiencing non-CVD death. And we can do this for other clusters as well. Because the method is based on clustering, a doctor can always go back and validate to make sure those subgroupings make clinical sense. We apply our method to several data set, and then the key message here is that no single method is performing the best across all data set, and our proposed method, DKAJ, while being interpretable, is highly competitive with various recently proposed baselines. So to summarize, we propose DKAJ. It is a new competing risk model that is both interpretable as well as highly performing. Come to our poster to chat more about it, and then here is a funding resource for our study. Thank you all.
Hi, my name is Divya, and I'm a postdoc at Cornell Tech, and I'm excited to share more about our work on using machine learning to study patterns of diagnosis. Recorded diagnoses play a central role in patient care, public health, and machine learning. So we should care about the extent to which diagnoses are incomplete and seek to correct them. This leads us to the central question in our work, which is to ask how accurate are recorded diagnoses and how can we measure this accuracy. So this is not an easy question to answer, so let's consider atrial fibrillation, which is an irregular heart rhythm. So on the left, I'm showing you an ECG or an electrocardiogram, a measure of electrical activity in the heart, and we'll use Y to represent the presence of the disease and S to represent the presence of diagnosis. So here we have a patient with the disease correctly diagnosed for it. Ideally, we would observe a continuous ECG for all patients. This would give us perfect information about Y and let us assess the quality of S. Studies on diagnostic quality often do something like this, but of course, this is very expensive and hard to scale to large samples. Instead, what we have access to is sporadic ECGs from different patients. We observe patients only at certain time points and only when an ECG is ordered. As a result of multiple mechanisms, diagnoses can be hidden. And I call these diagnoses hidden because they're hidden from the perspective of an algorithm or a clinician examining the problem list. Our insight is to frame this as a prediction problem and use machine learning to mimic continual monitoring. So we can use machine learning to predict from an initial physiological signal a proxy for Y and use that proxy to study the quality of S. So this builds on wonderful work that's been done in the past by many people in this room on how we can predict multiple outcomes from these physiological signals. And our work advances this work by using it to study clinical decision-making. Okay, so our approach has two steps. The first is to estimate a patient's risk of a disease R from their ECG X. And the second is to use that estimate of risk to study patterns of diagnosis between different groups. So how do we operationalize this first step? What we do is take advantage of the fact that for atrial fibrillation, it's very easy to detect. So if we have a longitudinal database of ECGs, we have a natural source of supervision in later ECGs. So we frame our prediction problem as training a network to predict, given one normal ECG, the probability that a patient experiences an AF ECG within 90 days. And we're able to do this using a data set of 500,000 patients and 2 million ECGs collected in the MGH and Brigham system between 2016 and 2019. To take care of the second step, we use a linear probability model to measure differences in diagnosis rates that are unexplained by differences in risk. This approach has several advantages over prior work, including that it controls for different distributions of risk between patient groups. It admits a large and diverse set of patients, anyone with an ECG. And finally, it models group-specific differences in diagnosis rates. Okay, so our model from step one is quite accurate. It's able to predict the outcome that we train it to predict quite well. It achieves an AUC of about 0.9 across demographic groups and is quite well calibrated. The headline result in our work is that we find that differences in risk do not explain differences in diagnosis. So the x-axis here is different quintiles of our estimated risk, and on the y-axis, I'm plotting diagnosis rate. And across each quintile, we see that white patients are diagnosed at far higher rates than racial minorities. Adding in a richer set of controls, including measures of health access, we find that racial minorities are 18 to 32% less likely to receive a diagnosis conditional on risk. And this is despite the fact that they are as likely to experience AF complications conditional on risk. The paper has much more, including sensitivity analyses across different specifications of the risk score, the data set, definitions of diagnosis, and different demographic groups. But I'll quickly summarize. The proposed method takes advantage of rich physiological signals to audit human decision-making. Using the proposed method, our study of AF provides estimates of hidden diagnosis rates among underserved patient groups on a sample that's 40 times larger than prior studies. And finally, our findings highlight systematic diagnostic inequities and provide a scalable approach for uncovering them. I'm happy to chat more at poster 8. Thanks.
Welcome to day 2. Thank you to our sponsors again. Thank you to our diamond sponsor, our gold sponsors, and our silver sponsors. And just a recap from yesterday. Yesterday we had Matthew McDermott give us a tutorial, and then we had 3 keynote speakers from Paul Liang, Serena Yeung, and Pierre Elias. And then we also had a perspective from Gabe and a panel on building health AI products. So today we will start off with a fireside career chat and then have 2 keynote speakers, 2 perspectives, and 1 panel. And just a reminder of logistics, we have the ML4H Code of Conduct, which is available on our website. And if you're presenting your poster today, please have it up by 3 p.m.
All right. So the first item of today will be a career fireside chat. Tara Tagavi is a Senior Director of AI at Oracle Health, working on clinical data and modernization of EHRs. Stephen Fo is a Senior Research Scientist at Google Research on the Context Research team. Irene Chen is an Assistant Professor at UC Berkeley and UCSF. And the moderator will be our own Sarah Jabbour, PhD student at the University of Michigan and Program Chair of ML4H. Let's welcome the panelists to the stage.
All right, I think we're still waiting on Tara, but we can go ahead and get started. Welcome everyone to our Fireside Career Chat. I think this is the first time we've done this at ML4H. The goal of this panel is to give early career health AI researchers a look at how careers evolve in academia and industry, highlighting the decisions, trade-offs, and turning points that shape careers. So to start, kind of an overview, before we get into a lot of advice, we'd love to hear the trajectory of how you got into your current position and what kept you here.
All right. Hi, everyone. I'm Irene. I'll go ahead and kick us off. I did not think that I would go to grad school. After my undergrad, I studied math. I thought I would work in industry. I joined a very nice tech company where they had 3 meals a day. It was a very cushy time. And then after about a year, I realized I just couldn't keep doing this. It was very nice. It was very fun. It was almost like college with more money. And I remember thinking, I got promoted actually. I got a decent raise, and I remember thinking, oh my gosh, is this gonna be my life, getting promoted and sort of chasing this ladder, and I don't even want what's at the very top of the ladder. And so then I did a lot of soul searching. I talked to a lot of people, and the thing that stuck out to me was looking at different people's lives and noticing in myself if I felt jealous of them. Around that time, a friend was moving into his PhD dorm at Stanford, and he was like unpacking his textbooks, and he was showing me his tiny bedroom with a twin-sized bed, and I thought, God, I'm so jealous. I wish I could be him instead of sort of my job right now. And that sort of kicked off a whole thing of like, okay, if I were to do a PhD, what do I do? What is sort of the next step? I am such a planner. I love making plans. I think I'm good at this particular career path because so much of it is planned out for you. But at that moment, I remember thinking like, oh, I don't know if I'm gonna get in anywhere, what will I study, et cetera. And so maybe what has been helpful for me has been just taking it one step at a time. I did my PhD at MIT. I thought I would work in statistical machine learning, maybe in the more statistical side, not at all applied. And then I found an advisor who's working on healthcare. And then that created another twist and turn. It was the right time, it was the right situation, it was the right people. And I think, yada, yada, here I am, assistant professor. So I think hopefully some of that resonates with people, or is at least sort of planting a seed of what kinds of people you find interesting, admirable, or that you're even a little envious of.
Yeah, so I think my trajectory is also kind of circuitous. I mean, as an undergrad, I was doing biomedical engineering, and I was interested in things related to like devices and medical devices, and thinking about different types of like biological therapies and things like that. And then, towards the end of my undergrad, I started looking for jobs, and I realized that you basically can't get a job as an undergrad with a BME degree. And so, I'd already been doing some research at that time, and so, I started thinking about PhDs, and ended up at Stanford in the biomedical informatics PhD. And there I even came into that thinking that I would still sort of work in sort of this like devices space, maybe doing things like arrhythmia detection and stuff like that. But over time I started working on predictive models of electronic health record data. I eventually started working on issues related to algorithmic fairness and robustness. Over time also took sort of a more like interdisciplinary, like social science oriented lens, and that led to sort of expansion of what I was considering in research. But then also really importantly, I did an internship in industry with Google, sort of midway through my PhD, and that sort of eventually led to me taking on a full-time research scientist position there, where I've been now for the last 4 years. And I'm also, I guess, not really sort of like formally a part of like the health AI group. So I'm a part of Google research on what is sometimes called like the responsible AI team. And we do a mix of stuff, but a lot of my work is still oriented around healthcare. And then due to sort of my prior experience in algorithmic fairness, a lot of it is sort of oriented around health equity. And my current role is also a little bit more maybe academic in scope and focus than like some in industries. Like I'm still doing a lot of publishing, going to conferences like this, and so on. But some of it is also product oriented work, and that is maybe also something that was important to me. It was actually sort of doing things that are grounded in real world context and use cases. And while it's like a bit different than working at like a health system or a health tech company or something, right? Like there are like large scale products, and there's opportunities to really have impact on those and understand like what things look like for real world products and systems and so on.
Okay, great. So big takeaway, find who you're jealous of. I like that a lot. And then there could be like multiple paths where you kind of find the same, like, oh, I feel like I'm enjoying this trajectory. So it kind of depends on the person. I kind of want to go into a little bit on like, a little bit more into like career discovery and like early decisions. So the first question is, what have been some defining values behind some of your career choices?
Yeah, when I talk to people who are younger and sort of coming up in their career, one of the themes I hear a lot about is like optionality. Like, I don't know what I want to be. Do I want to be a professor? Do I want to work in industry? I better do this thing that sort of maximizes my ability to get all of them. And I think for much of your formal education, this is like probably a good thing, right? Like, you want to get a high GPA because that looks good on your resume, which a bunch of different jobs will also like appreciate and admire. I do think at some point it switches. And so doing some sort of weird, super specific internship or a project that only appeals to 10 people in the world becomes almost like a risky thing, but also something that like makes you feel alive. And so one of the things that I have tried to hold as a value through all of this is that there are things that make me come alive that may reduce optionality, that may not be the most hype thing, that may not be the most exciting thing to the broadest amount of people. When I went to my first NeurUps, this is dating me, GANs were a big thing. Raise your hand if you've ever programmed a GAN. Okay, like a third, maybe half. Raise your hand if you've used a GAN in the last year. Anyone? Anyone? Oh, yeah, a few hands, maybe 3 hands, maybe, yeah, okay. These things come and go. Being in GANs 5, 10 years ago, not 10, maybe 8 years ago was a really advantageous thing. And I had no interest whatsoever. And so I actually never programmed a GAN, and it was not something that I made necessary. And so I'm not saying like don't ever chase the thing that a lot of people value and a lot of people are interested in. That is not what I'm saying. But I am saying that there are external forces that will tell you what is valued, and then there is sort of a equally important and maybe less obvious thing inside you that is your own value system and principle of this is an interesting problem to me for these reasons. The thing that made me come alive was working on fairness, working on equity work, which at the time that I started my PhD was sort of a nascent field and is rising, and as some of you may know now is less funded, less hypey, and I still really love it. And so maybe there might be a way to repackage it, maybe there might be a way to work on it in a way that isn't as going to attract controversy, but it is still the work that I want to do. And I think maybe as far as your question, Sarah, about values and principles, the world will tell you values, the world will tell you principles, but many times it may overlap with your own interests, but if you can find the ones that sort of feel right to you, even if everyone else is not as into it, then that's sort of an interesting thing to at least explore.
Yeah, I mean, I would second a lot of what Irene just mentioned. I feel like in my own career, like I've tried to, choose research topics and choose teams and things like that that were aligned with my values in most cases. And, in some sense, like, you can sort of fight headwinds, for example, like, as Irene was mentioning, like, topics related to equity and fairness and so on are not popular for all sorts of reasons at the moment. But there's ways to sort of like continue your work in a way that is aligned with your values often, and it may not be ideal, but there's sort of still ways to make progress. And I think there's also other ways that this comes up, in that like being at a large tech company, there's sort of many different teams that have very different approaches to how they go about research. And one of the reasons that I'm very happy to be on the team that I'm on is that we are in a team that sort of really values sort of like independent research autonomy and sort of like, having sort of a, scope and so on that is like very oriented around, pursuing sort of foundational research that we think is like important and relevant, both like in the fundamental like academic sense, but also like, around product and so on. And so, it's been a space where like I feel like I've had really the space to kind of like continue to pursue like what I think is valuable. And, I don't think that's something that, really necessarily is true like everywhere in industry or in academia. But, it's been something that has been, important for me. But, Yeah, so, in general, I think like kind of echoing what Irene said, like, it's important to kind of like stick to what you think is important and valuable, and, like whatever is hyped up at the moment will sort of change over time. There can be some value in, sort of like being on top of trends, just even in the sense that it brings more attention to your work. But, I think it's important not to do that at the expense of things that, are sort of aligned with your own interests and values. So yeah, might have more to say later, I guess.
Great. I think there's like a common theme oftentimes when I talk to PhD students, which is like everybody's really anxious not to be working on like the most trendy thing, especially when it kind of is not good for the path of like your PhD or something like that. Like sometimes you got to stay the path. So it's good to know that people who are doing very well in their career also decide to stay the path. Okay. So you're each in a different position in your career, one in academia, one in industry. What helped you figure out the kind of sort of environment where you do your best work?
That's a great question. I firmly believe that you often don't even know until you try it. So I want to sort of preface all of this with like, you can have first principles reasoning and then you get there and you're also allowed to change your mind. I want everyone in the audience to think about something that they are really good at. And maybe one way to figure out if you're really good at something is actually look around you or think about all the people in your life and think about what they're unexpectedly bad at. What is something that you're like, wow, why is everyone so bad at programming GANs? Why is everyone so bad at making plots? Why is everyone so bad at emailing? And one of the things that's been super helpful for my career, I'll take a moment, think about that for real. Like think of all the skills that everyone else is super sucky at and you're just like, man, it's so bad. You want to find an environment that fits those strengths for you, and then also the inverse, that like shields your weaknesses. People often ask like how I knew I wanted to be a professor, and there's like the lofty answers about like academic freedom and working with students and the mentorship and the teaching, which I firmly stand by. But the truth is that academia sucks in like a variety of ways. Like you get rejected all the time, you have it's very lonely, there's long feedback loops, and all of those things for me, I am uniquely good at. Like, it just doesn't get me down in the way that it gets a lot of other people down. And the way you find that out is during the PhD when you are also lonely, getting rejected a lot, and like, struggling in certain ways. And so maybe the salary is not as big of a deal to me, although if anyone wants to fund my research, please let me know. And so like the question is sort of how do you figure out what the environment is? There's academia, there's industry, you could go work in public policy, you could do a startup. All of those situations have their own bright spots and downsides. And I'm not saying any of us will be completely impervious to all of the downsides of any environment. Sometimes academia gets me down to, for example, right now. But I think for me, it does in fact feed a lot of the things that I am good at and the things that I am the downsides, in my head it sounded better. Okay, my strengths cover the things that make it really bad. For example, like I really like building community, and that is the thing that academia really doesn't have naturally as much, and it's something that I spend a lot of time on. And then the things that are positives, I think, sort of cover some of my weaknesses, which is like, I don't like necessarily someone telling me what to do all the time. And I don't like feeling pressure to like have to work on this project. And no one tells me that either. So maybe that's my like general thought of like how to pick the environment that would be the best sense, with the caveat, of course, that you don't know until you try it, and then you can sort of recalibrate.
Yeah, I mean, kind of building off of that, like I felt like in my career, it's been, it's the kind of thing where you really don't know like what your preferences are and like what works for you until you've sort of like been in a bunch of different circumstances and scenarios, like worked on a bunch of different types of teams and sort of like, tried to just feel out what makes sense. And, like for me, it's turned out that, I really like working with like sort of a broad set of collaborators that, both, are better than I am at the things that I care about and, have a lot of skills and expertise in areas that I'm not very familiar with, right? So both kind of like a broad interdisciplinary set of collaborators and like sort of, deep experts in like stuff that, I'm also like nominally, sort of focused on, right? Because, in some sense, like you need to be challenged so that you can grow in the areas that you, care the most about, but you also want to like have sort of a broad, broad perspective and so on. So, like that's been something that, I've sort of, sort of learned is important to me over time. And, there's also, I guess, like when we're talking about different types of careers and things like that, right? Like, questions related to like work-life balance and, the amount of, job security and safety and psychological safety and all these other things that sort of go into, what makes up like a fulfilling career that you sort of enjoy on a day-to-day basis, aside from any of the more sort of like, tangible things that you can measure. Like, those are also things that are not necessarily like, specific even to industry versus academia or even any given company, right? Or organization more broadly, but more so like the specific context of your team and the people you're working with. And, a lot of that is stuff that, maybe, it's sort of hard to necessarily like predict or anticipate exactly like, what to expect in a given circumstance. But, it's also something that, if you talk to folks that, have worked with the folks you're considering working with, you can kind of like, suss out what it's like to kind of work in that environment. So yeah.
Hi. Yeah, welcome, Tara.
Sorry about that. Got stuck in the traffic and there was a so it was quite a mess. Sorry about that. Yeah, sure, absolutely. Yeah. So my name is Tara Tagavi. I'm a senior director at Oracle Health, working on the clinical data and modernization of direct and health record. Yeah, I'm glad to be here, and I'll join the rest of the conversation.
Cool. I'm actually going to restart. I'm going to ask the first question, if that's okay. So before we wanted to get into career advice, we wanted to hear the trajectory of how you got into your current position, and what kept you here.
Yeah, sure. So I did my PhD in computer science. So I was a software developer, joining IBM as a software developer. And it's been a long time ago, actually. So I joined IBM in 2007. And worked there for a few years. And then this is actually, I saw one of the questions was around like, what was the turning point really? So I was working on algorithm design, software development for the chip design basic organization of the IBM. And this became really the turning point when I realized that a lot of the work that I'm doing is incremental. So I was looking for some area that I can put like, push it more further, like a newer, basically, area that I can really create work that is not only incremental. And that is where, when I basically looked around and saw that, my interest was in math, I was really good at it, and computer, so I kind of like found data science at that point, or applied science now, as we call it, as like an area that I can create really improvements that are like, it's not marginal only. And I got a degree in applied statistics. At that time, it was back in 2011, 2012. There was no concept of really, per se, machine learning. It was very minimal. There was some like people who were working in statistics. And then that's how I get into this field. And then I joined Qualcomm as a scientist. I joined Amazon as a scientist, and then I joined Oracle. Now, as continuing that trajectory of the science. And then I moved actually to management and just created teams, and then created like more of initiatives, and kind of went up the ladder that way.
Great. Okay. So I wanted to talk a bit about skill building for like modern health AI careers. What's one skill that turned out to be far more important for your career than you expected?
You want me to go first? Yeah, sure. So I think, soft skills, in my opinion, are the skills that are more important in your career. Obviously, technical skills, knowing basically keeping up with the pace of the domain and the overall the field is important. However, more than so is your ability to basically bring initiative, create like teams or work under you that has an impact on the others and influence basically. In my opinion, overall, I've been in industry for 20 years now, almost 20 years. I found the ability to influence, the ability to work in the teams, And then obviously technical skills, I mean, you should back it up with technical skills, but overall, in my opinion, soft skills are more important. People who have stronger soft skills, they are more successful, in my opinion, overall during their time.
Yeah, something I found sort of useful in terms of framing this is just, sort of thinking about how you sort of respond to ambiguity and maybe like large, complex projects where you don't even necessarily know like what is the relevant background knowledge that you need in order to like make progress, right? And so, I think in some sense, like this is kind of like what a PhD teaches you to do in like the most generic sense, like sort of take something that, is really underdefined and sort of not well scoped and sort of say like, how can I, go and seek out all the little bits of knowledge that I need in order to make progress, and then sort of like actually innovate on the components that, there's sort of no existing knowledge or solution. And so, like I think that's something that, I sort of encountered a lot in, kind of like my education, which was like very sort of, it was this kind of like interdisciplinary, like both biomedical engineering and biomedical informatics. They're both like kind of, themselves sort of like underscoped, ill-defined fields that are, both like applied and sort of, foundational and technical and so on. But like, there's not like a core set of knowledge there. And so in some sense, it's about saying like, what problem do you care about? How do you like develop a broad enough understanding of everything that's out there such that like, you know where to look for the pieces of information you need, but you don't necessarily have this like broad and rigorous foundation on like every single topic, which, maybe you'd imagine you might build with an alternative approach where you sort of like go and try to fill out, your knowledge base in a very like structured, systematic way. And so, it's kind of like a mindset and philosophy that I feel like, maybe is not something that everyone runs into, but I feel like has been like really useful in terms of like me trying to understand like how to operate in spaces where, I don't necessarily know what I'm doing in all cases.
A related thing to what Stephen just mentioned, I think for me, is I often think about this as just when to go hardcore and when to not go hardcore. When you think about your career, or even just like the long landscape of things that you could do or could not do, or people are asking you to do or not, I have found in my life that there are some times when push comes to shove and you really need something done, that I can dig deep and dip into this reservoir inside of me. And you can like, some people call it, we might pull all-nighters, or you might sort of cancel all their stuff. We'll probably talk about work-life balance later, but there's this idea that on occasion, when you really want something, you can dig deep and you can do something that astounds you and sort of becomes much more useful in your career. It could be learning something, it could be pushing for a deadline, it could be being so finicky about plots that you're going crazy. For me, I think it comes up in weird ways. For example, my first year, I was reviewing for NeurIPS. I was so nervous that I spent hours and hours, days, weeks, making sure my reviews were good, and I didn't want to disappoint anyone. And then I got top 400 reviewer at NeurIPS, and I was like, oh, this is too much. This is I shouldn't have been pulling all-nighters for this. This is too much. And maybe the skill is not so much knowing how to dig. I think anyone in this room, for the right things, really could muster in themselves that superpower. But I think the skill is knowing when to dig, to dip into that reservoir. Because the truth is that if you dip time and time again, one day you'll go back and it will be dry. Because either you didn't really want it, or because you dipped too much earlier, or because you didn't wait long enough for it to regenerate. And so I think, whatever your circumstances are, and whatever age and whatever other life factors might affect that reservoir, I sort of want to challenge everyone to think about what are the things that you would really be happy that you had dipped into it for, and then what are some things that you're kind of you know what, I probably didn't need to have pushed myself that hard for that thing. And discerning that, I think, is not an easy skill, but I think is something that I've gotten a lot better at over time. And then also just knowing how much is in that reservoir. Today, there's nothing in it. Maybe tomorrow we'll be able to get something going.
Okay, great. There's a few things that I wanted to kind of follow up on. One is this intersection of, soft skills and us working in an interdisciplinary field. So health AI is incredibly interdisciplinary, and these soft skills are very useful. Knowing how to gain broad knowledge on different areas is very useful. But in terms of the people that you're working with, when you're considering a new collaboration with someone from a different field, how do you assess if you'll work well together?
I'll go first since I have the mic. The rubric, the sort of heuristic I use is I like working with people where I can learn something from them. And so that means that like we're not right on top of each other. There's some of my dearest friends, people in this field who work exactly on the same things as me, and that's awesome, but also we don't have as much to sort of like, we don't bring different things. And then the second part of it, which is embedded in there, is that I can learn from them. Like, do our communication styles work? Is there enough respect? Is there a working relationship that makes me excited to go into meetings? I have worked with people, no one in this room, don't worry, it's not you, but I've worked with people where I like dread the Zoom call. We do the Zoom call, and then afterwards I'm like, oh, I gotta like take a break for the rest of the day. Like that took everything out of me. Don't work with people like that. It's like your body is telling you don't do it. And so I would say for me, it is people that I can learn from, and that changes obviously as dynamic over time.
Yeah, I think I'll second Irene's points there. And maybe you know, to add to that, like there are folks where I read their papers and I get like really excited about, you know, the fact that they're thinking about some of these problems that, you know, maybe are related or similar to the ones I'm thinking about, but they've sort of approached it from a very different lens. And I feel like, you know, there's often like a lot of ways that we can improve the work we're doing by, you know, sort of integrating different disciplines and perspectives on issues and so on. And so, you know, if I read someone's paper and I get really excited about the way that, you know, they're presenting something, you know, that makes me really excited to work with them. I guess it doesn't necessarily tell me if it'd be a successful collaboration, but at least it helps you build excitement. But, you know, kind of like Irene's points, like, you know, you want to work with people that, you know, help you grow. And, you know, those can be people who, you know, are both sort of like expanding your breadth and maybe expanding your depth.
Yeah, and so I really, when I talk to people, different places, or when I interview people, I really look for that level of energy, engagement, and the sense of ownership that they bring to the table, because that is really extremely important. If they did that work really with like the passion that they put when they are explaining their experiences, that basically, in my opinion, can translate into like they bring that passion into the new work, right? I look for that kind of like really energy and the passion that they bring into the picture. And the other areas is really their ability to deliver, their ability to basically drive a project, work. And obviously, like, you know, as I mentioned in the beginning, that their ability to work within the team, and they kind of like, you know, are really a team basically player. These are the values in the candidates or people I talk to, even if not for a direct job, but like I really would like to kind of like fill up around myself with these kind of people. And as you know, they mentioned also this, like, you need to have like diversity in your team. Everybody is good at one area. Somebody is good at, you know, development. Somebody is good at, you know, coming up with ideas. Somebody is good at, you know, socializing the ideas and creating that influence. So everybody is good in one area, and obviously everybody will have like some level of a skill set in everything. But I mean, we are human beings. We are good at like we do have like one expertise which stands out, right? So my goal is to fill up my team with diversity. And I look at people's strengths really from what they bring, not necessarily comparing people with each other, like it has to be like, you know, the same way, but what strengths does everybody bring? So I'll try to actually emphasize and develop on people's strengths where they are, and then obviously you can always improve people on other areas that they lack.
Great, yeah, I think sometimes as PhD students, it's easy to think like when you're working with someone like, oh, they know all these things, I'm not gonna be able to like keep up. But the point is that you don't necessarily know all the things that the other person knows, so that you can complement each other. Okay, great, so on the same topic of collaborations, different fields often have very different timelines and incentives and definitions of success. How do you navigate like mismatched expectations when you're collaborating or working with people in other disciplines?
Yeah, so I work with teams like that have like different basically agenda from my work at Amazon and also now at Oracle. I've always been a scientist, drive a team of scientists basically. However, I work with engineers, with the product team, at some points with like even the sales team. So basically, that is true. Actually, many times the priorities are different. I've seen, for example, sometimes like product team pushes a product and wants to just get it out of the door. They ask for like simpler models, no models, basically just get the things out of the door because it makes basically their work look better. However, on the other side, like for example, scientists might be like emphasizing on like the quality of the model and just a spin, analyze and improve and those kind of things. Engineers more on the service side. So many times priorities do not really align. The best way to really go about this is that to look at it from not what is in it for me, but what is in it for the whole project and the team and organization. What's the best, right? And we can always adjust based on that. Like, for example, if you see that, you can put like if you take like another month, you can take a much better model, but then we lose the market due to that, that's not necessarily a good thing. You can always do a revision later on your model, right? But let's have like basically the product out. Or if, for example, you have like a huge model that put a lot of latency on your service side, that's not necessarily again a good thing. You can always like do some optimization and take more time later in later revisions to do that. So basically, look at it from the top. What is the best interest of the organization? And if the best interest of the organization is to now do it based on this roadmap, and you can always work with your leaders on that, every team should do these adjustments, basically, that we adjust our work and prioritize. And many products are not really out of the door. They're the best in their best basic shape of it, right? So we need to basically look at from that perspective and consider the other the burden that we put on the other groups and teams and skill sets, and to kind of bring this into this consideration. I answered this question from the standpoint of the product, basically. I don't know if like people have like different type of answer, but this is basically what I'm always like looking at it from.
Yes, I mean, being in industry as a research scientist, I sort of maybe sit like kind of within the same dynamic, but experience it differently sometimes, right? So in the sense, me personally as a researcher, it's valuable for my own career to publish things and get papers out, and to do that in a way that is perhaps like agnostic to the particular product context at the company, but at the same time, it's like valuable for my career to do things that have impact on those products. Right, and so there's some like personal balance there that you have to strike in terms of how do you sort of spend your time? How do you think about which of those aspects are maybe more relevant and important? And some of those things help build your, or at least I think of them as building sort of like my public portfolio of research and so on. And then some of those things as being things that are sort of like internal to the company and not necessarily things that would necessarily be externalized, but still sort of help build my career, right? And so, there's some tension or, sort of like different trade-offs to make there, and different people that are research scientists in industry sort of like make different decisions about how to sort of balance those things. And, there's also kind of a totally different thing here that I think is interesting, which is that our field is one where there's a bunch of different disciplines that have different norms around publication and, what is considered like valued. And so, I think one of the clear ones is, clinical folks tend to value like journal publications, CS folks tend to value conference publications. And so, you sometimes get into these weird situations where, you may have like a NeurIPS paper and your clinical collaborators, don't really value that at all. And then, vice versa, you may, publish something in a clinical journal and, you may even do things that are interesting from a technical perspective, but then those, aren't really seen by people publishing in computer science venues and so on. And, venues like ML4H, I think, try to, straddle this boundary to a certain extent. But it's challenging, right? Because, in some sense, we're talking about publishing conference papers that are more clinically oriented, and then there's a question about how people from both of those communities will like perceive those and their impact and so on. So, I think like, in some sense we have more options in terms of like how we can pitch and frame things for different communities, but at the same time we have to sort of deal with these, different disciplinary norms around like what is considered impactful, and it can be challenging at times.
I have two thoughts. One, have the conversation up front. In our dream world, this project yields a medical paper and a neurops paper. That's the ideal, and we're going to march towards that. And if people aren't on board with that dream, then we probably shouldn't be working together. So at least having that conversation up front is helpful. Who knows if you actually achieve it, but at least you're sort of striving towards the same goals. Second thought is that as an academic, oftentimes it's sort of the question becomes like venue or what kinds of angle to take in the project that could be of most interest to different parts of the team. In my research career, I have found it to be the most energizing and the least problematic on this particular angle when the project is super inspiring and very expansive. There are projects that are basically just going to be one thing, and then we're just sort of trying to optimize for how many of our career goals this one project fits. And there are projects that could be 5 papers, 10 papers. This could be a PhD student's thesis. This could be, a whole department one day, who knows? And those are the projects that I get the most excited about. Will take the longest for it to pan out, but then I think there's more of an abundance mindset and there's less, oh man, like if this doesn't go into an econ journal in the next year, then I'm screwed. It's more like, oh, there's gonna be an econ paper that comes out of this probably, and a machine learning paper, and a policy paper about the implications there, et cetera. And so it is a hard thing to find those kinds of projects. They come around once in a while, but I think when I think the aphorism in tech is, when you're in a rocket ship, don't argue about which seat you're on or something like that, but apply that to academia. So a smaller, less funded rocket ship. But similarly, figure out what kind of projects feel more expansive, and then still have the conversation up front though about what kind of papers and what kind of venues.
Okay, great. We have about 7 minutes until I open up the floor to Q&A, so I'm gonna kind of pick and choose on a few more different topics. The first one is on failure. So can you share a failure or setback that taught you something about yourself or about this field, if you're comfortable?
So yeah, I think in a lot of ways, the arc of my PhD research was realizing that stuff that I did in my first few years didn't really make much sense. And then I spent a few years basically just sort of digging deep into, some of those issues. And then, in some sense, trying to understand those failure modes, was the contribution of my PhD. So in some sense, is that failure, maybe, but I also think that that's kind of where interesting stuff happens. And, I think the main takeaway for me from all of this really is just sort of sort of saying when something feels weird, you get a result and you're like, huh, that's strange. Don't necessarily just kind of brush it off, right? There's actually usually something interesting and fundamental there. And maybe trying to understand that is itself something that is a meaningful research contribution and can push the field forward. So yeah, that's just kind of an anecdote that I think might be, or might resonate for some people.
Yeah, I mean, I've been working in industry for a long time, so I can talk about several actual failures that I had or the team had. But one that stands out is that, so our field is very dynamic. This means that we need to be really quick in adopting the new technology and coming up on the wagon, basically. Otherwise, we would be left out, right? It's really difficult to catch up. And I've seen this multiple times happens in organizations that they don't really pay attention to the development in the field at the time that they should. And when they do, it is already too late. It's more difficult, basically, to adopt, right? And this is a mistake that I did also myself. I mean, I got very much involved in projects and daily activities that I didn't really have that much of a chance or time. And probably it was a mistake, so I should have opened up time in my basically work to kind of like, really adjust to the, or learn about the new technologies and, the advancement in the field more quickly, basically, on time when it happens. So, I mean, you guys, many of you are like, in your early career, and this, as you can see, the field is very dynamic. So, I'm gonna take this advice to kind of like, incrementally adopt yourself and, learn the new things when it is coming into the, when it is really still hot and new and, kind of like, it's easier to basically adjust to the advancement in the technology and basically the field if it is incremental rather than just, have like a gap and then like suddenly update yourself. Yeah, I mean, that is basically one area that I've seen. And I mean, I don't want to name, but like there are organizations, we know that, they kind of were doing good or companies that they were doing good, but because they kind of like lost the ball and couldn't really adjust to the technology on time, the new competitors came along and, swept it away. So yeah, I think that is one thing that, really remains with the people for a long time that, adopt yourself or adjust to the advancement of the technology really incrementally and over time. It's easier. Yeah.
I really like that point from Tara. Maybe a way that sort of shapes in my life is that failure for me is not necessarily the paper that got rejected 3 times, although that was pretty brutal, but is more the time that is wasted working on projects that were not either something that excited you personally, to Stephen's point, or sort of technologically the most good fits for what's going on right now. There's this notion of the bitter lesson, which many people people in the audience probably are familiar with, which is that you should work on technologies that will adapt well to scale. We have a lot more data, we have a lot more compute. It's not that no technologies will matter ever again, but it's that as things change, they are likely to change in this specific way, and then you should take that into account as you pick the kind of projects you work on. And so when I look back on all the things that I've worked on, the failure to me is the lost time on projects that were either not going to pan out, so we didn't have like a test early on to say, is there enough of a gem here or enough of a promise to work on, or is that didn't keep up or didn't take into account all of the other things that are going on and therefore become less and less relevant as models get better in a very specific way or data sets get bigger in very specific ways.
Okay, I think we have time for one more question before we open it up for questions in the audience. So if you could give one piece of long-term career advice, given that the field is going to look very different probably in 5 to 10 years to researchers in this room, what would it be?
So I've been thinking a lot about this. I teach a class of undergrads, and they're constantly asking or sort of telling me about the job market. I heard recently from Allison Koenecke, who's in the audience, who will be giving a talk later, about the fact that new grads, when they interview for jobs now, oftentimes will be asked to be interviewed by an AI. So there's no human for the first round, and then they instead will read out questions and then give their own responses, and it'll be recorded, and then there's some sort of preliminary speech recognition AI pass, and then if you pass that, maybe you'll talk to a human later. And more it feels like this process is becoming very impersonal, it's very automated, it's very prone to bias. What could one early stage researcher do in the era of, infinite, papers that are generated, and who knows if they're any good, or AI slop that's created. And I think there are 1,001 ways that you could use these tools to make your life easier in ways that do not enrich yourselves. My advice then is to, 1, be familiar with those tools. Like it's happening right now. I'm not saying use them every day for research purposes, to understand how you could cut corners, but understand what it is out there. And my hypothesis, my my bet for the future is that it will become more and more important to be sincere, to have high principles, to put your name on things that matter, that stand for who you are. And if that means reaching out to people and emailing them an actual email that you wrote yourself and didn't use a large language model for, people can tell the difference. As someone who receives a lot of emails, especially around PhD application season, I can instantly tell if someone used a large language model to write this email. Similarly, as you pick on projects to work on, people can tell if you really care about that, if you thought through everything carefully versus you sort of just followed something that everyone else was doing, et cetera. So maybe my advice is to care a lot, even when it becomes easier and easier not to care.
Yeah, I mean, I would second a lot of that. And I feel like I don't know necessarily whether this will, always continue to be true, but at least for me, like, I feel like it's been important to, sort of think about like how I sort of build my skills and overall like set of, research projects and so on, in terms of this idea of like the T. So in some sense, like you have this broad set of expertise where you sort of know vaguely, like, in some general sense, like what's going on like across the field. So you can sort of, look and find, different pieces of information when it's sort of relevant. But then you have this one area or, maybe several areas that, you sort of go very deep on. And I think like that area you go very deep on, like should be one that, is aligned with your values and like fundamentally, like it should be something that, you actually care about deeply and is not necessarily something that is like aligned with whatever is currently hyped up. And I do believe that, like employers and potential people, potential collaborators and so on, like can tell the difference between, something like you're genuinely passionate about versus something that, you're sort of doing just because of the circumstances of how, you ended up working on something. And, it's not to say that like everyone, finds themselves in situations where they're able to sort of, do this, but in some sense, like, if possible, like I would, choose to work on things that, you have like genuine passion and excitement about and like are aligned with, your values in sort of all senses of the term.
Yeah, so I would say find the right balance between going deep and going broad. So I've seen people that, like during all these years that I worked, that, they know one area very well. They don't know anything else outside of that area. Or I've seen people that are like very superficial, just like, know buzzwords and keywords. They don't know anything about that beyond that, right? That buzzword and the first like line of definition. So neither of them, both of them are in different like a spectrum. At least the people who are going deep, at least they have like some options. The problem is that you will lose the options if you go only deep and you don't have knowledge about other areas. I found it really in my career that, I want to be like deep in like certain areas, but also learn other areas to some extent and be familiar and kind of like, have like have done some research on that and know about that and get myself like into different areas really. So I found it really like a good advice to kind of find the balance, the right balance between how you want to go deep in one area and also broad on the other areas. And the other thing that I can say within the same line is that develop your skills even if it is not within your comfort zone. Try to learn in other areas, and this is an advice not just for career, for life also. During your life you would like be like exposed to like many other like aspects that you haven't been really seen as like when you're just graduating, right? So I graduated 20 years ago. I know I've been in this basically your shoes. So I know like later in life, you need to have much more skills than just like, the basically area of the work that you do. You need to know about finance. You need to know about like a lot about the medical stuff. So, there are a lot of things that you need to know. So in my opinion, knowledge is the weapon really. Try to learn many other areas and try to be like sensitive to basically other areas of work. And I found it like, actually there are many opportunities that you can do. Sometimes people say we're busy with our work, we really just don't have time to like, learn about anything. There are many opportunities that you can basically use toward that. Examples of such for myself, I learn when I interview people, I learn from them. Like they come from like a specific area, and then I don't know about that. I do some research on that area, read a couple of papers, and I kind of learn about the areas that I don't know from the people the candidates who come like interview with our team. I learn from like people who, I meet in parties and, like gatherings and different places. What area are you working, this area, whatever. Interesting, like basically pick up some words and then I do go, research myself. So kind of like I'll try to, start like from like clues and, see like, for example, talking to somebody or whatever, I'm here, you're talking to people from different areas, right? There were like yesterday posters that I stand by and I didn't know about the area. So just like I did a little bit of Google, I just took some notes and later I will do some research on that. So my point is that both at work and beside work, try to learn about different basic topics. Obviously, in your work and your area, try to become really deep and find that balance, and that will help you really. That will make you stand out.
Okay, great. Thank you so much. I will go ahead and open it up to questions from the floor. We have a mic up here if anybody has any questions.
Thank you so much. It was a really interesting conversation and I learned a lot. So the question I had is, it's very difficult to connect the dots like looking forward. You are in the later stages and you're looking back and you feel that there might be some things that you did that you get like maximum ROI from. Like you invested less time in that then, but now it's like really useful to you. Do you have any advice or tips like that that even today is relevant for like early careers?
Yeah, so the question is about like what were things that we did some level of investment and came out like useful. Yeah, I mean I've sure like for example, I mean my case many years ago I kind of like had I mean, as I told you, like I was a software developer, so I had a lot of expertise in like C, C++, whatever. But at some point when I moved to science, I kind of like I remember it was like Christmas time, and there were like a few days I picked up a book on Python, and at that time, I'm talking about 2011, Python was not really well developed, but I thought, okay, this is I've heard actually this is a good language to learn, so I spent like few days really learning and coding, and actually came up really useful in my life. When I was an IC, I basically used that. So just investment on like. Out of like my extra time that was a dead time, I remember I used to sit in the office and it was like few days before Christmas and people were not there and there was nobody bugging me, so I kind of used that time to do this. I always try to kind of find time that are dead and Friday nights or like right after deadline and these kind of things that are extra time that I kind of dig into like an area that is basically interesting. Another basic area was that when I was at Amazon, another example, when I was at Amazon, I was working Amazon Go. I was actually owning the team on the behavioral models. I was not really working on computer vision, but there was a sister team who was doing the computer vision. And at some point I found like some extra time on my plate and I learned about their papers and their basically most important models and what they're doing. So that actually came really handy years later when recently actually when I moved to Oracle Health and we had like projects on the multimodal basically and I kind of developed and picked up from there. So yeah, I mean there have been many like areas that kind of like I found times that were dead and that put it toward a skill that I later was able to use.
Yeah, I mean, just maybe like one or two thoughts. Like, I can basically, attribute the fact that I have the job that I have to the fact that I did an internship in midway through my PhD, and I only got that internship like through a chance encounter with someone I talked to at a conference, right? And so in some sense, like, it's not necessarily reproducible, but in some sense, like by just, being at places like this and talking to lots of people, you sort of like create opportunities for yourself in some, diffuse and nebulous way. But, I think maybe as kind of like a meta point here is like, in some sense, there's like a selection bias to asking the people that were successful what they did in order to, achieve whatever it is they did. And so in some sense, like, maybe that we think that these things are the reasons why we were able to, get wherever we got in our career, but we don't really know whether those are actually the behaviors that, are the ones that, lead to success in some sense, because you're not asking like everyone and then, thinking about like what are the actual behaviors that lead to those things. So, in some sense, like, what do we know?
+1 to Stephen's thing about showing up to things like ML4H. Congratulations, you guys have all done it. I just talked about how you find things you're good at and didn't do them more and more. I'm actually terrible at attending conferences. I just want to be in my hotel room, like watching TV. So one of the things that has helped me and has paid off is that instead of wanting to leave, or I still want to leave, but I set a goal, I pick a number, 5 people, 10 people, 3 people before I'm going to scream and want to leave. And so just go out and meet people. Meet, by my definition, is literally say, hi, my name is Irene, what's your name? And I found the highest ROI, so to speak, by meeting people who are at my level. I think there's a tendency to say, oh, here's this big shot person, like I want to tell them how much I enjoyed their talk. You should definitely do that, but I found that it is yielded more long-lasting relationships professionally, but also personally, just meeting people who are sort of at your level, understand the things you're going to, and you can sort of share strategies there. Stephen and I met at a conference just like this many, many years ago.
I came to the US for grad school in 2007 and left academia in around 2016. So at the time, the US was, in my mind, obviously the place to do science and to do tech and stuff like that. So things are not the same now. So do you have any advice for the students here on how to select the environment? What are the things that you should look for in the environment where you want to pursue your career?
I think anyone who tells you that they know what's going to happen in the US in the future is lying. None of us really know. I will say, I'm at UC Berkeley, and the professors, we have a group chat, and we talk about, is it time to go? Like, should we be looking at other places? People in Europe are recording them. And I will say, you do the math, you look at what's going on now, and also what you might imagine to, more funding cuts, et cetera, and the math still says that we're staying here. I would say, like, every single UC Berkeley professor that I talk to has not left for Europe yet. I don't have much to offer concretely, but I would say nothing is set in stone, the good and the bad. And so being able to, I guess I call it staring into the abyss, like I would never consider ever leaving academia, but maybe I would. And so thinking about what are those conditions that would cause you to leave academia, change your career path, what would need to change, and being very honest with yourself about what it would take, rather than being, say, a frog boiling in water and then slowly dying. So just being able to confront what the scariest possible version of is, and seeing, have we reached that yet?
Yeah, I'll second Irene's point that it's very hard to make forward-looking predictions about how, kind of the climate will change, like particularly in academia over the next, few years. I can maybe just sort of, say things in industry, have changed over the past few years, but I wouldn't say that much as a result of things that are going on in the current US political climate. So, I think there have been industry-wide shifts in terms of the way that, AI has become more central to a lot of businesses, and that's changed the way that research is conducted and how companies think about publication and things like that. And, but those are changes that have been happening for the last few years. And if, aside from those large meta changes, I would say there haven't been changes necessarily to the way that I scope my own work that is in industry. And so, regardless of sort of what's going on in academia, I would say that the opportunities in industry haven't changed a whole lot in 2025. And so, if all stays the same there, I believe that there will still be opportunities for folks to do research at least in this context.
Yeah, as they mentioned, it is hard to predict what's going to come in the future. Definitely, there is opportunities for research both in academia and industry. The environment is very different from academia to industry, and I've been in both. I would say look at what your interest is, which basically environment you want to be in. What type of work you want to do. Because things will change, right? The policies will change, the environment will, basically the way that the things are getting conducted will change. It's difficult to, count on that, but rather count on your own skill, your own development. Try to basically be in an area that you feel more comfortable, you like it, you put more passion on it, you are basically interested in it. That is the key to go about that. I mean, geographic location, I don't know, like people have different preferences. Some people are bound to this country. Some people are more open to go back to their own countries or other countries. I mean, I would be like, personally, I would be open to move and go other places if there's not like an opportunity for me here. But I didn't find it to be the case, at least now. As you mentioned, I mean, at the moment, I don't think so. There is a reason. I mean, there's more panic than reality. But I understand that there has been a change, in the policies. So, but overall, again, policies can change. So that's not something that you can count on your own, yourself and your own development and your own interests.
Great. Well, thank you all. We are out of time for this panel, so maybe we can give them a round of applause again. I feel like I'm having less of an existential crisis about my career, so that was helpful, I'm sure, for others as well. And we'll go ahead and wrap up the panel. Thank you, everyone.
Hello, my name's Emma. I'm part of the organising committee for ML4H. Thank you so much for that very illuminating fireside chat from some people that I personally very much admire. It's my pleasure to announce the Spotlight demo talks next. So if we could begin with the first talk. I ask that the next person, if you just come on stage after, no need to wait for me to come back to announce anything. Thank you.
Good morning, everyone. I'm Sumuk. I'm a lead data scientist at the Cardiovascular Data Science Lab at Yale. And I'm excited to show you CardScan, an on-device AI for scalable, privacy-first ECG interpretation. So we have ECGs everywhere. We have the classic 12-lead ECGs, and more recently, the single-lead ECGs that are available on our wrist right now. And the ECG is captured on the device, sent up to a cloud server where the models run. And this is the usual setup for how AI ECG is being used today. So before CardScan, we had already built and deployed a fully validated 12-lead ECG model for detecting early cardiac amyloidosis. And this is a CNN trained on over 32,000 clinical ECGs. And we have currently deployed it as a web application on our website. And coming to the second model that's used in this particular application is the single lead variable ECG called IDSHT. And this is a noise resilient and ensemble model trained on over 260,000 single lead ECGs to predict structural heart diseases. And we deployed it as a mobile application, but the model was still running on the cloud, and we recently used it in a 600 participant clinical study. So why on device? So everything we have built so far is on the cloud. It involves users uploading their ECGs, that's their personal health information, to the cloud where the models are run. So this introduces latency uploads, and it's dealing with sensitive health data and is under many regulations. And internet accessibility is also a concern. So the solution is a mobile application that runs the models on the device without the need for internet, and everything is offline. So that led us to develop CardScan. So it's a mobile application that runs models entirely on device. It's end-to-end offline, and it uses the same validated weights as the ones on our web tools, but it's smaller and the accuracy is still the same. And we also use real-time feedback with the neural engine accelerations from the device. So how the app actually works. So we have, for the 12-lead ECG pipeline, we have the application, the user just opens it up, points the camera to a ECG, either a printout or on screen. And the first thing that happens is a lightweight YOLO cropper that automatically detects the ECG in the frame and then crops it to the bounding box of the ECGs to remove any backgrounds and clutter around the ECG. And the user selects the AI ECG model to run, and the model inference is obtained. The second pipeline is a single lead pipeline where the user selects an ECG to run the inference on. So these ECGs on our iOS app are from the Apple Watch ECGs. So we tunnel the ECGs through Apple Health and display it on our app. And then they enter the age and sex, because this is an ensemble model, and age and sex are two of the many parameters that are required. and then the model inferences run, and we also display the ECG metrics like QTC interval, the heartbeats, and heart rate variability. So how we engineered CAT scan? We took the validated models that were either in TensorFlow or PyTorch, and then we converted them into TensorFlow Lite and Core ML versions of the same model. So it's the same validated model. There was no retraining required or no optimization required. We just converted it into a different format. We also tested it to ensure that the accuracy and the fidelity remains the same. And the rest was building an app around it, the pipelines, the YOLO cropper to detect ECGs and auto crop ECGs to remove the backgrounds and stuff. So this app unlocks many uses. This can be used anywhere and without internet connectivity, so global deployments become easier. It ensures privacy because nothing leaves your device and everything is run on your device. And it's faster than the web applications because it uses lightweight versions of the model instead of the complete versions. And then it's very much scalable, and it can be deployed in research and clinical usage. And as for the next steps, first we are building out a larger model library. Currently we have the ATTR-CM model for the 12-lead ECG and the IDSHD for single lead. We are working on bringing in more models onto the hub. And we are also focused on cross-platform development. Right now it's only iOS first because of the tight-knit core ML and the neural engine accelerations available on the device. We are also working on integrating LLM on device. Apple recently came up with using the on-device LLM for our application, so we are working on integrating that. And we are also pursuing regulatory approval for clinical deployments. Yeah, thank you, everyone. I'll be at the poster session. In case anyone has any questions, please feel free to come up. Thank you.
Good morning. I'm here today to talk about Tumor Detect, which is a workflow efficiency tool designed for anatomic pathology laboratories that process thousands of pathology samples every single day. Concretely, Tumor Detect aims to optimize the clinical efficiency for high-risk patients who typically only represent about 10% of a typical lab's caseload. In the current workflow represented up top, pathologists in these labs typically review cases on a first-come, first-served basis. For malignant cases, pathologists need to order ancillary tests in order to complete and sign out the patient reports. If these cases are reviewed in the later half of the day, usually the earliest these report results are available are the next day, if not the day after next, which means patients at the risk of cancer often have to wait 48 to about 72 hours for a pathology report, which is unacceptable. But you can see that there's a simple prioritization problem to be solved here. In the Tumor Detect scenario at the bottom, Tumor Detect can run on a pathologist's lab's caseload overnight, such that when a pathologist logs in the next morning, they have a prioritized list of high-risk cases flagged by the algorithm for review. By reviewing these cases first thing in the morning, pathologists can catch what we call the ancillary testing window, such that these results are available the next day at the latest, if not usually the very same day. This drastically reduces the turnaround time for patients meaningfully. Tumor Detect itself is comprised of a set of different patch level classification models, which, given an input whole slide image, will generate regions of possible cancer among many others. The prevalence of these regions determines if or not a case is prioritized for review. Patient cases with possible cancer can be filtered for by a pathologist and be reviewed first. Furthermore, in these cases with possible cancer, the algorithm will also highlight fields of interest, helping focus the pathologist's attention on regions to review and assign a diagnosis to. This solves the critical needle in the haystack problem that pathologists are plagued with every single day in trying to pan around the slide and identify regions to focus their attention on. To evaluate Tumor Detect, we deploy it on nearly 1,600 patient samples comprised of both benign and malignant cases across 11 different tissue types. While we optimize for specificity, we maintain high sensitivity across all of these tissue types. But to really assess Tumor Detect's main value proposition, which is case prioritization, we run a simulation that's modeled after a real laboratory's caseload. So for this lab, we know the ground truth results for these cases. We know our own model's true positive and false negative rates. Using this, we can calculate in the unassisted setting versus the setting in which Tumor Detect is run, the difference between the time to first review for these malignant cases. To demonstrate, in this toy example, the first row shows the unassisted scenario, which is kind of chaotic with these malignant cases distributed randomly. On that same case list, in the second row, you see Tumor Detect's predictions, and in the third row, you see if that case list was to be reordered based on Tumor Detect's outputs. So we run this simulation about 10,000 times, each time measuring the difference in the time to first review for malignant cases in both these different settings. So what do we see? As you would expect, malignant cases are prioritized for review when using Tumor Detect. Quantitatively, because in the unassisted setting, the malignant cases are spread randomly across the case list, about half of those cases are reviewed in the first half of the day. However, when using Tumor Detect, that number jumps up to 71% of those malignant cases being reviewed in the first half. This, compounded over thousands of cases every day, over months and years, amounts to a drastic impact for patients at the risk of cancer. To conclude, we show that Tumor Detect not only decreases the time to first review for malignant cases, but it also increases pathologists' efficiency on those cases using fields of interest, model overlays to focus their attention. This is not just a proof of concept demo. This is a product that's live in multiple laboratories today, being deployed in thousands of different patient samples. If you'd like to learn more, please drop by our poster today afternoon. And finally, I would like to acknowledge and thank my co-authors, the members of the PathAI Pathology Network, and various internal teams at PathAI that make not only the development of this product, but also its adoption possible. Thank you.
All right. Good morning, everyone. My name is Samuel Kim. I'm from a startup called Only Health. I know it sounds a little like, we are the only health, but it spells a little differently. Only Health, we are building a medical coding platform specialized for the home health industry. Among the various features this product has, I, as an ML scientist or an engineer, I'd like to talk about a little bit of a ML aspect of this product. Before I start, I'd like to use this opportunity to introduce that we have openings. So we are actively hiring. So if you find this presentation interesting, or if you like my jokes, then please talk to me after this. I'll be at the demo table this afternoon as well. So medical coding in general is very important in various ways. But when it comes to the home health, you'll face different challenges. This is a list that you will face, you will face in the home health coding industry. Of course, this is not the exhaustive list by any chance. So the first is you will dealing with unstructured data. So documents arrive as a nasty, narratives notes. They are deeply heterogeneous, and most of the times they include the medical histories that are nothing to do with the current episode. And you're dealing with the very strict Medicare rules that will impact your reimbursement as well. Last but not least, you are dealing with the legacy tech. I was so surprised when I saw they still using the fax machines. I don't know if you know the fax machines. I think most of us in this room never seen the fax machine. I think it's right after the Stone Age that people uses with the floppy disk, right? So this platform actually try to expedite the process and ease in the process of the coders. So this platform, I don't think you can see the screen well, but this platform actually does the workflow shift. So this platform automates a lot of time-consuming processes of the coding process. so that the coders can spend more time in like verification or refinements of the process rather than scrolling up and down like, several documents. Each document has 100 pages. You don't have. I mean, the coders don't have to wrestle with a lot of documents, so that it can expedite the process. It also provides a very interactive UI, so the coders can confirm, reject, or add the codes based on the recommendation that this platform provides. And it also completes the ML cycle so that the coder's behavior can be used. Actually, it's being used to improve the ML performance of this platform. So this has a multi-stage AI pipeline. It consists of a ingestion process and a candidate generate processing, and then verification process. It is designed to maximize the recall and the precision of this the code recommendation. To be more specific, this candidate generation process uses a supervised machine learning method that no one is using these days. Everyone uses a ML, like LLM these days. But we have this pipeline, the candidate generation part in this pipeline, so that it optimized for the higher recall to capture all the potential codes. And then it follows by the verification process, which uses zero-shot verification against all the guidelines and then rules that I just talked about for high precision. This actually mimics how human coders do their job. So this is the numbers of the current AI platform that we have. So the left two figures show the histogram of the codes with respect to the recall and precision values. Take-home message here: it works pretty good, but in real world, it doesn't mean anything unless it actually helps the human coders, right? So this 88% improvement we had for certain types of documents. So this calls the presentation. So again, let's meet at the demo session this afternoon. Thank you.
Okay, hello everybody and good morning. My name is Mohammed Bahroun. I'm a master's student at Harvard Medical School, working with Pranav Rajwarkar. And with me is Siavash Raisi, also a master's student at Harvard Medical School, and Thibaut Heinz, who's with us in the audience. Today, we're presenting RADGame, an AI platform for radiology education. So RADGame, traditional radiology education is passive in the sense that people absorb information passively through classroom or textbook settings. It's unscalable in the sense that people require human supervision, and it's general in the sense that people receive the same feedback. Multiple people receive the same feedback. In contrast, in RADGame, we employ active learning, and the platform is scalable in the sense that it doesn't require human supervision, and is personalized in the sense that people receive feedback based on their errors. We do this by repurposing AI training material, which we define as material originally designed to train AI models like large-scale datasets and evaluation metrics. And instead of using these to train AI models, we actually use these to train future doctors. So RADGame has two modes that target the canonical tasks in radiology education. The first is localize, where people are taught how to localize different findings. The second is report, where people are taught how to write radiology reports. In localize, users are presented with a chest X-ray image and a set of findings that they have to select from. For each finding that they think is there in the image, they have to draw a bounding box and where they think it is. Their bounding box is compared to that of a board-certified radiologist from a public dataset. If their bounding box and the radiologist bounding box have an overlap of 0.25 in terms of IU, that's considered a match. Otherwise, it's considered a mismatch, and the users are presented with an explanation on how that finding can be seen next time in the image using MedGemma. So we use MedGemma to generate visual explanations of the features of that finding, so the user can learn how to spot it next time. The second game mode is report. In report, users are presented with a chest X-ray image along with age and indication to help them write a report. Then they write a report from scratch. Their report is compared to that of a board-certified radiologist from the REX gradient dataset. And we compare the reports using GPT-03. GPT-03 will categorize errors between the two reports across 4 different categories: false positive, false negative, misassessment of severity, and location error. These errors are used to calculate what we call a Crimson score, which is a score between 0 and 100. This score is calculated as the number of correct findings, which are findings that are matched or consistent across the user report and the ground truth, over total findings. Along with Crimson, which measures factual correctness of the report, we also report another metric, which we call a style score, that judges how well the report correlates with the radiology standards. And this is done by looking at systematically the regions, whether the user mentioned all of the important regions in a chest X-ray, like the heart, lungs, and mediastinum, along about whether the user writes in full clinical sentences and full sentences and uses clinical language.
So thank you for that. So yeah, over here on the left, you can see some examples of what the user interface looks like on the user's end. So on the left here, we have the user interface for RADGame Localized, where, like Mohammed said, a user is presented with a chest X-ray and a series of different findings that they can then select from to draw boxes for. They then receive feedback there on that second box. And on the far right there, we have the RADGame Report UI, where once again, a user is presented with a chest X-ray, except this time they're expected to also write a report in the text box. And on the very far right there, I'm not sure if you can see, it's a little bit small, but we have sort of like the aggregate Crimson score with all of the errors laid out for the users to learn from. So to evaluate the efficacy of RADGame, we also ran a multi-institutional, multinational study with 18 medical students. Students were split into 2 experimental groups. The traditional group traditional control group had students being presented with a chest X-ray, and then the ground truth sort of like findings of report overlaid right next to it, akin to something that you would probably find in a textbook in a more traditional sort of classroom setting. The experimental group, or the gamified group, had students having full access to all of RADGame's capabilities, meaning that they were receiving AI-generated feedback for all of their submissions. So to evaluate their baseline performance on these 2 tasks, we first gave them an initial pre-test, and then we asked them to complete a certain number of cases in each task in their respective modalities, and then we evaluated them at the end with a post-test. And what we found in our results is that across both game modes, students in the gamified group showed higher accuracy compared to those in the traditional group, sometimes by pretty high margins. And also, as students progressed through all of the cases that we gave them in each of these modes, the average amount of time that they spent per case decreased, showing that RADGame has the potential to hopefully improve accuracy and efficiency for medical students that are trying to master these 2 tasks. So that's all we have for you guys today. Thank you for listening. Our poster is going to be at the D4 booth, but we also have this QR code where you can actually access the platform yourself. We'll be giving out access codes at our booth if you're interested in trying that out and playing with it a little bit. But thank you.
All right, so we'll be going on to the next keynote. So today we have Julia Adler-Milstein. She's the founding chief of the UCSF Division of Clinical Informatics and Digital Transformation and a professor of medicine. As one of the nation's foremost experts at the intersection of health policy, health informatics, she has authored more than 250 influential peer-reviewed articles which have directly shaped federal and state policy, particularly around health system interoperability and AI governance. So if we could have those in the back right, if you can either step out or please sit down. All right, thank you, Julia.
All right, well, thank you so much for having me. It is hard to follow breakout sessions and coffee breaks because really you are all here to talk to each other, but I am thrilled to be able to be giving one of the keynotes. I fear I might be the only person in this room who has never actually developed any type of machine learning model, but I am really excited to come to talk to an audience that focuses mostly on that because I think we're at a moment in the field where it's time to connect the people who are developing tools with the people who really understand how to study their implementation and impact in real-world clinical settings. And so my talk today is really focused on that intersection and in particular how we close the gap between where our AI capabilities sit today and health system readiness to integrate those tools. But I want to start with a question for the group. So how many people in here have developed some type of AI tool? Okay. Expected the vast majority. Okay, so here's like an Oklahoma moment. I want you to be honest. I just finished watching Ted Lasso. I'm known like the last person on earth to have seen that show, but I now appreciate moments of truth. So for those of you who have developed a model, you're gonna have two choices. One is like, you wanna move on to the next model and make it someone else's work to figure out how to actually implement it in clinical settings, versus you yourself wanna take that model through to the end and see the clinical implementation and impact. Okay, so option one is really important, want that work to be done, it's just not my thing, versus nope, at the point I've developed it, I really want to go on to do sort of the next set of work to figure out how to get it ready for real world use, okay? So how many people are in camp number one? Okay, again, this is like our honest moment, okay? And what about camp number two? Okay, super interesting. This is the first time I've asked this question. I actually think it's really important to understand whether we need to start cross-training people in our field in both the discovery side of the science and the delivery side of the science. And given that most of you raised your hand for option B, I think this is the grand challenge that sits ahead of us, is how do we help people who have a lot of skills and backgrounds in how to develop AI tools to then learn the additional skills needed to get them ready for real-world clinical implementation and to be able to study their use. So with that context in mind, I was really struck when I saw one of my colleagues, Amir Dan Rubin, who some of you may know, present this slide. It really resonated with me. The concept that that AI is moving much faster from a technological perspective than people and processes. And so what we're seeing is this huge explosion of invention, right, where feels like there are new models and applications coming out every few seconds, and then to actually get them over the hump to diffusion. And for me, what this slide crystallizes is like, why? Why is that process so slow? If we believe these innovations are valuable, what are the roadblocks? What are the speed bumps that are slowing down that process of translation? And what's really clear is that it's just a whole different set of issues that you encounter at the point that you're ready to move to the diffusion phase, right? So this is where you have to start to get into things like, how do you change organizational behaviors? Are there like legal and regulatory issues that you bump into? How do we think about individual learning curves? And then issues of like, is this safe, right? What is your compliance officer going to say about whether this tool is safe or not? So again, a very distinct set of issues, and I will argue that the ones in yellow are actually really hard issues, and that we don't have smooth pathways for understanding how to address those. And so if we want to be able to really quickly take tools from innovation all the way through to diffusion, we need to develop, again, better pathways and strategies to tackle those issues. A second place where I saw this issue emerge is on slides like these that I see in talks that sort of array AI tools on two dimensions, technical readiness and market readiness. And I felt like I kind of understood what technical readiness is, but like, what is market readiness? Do we really understand what that means, how to assess it, right? How to determine whether a tool is market ready or not? Again, I think it goes back to this same concept of like a tool is a well-defined, well-crafted thing. We sort of understand what it does, but that's very different than understanding how to introduce it into a real-world clinical environment and all of the sort of challenges and barriers that go along with that. So I have no idea if this matrix is accurate. We could probably argue about what should go in what quadrant or not. But I think a lot of that has to do with understanding like what is market readiness and how do we assess it. And so that's, I think, part of this argument that I want to make to you today, is that like we need to be much more specific about what that means, how to assess it, and then how to remove barriers to market readiness of tools. So all in all, I and others have been calling sort of this set of work to advance clinical implementation of AI tools, health AI delivery science. I'm curious, how many of you have heard that term before? Okay, so not too many. I hope after today you will start using it because I think it's helpful for us to have common nomenclature around not just what we sort of will often call like clinical implementation or clinical translation, but there's a science to this work. Right? It's not just like figuring out who to talk to at a health system who will say, yeah, sure, let's try that. Right? There's actually like a science to understanding how to take AI tools and implement them into real-world clinical settings. But this science is pretty nascent, and there are just a few papers that have started to describe like what are the theories and methods that underpin health AI delivery science. What I want to talk about today is, I think, what are the big questions that I think that field of health AI delivery science should be tackling. I think some, you probably, if you're on the AI conference circuit, you've heard about before. So the need for AI governance, for example, and new roles that are emerging in organizations like chief health AI officers, right? That's one part of delivery science, is understanding sort of the governance structures and the leadership that's needed. But again, I think that's pretty widespreadly recognized in a widespread way that we need some of these roles and governance structures. We also talk a lot about issues around assessing AI for bias and drift. Again, before you're going to even really get to a real-world clinical setting, you're going to be asked to test that model locally and ensure that, that it's appropriate for that population. We also talk a lot about addressing an AI digital divide. What are the policy structures? What are the incentives that we need? So again, really important questions, but ones that I hear talked about a lot, so I don't need to sit here today and talk to you about them some more. Instead, what I want to focus on is questions that I think are really equally critical to closing the innovation diffusion gap, but don't get talked about as much. And for me, these are the exciting scientific questions for those of us who want to pioneer this field of AI delivery science. So the rest of my talk is just talking you through these questions. I don't have answers to them, but I think for those of you who are building careers, and I know that many of you out there are students, these are questions that I hope might captivate you as you're thinking about areas in which you might want to pursue your work. So the first question I think health AI delivery science needs to tackle is, what does patient engagement mean in this new era? And in particular, are we at a moment where two things are going to come together to transform patient engagement? So EHI stands for Electronic Health Information, and we've actually had regulations for many years that actually mandate that patients have access to every electronic piece of their data ever created. So any health system that you've ever been to, if you ask for an electronic copy of your health information, that healthcare organization is required to give it to you. But it may not be a surprise if any of you have ever tried this or have heard of others who have tried. Very hard to make any sense of this data, right? It can be just like a huge file, just for most people, totally uninterpretable. But now what we're starting to see emerge is that patients realize, well, if I can combine my electronic health information with a large language model, I can start to ask questions of it, make sense of it, and perhaps get to a point where I can actually better understand my health and how to act on it. And so I think the question is, like, are we ready for this era? How do we help patients combine their electronic health information with large language models? What are some of the safeguards? How do we also enable it? How do we help them ask questions in the most effective way? Are there other tools that we should be combining with this? I think it's sort of this watershed moment for patient engagement, but we need people to be thinking about how patients can most appropriately be engaged. I did a study quite a while ago when Apple Health Kit was first released, and we were like, this is our watershed moment for patient engagement, right? Once patients can get their records on their phones, like this is gonna break the dam open, and then every patient's gonna be interacting with their health information. It may be hard to see on the slide, but for the first 11 health systems that enabled Apple Health Kit integration, the best health system got just over 2% of their patients to ever use it. So that was not our watershed moment. But now we're starting to hear stories of what I think indicates that we are at this watershed moment. This is a seminar series that we run out of my division at UCSF called Innovations at the Intersection of AI and Diagnosis. We had an incredible panel where we had patients come for the first time to talk about, like, how are they using large language models in their diagnostic journeys. And there was many powerful stories, but one was of a mom whose child basically had a series of misdiagnoses and just an excruciating amount of testing that he ended up not needing. And she basically tracked down a copy of his record, put it into ChatGPT, gave him what ended up being the right diagnosis that then she took back to the healthcare system and resolved really within hours. So this is what gives me sort of a sense that we're at sort of a different era of patient engagement, but also that it's not going to be every patient that can do what this mother did, and so that we need to build an environment in which patients can figure out how to use this set of tooling to really advance their own health in different contexts. So the second question that I think is really critical for health AI delivery science to tackle, and this is one of, I think, the major roadblocks that we see at our institution, where we have a huge number of researchers who come and are like, we have this great tool, and we want to implement it, is that they don't really understand some of the capacity constraints that sit within health systems. And so as an example, we had one of my clinical informatics fellows who developed a lung nodule detection tool. Tool itself was awesome. We had no staff who were able to follow up when we detected lung nodules. And so not surprisingly, our compliance officer then said, well, no, you can't turn this on, because if we detect something that could be problematic for the patient, we then need to have the capacity to act on it. There are other examples of this sort of capacity constraint that have come up recently. So Vinnie Liu from Kaiser, who some of you may know, again, developed a suicide risk prediction tool, and then again ran into the same thing. How are their staff available to be able to respond, right, even in a more critical scenario? Another example from our county health system, Adam Yala, has an incredible tool that will identify at the point of a mammogram whether there's something abnormal that should be followed up on. But again, that requires the clinic to have capacity to see those people while they're still there same day. So I think we just see more and more versions of this problem where there's actually an incredibly good tool that provides useful information that meets some capacity constraints of health systems. So what we need is a way to identify and move upstream an understanding of those capacity issues, so that at the point that you've developed a tool, you can understand sort of the workflow, so to speak, of who needs to be able to act on that and understand if there's capacity in the system to do that. I think a close friend of capacity is authority. Right? So it's not just, is there capacity, but does the person who is leading the development and implementation of this tool, are they actually positioned in the health system to say, like, well, we are going to move staff from this need to this other need now that we have this tool in place. And so this is where it comes back again to sort of understanding the structure of the environment in which you want to implement an AI tool well enough that you can understand how sort of capacity and authority work in order to get that tool, again, implemented in a way that's actually going to be actionable. So again, some people have written about this, and I think, you know, again, it's the sense that if we give end users tools, but they don't have capacity to act on them, that really we're just creating frustration rather than value. If you look at different models that are out there for sort of assessing when it's worth investing in developing an AI tool, some of them point to these issues. So this is one of the models, the firm assessment. And what you can see here, sorry, the font is small even for me, is I think in this second category here, right, given the cost of the action, its benefit and work capacity, right? So it's just this one piece, work capacity. I wish that were in bold, because I think like work capacity is really the key thing to be able to understand. Because if that work capacity isn't there, it's basically you have no causal pathway from your AI tool being implemented to actually having an impact on outcomes. So again, I hope we'll see more of these frameworks in place, but with a particular focus on understanding this issue of capacity to act. All right, the third question is really about the optimal AI unit, and whether we are at a place, again, in the field where we understand how if we deploy not tens, not hundreds, but potentially thousands of different AI tools in the same clinical environment, like how are they going to interact with each other? And how do we think about what the optimal unit to which to apply AI is? So right now, if you look at the vast majority of tools that most health systems are looking at, they target isolated clinical predictions, right? I just gave you examples, right? Suicide risk, lung nodule detection, right? Abnormal mammogram. For any health system, right, there's probably hundreds of thousands of individual tools that might be relevant to the care that they deliver. And that becomes very unmanageable very quickly, right? We can't have sort of an AI tool for every piece of information that might be relevant to any given clinical decision. So what do we see? We now are seeing tools that are trying to sort of go up a level of applicability, right? And so they're taking like an entire clinical process or administrative task and then saying, how do we tie AI tools together to support that entire pathway? Again, not a whole lot of tools that are doing this, but I think it's the direction that we're seeing because of this issue of sort of too many isolated tools that aren't, that sort of, for which there's just limited capacity, right, for a health system to work with them. But ultimately, where I think this is all going, right, is that these tools need to be able to understand properties of the system, right, and how different aspects of the system work together, so that you can support sort of chains of information needs, whether that's information seeking, summarization, agentic pieces, and for that, I think the big question that raises is like, are we heading from today's world of sort of largely isolated and controllable clinical prediction tools that humans are more than often than not in the loop on, to sort of a totally flipped version of that, where it's really a closed loop autonomous AI system that's managing individual and population care? Because the complexity will just be too hard for any human to be able to react to all the different AI inputs. And so instead we have to say, like, this is a property that the AI system is best left to address. And again, I love this diagram because I think if you were asked to like really map out like how do health systems deliver care, like it is beyond the complexity of what any human can really understand, right? There are so many inputs and outputs, and understanding all the different relationships between them is extremely complex. And as again, I think is sort of beyond the capacity of any individual to understand, which then makes it hard to understand how to introduce isolated tools into that environment. So this is, I think, both a good thing and a scary thing. The scary version could be, is there a system that then allows a CEO to say, I want to increase profit by 10% next year without compromising the quality or safety of care as we provide it today, right? And then you could imagine a system that reallocates patients and rooms and, right, I mean, the whole workflow that stems from that. Again, depending on where you sit, that could be like a dream tool, or that could be like a total nightmare of a tool. But I do think that this is where, right, like eventually these tools are going to head, is that they'll be able to understand how all the different parts of the health system relate to each other, and then be able to use different layers of AI intelligence to be able to sort of direct human resources to be able to optimize over different outcomes. I haven't seen like this exact version of a tool out there yet, but we are definitely starting to see companies that are coming to us and are basically like, we can take over your hospital and for sort of 1/10 the cost of your current human capital, basically deliver the same level of care. I personally don't believe it right now, but I think that like in a not too long of a time, we'll be able to start to see demonstrations of how close these really system level AI solutions are to being able to both understand and then optimize the way that again, human and other sort of complex and expensive resources are deployed, and again, flip the script from sort of us saying what we want the AI to do to AI telling, you know, a health system what they should be doing. Okay, so again, I think this question of like, what is the optimal AI unit, how the units will interact, and are we headed towards system level AI is the third big question. There's a lot of really interesting things that I don't have time to get into today about sort of how the whole electronic health record developer market power is playing into this. I think it's very hard for new innovative companies to break into this space right now. I'd say that's more of a policy issue, so I'm not gonna cover it in as much detail today, but I think it's hard to not at least mention it because these dynamics are also, I think, influencing the questions of what types of AI tools are deployed and at what units of scale and with what degree of coordination. Okay, question 4 is really around ongoing AI monitoring. And again, I suspect many people in this room are thinking about different methods for this, and I think it is going to be sort of the critical functionality that we need to develop as rapidly as possible. Right now, we're spending a huge amount of time sort of vetting and piloting and like retrospectively assessing and then prospectively assessing each tool as it comes through. But most AI tools are going to spend just a fraction of their life in sort of that initial phase of testing, and they're going to spend 99.9% of their lifespan in a phase of needing to be monitored. And again, this is like, there's many dimensions to what good monitoring looks like. So this is our AI oversight process at UCSF. And again, you can see in like the very bottom corner is like monitoring, right? But I actually think if this were represented in terms of importance, that would be like the dominant part of this whole AI governance process. So we have been working to just try to start to articulate like what are the different dimensions of AI monitoring that we feel like we need to have in place at our health system. Again, different health systems I think are all working on this, some version of this in parallel. And so I'm excited at the point that we can sort of have a platform to all share our models and get to some kind of a best practice. For us, this has like a real-time monitoring dashboard where we can see all the different AI tools that are in place, be able to visualize the key metrics that are relevant to those tools, and be able to identify when a model is out of bounds on some dimension. But the key and hardest part of that is like, then what is the action to take? And I think, frankly, that's where we're stuck right now, is like we can come up with the measures, we can come up with some guesses on sort of what maybe an out of bounds value of that measure would be, but then we're like, so then what would we do about it, right? Do we take the model offline? Do we do some kind of like forensic investigation? Like how do we actually pinpoint the issue and like whether it's a good thing or a bad thing? So again, I think a lot of work to be done around that sort of actionability piece within this framework of AI monitoring. There's also, again, a whole sort of technical infrastructure that sits under monitoring, so a data integration layer that we need, again, especially if you're using AI tools that are coming from different sources. We also are doing some, some sort of metadata work around hosting an AI model repository and the governance and compliance piece. So again, like how do we store versions of AI models and their history as they evolve over time? Do we use internal or external benchmarks? Again, documentation of compliance and governance that sits around each of those models. And then we have a lot of different audiences that are interested in like the reporting and analytics, right? So some of them are our clinical stakeholders whose budget is paying for that tool. And they mostly want to know, like, did we get the value that we thought we were going to by investing in this tool? And then we have a whole different group of stakeholders who are really worried about sort of the safety, trustworthiness, equity issues. So that's a different set of metrics that they want to see. And so we're trying to articulate all the different audiences that want to see the reporting and analytics around AI monitoring and help them be able to see the data they need. And then there's just a whole coordination layer, again, because AI tools are touching so many different types of stakeholders. And then we have a whole group of researchers who are interested in working on implementing and studying these tools. And so a lot of the work is just the coordination between all these different types of stakeholders. So we started this AI monitoring process with, I'd say, a very academic approach where all the stakeholders were at the table, lots of opinions, we did a literature review, and I think for the first tool that we applied this to, which was to monitor our AI scribe, it worked well, but it was clear that that process was not going to scale. And so for AI scribe, right, we have this whole dashboard, we have the metrics, all those things that I described. And so the work we're doing now is really to figure out, like, how can we distill that down to its essence? Like, what is the minimum essential that we need to do for monitoring? And then how do we rapidly scale that up? So again, I think this was like the Cadillac version of monitoring. We did it for one tool. We sort of know what that looks like, but now we need to get down to a much more sort of simplified approach and framework. But as I said, I think the hardest part of this is like the actionability piece of AI monitoring. Who should we alert based on sort of what criteria, and then what would they do about it if a model or set of models isn't performing in the way that we expect? So again, for those of you who are working on this, like, I would love to know what you think is the best approach out there, because it's, I think, been hard for us to figure this piece out. Okay, last but not least, I think a key question for health AI delivery science is really about this question of what does it mean to have an AI-ready workforce? And again, we talk about this a lot in the clinical setting. You'll see curricula like these, right, that it's like for family medicine doctors, you can go take a whole module that explains what AI is and how to use it. And then others that are more about, like, if you want to use AI in diagnosis, here are things to know. So I think we have some good sort of curriculum out there for those who are interested in upskilling around their understanding of AI. Some of the harder work here has been questions around, do we let our trainees use AI tools? And again, as we're training people to be clinicians, we expect that they will have demonstrated a certain level of proficiency that doesn't rely on technology. But this is really starting to be tested in new ways. We say, well, if these tools are out there and they're going to have them available to them to practice with for the rest of their careers, why would we not give them to our students? And so where I feel like we are is we're caught in this cycle of like, are these tools upskilling tools or are they de-skilling tools? And like we literally go around in circles. We're like, these are upskilling, this is de-skilling, this is upskilling, this is de-skilling. And I think the only way out of this cycle is that we actually need to be able to have agreement on what it means to be skilled. And we need to be able to measure it. And so really the answer is like, this is an empirical question. And what I've learned as I've started to do this work is in like the medical education world, we actually don't have a great measurement framework and way to evaluate clinical competencies in areas like clinical reasoning. And so I think these technologies are really putting pressure on all of the ways that we assess and give feedback to our trainees, because we can't then figure out if these tools are upskilling or de-skilling them without some way to measure whether they are skilled or not. So again, for anyone that's interested in like how we measure things, this has been such an exciting era because there's a million different things to measure. And I think at the heart of health AI delivery science are really measurement questions and how measurement meets the real world in all of these different contexts, whether it's patient engagement, whether it's sort of how health systems are safely and effectively deploying AI tools, or whether it's sort of what the future of medical education and training look like in a world in which AI tools can do a huge part of the clinical reasoning work for them. So I will just end there. I hope that this has been stimulated some of your interest in this concept of health AI delivery science and some of the questions that I think are really exciting to address as we move forward, and that groups like you, who I now know are interested not just in building models, but in actually getting them into real-world clinical settings, will work with me and others on addressing. So thank you so much.
We have time for 2 questions.
I asked 5, you only have to ask 2, so.
Thank you for a great talk. I have a question on your last question on upskilling and de-skilling the AI-ready workforce. Have you thought at all about kind of how these questions are being asked outside of healthcare? Because I know like in education, they're kind of like a lot of areas are kind of dealing with the same thing, which is like, okay, our students, are they actually learning or are they relying on the AI and stuff like that? So I'm wondering kind of what your thoughts are on that.
Yeah. No, it's a great question. And I think there is a lot to learn from different sectors. I mean, the bit that I've looked at in education, again, I think they have many more sort of common rubrics and standards for sort of educational assessment. So then it's easier to tell sort of whether use of these tools are helping or not against those. So I actually think that's where we, you know, if we can import some of that, we'll have an opportunity. But also say that like, I think all of us are in this, you know, it's like how much experimentation can we do in a way that feels safe? And so I think that that's the hard part right now is that, you know, someone who graduates from UCSF, we still have to say this is like a fully trained, you know, doctor or nurse or pharmacist. And so how can we introduce these tools in a way that still gives us the confidence that we can say that at the end of their clinical training?
Just wanted to ask you about the level of, I guess, AI readiness or reporting and analytics readiness that, you know, any healthcare system or community hospital who wants to onboard must have in order to get there? Or like, do you think it's going to be possible to jump from, you know, kind of no or limited reporting and analytics at baseline to like actually the full impact pipeline that you showed us?
Yeah, I mean, I do think that over time, like I think as with many things, like the, you know, well-resourced academic sites will probably be the groups that develop them. And then, I mean, we already see commercial tools that are out there that do versions of AI monitoring and that, you know, are accessible at a, you know, I think reasonable price point. So I think we'll sort of see a traditional approach in which, you know, right now it's limited to certain institutions, but I think it will become commoditized and democratized, and that will allow other institutions to catch up. I think the risk is like, will there be harm that happens in that gap? And is this a place where we need policy intervention to sort of avoid or shorten, you know, that window? Again, I think most places that I've been, like, are at least thinking about this and are trying to figure out like what is the right tooling. But as you said, the resources are limited, and so I think they're doing the best they can, but we do have to close that gap. Okay, thank you so much.
All right, this thanks Julia again for the excellent talk. Okay, so the final, or the second perspective today will be from Sherri Rose, talking about machine learning for health should consider social drivers of health. Sherri is a professor of health policy and director of the Health Policy Data Sciences Lab at Stanford University. Her research is centered on developing and integrating innovative statistical ML approaches to improve human health and health equity. Within health policy, Dr. Rose works on ethical algorithms in healthcare, risk adjustment, chronic kidney disease, and health program evaluation. She's published a lot of papers and wrote a book on ML for causal inference and has won a lot of awards. And she couldn't make it here today, so we have a video recorded from her for us to ponder. Here it is.
My name is Sherri Rose, and I'm delighted to be sharing our perspective piece, Machine Learning for Health Should Consider Social Drivers of Health. I want to thank the organizers and the board for the invitation to submit this perspective piece for consideration at ML for Health. And I also want to start with an acknowledgement of the intellectual leadership of the first author for this piece, which is computer science PhD student Neha Srivastava, for her brilliant ideas and stewardship of the work. We all know that algorithms are pervasive in health and healthcare, and that they can also cause harm. We have many different types of data in health and healthcare as inputs into different types of algorithms, which can include ML and AI algorithms like those being examined at ML for Health, as well as simple checklists and standard regressions that are also used in practice in the healthcare system. But the ultimate goal here is to have outputs that are clinically or policy relevant and have those results inform decision making. However, these algorithms can have negative impacts on marginalized groups. We know that there are many different types of groups that are marginalized by the healthcare system, including racial and ethnic minorities, disabled individuals, individuals living in rural communities and lower SES communities, as well as individuals who are uninsured, among others. These groups already experience lower life expectancy and poor health outcomes. Algorithms could more frequently be contributing to health equity rather than harming it. Therefore, when we look at the impacts of clinical machine learning, we know that algorithms can exacerbate social injustices across societal domains and levels. Some examples include systematic underdiagnosis for minoritized groups, ruptures in institutional trustworthiness, and environmental and ecological degradation. However, our current evaluations typically emphasize individual impact and responsibility, as well as biomedical ethics principles, leading to an emphasis on fairness, bias, safety, and privacy. And to be really transparent, a lot of my work has also looked at these issues, in particular, fairness and bias. That said, this narrow focus can underemphasize systemic harms, power imbalances in the distribution of harms versus benefits, and the reproduction of inequities. Our piece, therefore, aims to center social drivers of health, SDOH, and why are we doing this? We want to link algorithmic harms and social conditions producing health inequities. Our contribution proposes a mapping between algorithmic harms and SDOH frameworks, so the correspondence between these frameworks. We highlight that neglecting SDOH leads to ML systems that worsen health inequities, and that SDOH frameworks can enable more accurate and comprehensive harm assessment, as well as equity-oriented design and evaluation. Overall, we're arguing for comprehensive consideration of SDOH in the conceptualization, creation, evaluation, and use of clinical algorithms. Before introducing our correspondence framework, I also want to situate us in definitions of SDOH and the SDOH framework that we'll be working from, as well as a taxonomy of algorithmic harms that I'll get to in a moment. So when we talk about SDOH, we're considering the non-medical factors that impact health outcomes and disparities. We can look at structural SDOH, which are upstream factors that generate social stratification. Examples of this include public and social policies, cultural values, and income. We can also examine intermediary SDOH, which are downstream factors that directly influence individuals. Examples of this include the healthcare system, living and working conditions, and food availability. All of these different types of SDOH have an impact on health outcomes and inequities. And this is the SDOH framework from Solar and Irwin 2010. The taxonomy of algorithmic harms that we examine is from Shelby et al. 2023, where we look at representational harms, which is negatively stereotyping, erasing, or alienating social groups, allocative harms, inequitable misallocation of resources and opportunities, quality of service harms, alienation and lower quality of services experienced by minoritized groups, interpersonal harms, impacts to trust, trustworthiness, privacy, autonomy, agency, and empowerment, and social systems harms, harms to broader social structures, including environmental, political systems, and cultures. So what we do is we bring together this correspondence between socio-technical, algorithmic harms, and SDOH frameworks. So we give some examples of algorithmic harms illustrate these. With representational harms, one of the examples we demonstrate is race adjustments in predictive algorithms reifying harmful race-based medicine. For allocative harms, one that we include is a diagnosis algorithm that underdiagnoses minoritized groups. Quality of service harms could include NLP that misinterprets symptoms from patients with diverse language backgrounds. An interpersonal harm could be an automated risk score in the EHR that causes stigma and patient disempowerment. And then a social system harm could be model training that contributes to carbon emissions impacting public health. Now, we have many more examples in our paper where we show that a range of algorithmic harms ultimately impact health through SDOH factors. Now, this creates a tension in ML for Health, where we now have that health ML introduces novel structural inequities impacting health. But this work is intended to improve health, but it can often worsen health inequities via SDOH. So this is in contradiction to the purported goal of ML for Health. A key issue is that in machine learning for health is the unequal distribution of harms. So here we have harms versus benefits are distributed unevenly, and communities already experiencing adverse SDOH are most likely to experience algorithmic harms and can often not benefit from health ML due to the material realities of their healthcare infrastructures. So we propose an SDOH conscious algorithmic praxis modeled after a recent paper by Kazanchi et al. 2023 calling for a racism conscious praxis in medicine. And in our SDOH conscious praxis, we suggest ways to engage toward identifying underemphasized socio-technical harms and envisioning socially conscious and equity promoting algorithms where this is possible. And you'll notice this asterisk where I've stressed that an equity promoting algorithm may not exist. And so when we're envisioning equity promoting algorithms, we know that health algorithms can materialize inequity, but they can also be intentionally created to materialize health equity through considering SDOH. And when we talk about creating equity promoting algorithms, we can think about integrating SDOH and algorithmic design and equity promoting resource allocation. So one thing I want to stress here is that this does not mean simply adding an SDOH variable in an existing algorithm or a new algorithm and expecting that to be equity promoting. Often this does not actually lead to equity promoting algorithms, as it can just reinforce an unjust equilibrium by including that SDOH variable in the algorithm itself. But we'll come back to that because there's ways to interrogate that about when that would be potentially appropriate to do and when it might not be. But we do include some examples in our paper from the literature about creating equity promoting algorithms that have already occurred previously. One of those examples is from prior work in the lab, where we looked at a health payment algorithm in Medicare where we proposed resource redistribution given structural and social disparities. And I wanted to just briefly note that another thing that we considered here is that in order to have impact on social and structural systems, this doesn't just stop with the research. And so we also created, in collaboration with Stanford HAI, a policy brief for policymakers and community engaged practitioners and other individuals who wouldn't otherwise find the research article, or maybe the research article was not written in a way that was accessible to individuals who are not part of the research ecosystem. And so that was something we prioritized with that work as well. But so let's come back to the idea of what it means to consider SDOH and what those types of actions can include. So equity promoting algorithms alone cannot address root causes of inequities. And while using SDOH to design equity promoting algorithms, we must simultaneously avoid normalizing inequities. So that again can include things like thinking very critically about whether including SDOH variables in an algorithm is actually equity promoting. And examining non-algorithmic structural interventions upon root cause factors. So one thing I also want to emphasize here is that we need to be really careful not to divert resources away from intervening on the root causes of inequities for an overinvestment in so-called AI solutions that will not actually promote equity. Additional actions that consider SDOH can include not building the algorithm at all, as I mentioned earlier, and dismantling existing algorithmic systems. Sometimes an algorithm is not going to be the solution to the problem. It's actually exacerbating the problem. Now, along with structural analysis, community-based approaches can illuminate the social and structural factors that contribute to inequities. And so when we consider community engagement, we can identify SDOH and their interrelationships guided by those who are most impacted. And through impacting social systems, through impacting algorithmic systems, communities can claim agency to represent themselves and influence systems that impact them. Our paper includes a number of recommendations, which includes curriculum on structural analysis, systems thinkings from the community engaged literature, and community engaged approaches in applied ML courses in order to develop competencies in these areas. We also recommend collaborating with offices of community engagement where those offices exist in your institutions, as well as following community engagement best practices from the literature, particularly the community engagement literature. And I want to stress that this is often going to involve collaboration with scholars and community practitioners who are already experts in these areas, because it's essential that when we're doing community engaged work, that it's conducted in a non-exploitative and in a non-extractive manner. And we discuss more about this in the paper. I also am including here some brief extended recommendations, because when I talk about this topic with other scholars, there's a number of things that that often comes up in response. And so I think broader recommendations include just deep engagement with the applied context. For example, the analysis of those structural causes. And so that means we need to continue moving away from toy examples in our machine learning papers. I also have crossed out here least publishable units. It was already years ago, it was already functionally an impossible challenge to keep up with the literature. And many short papers often, producing many short papers, these least publishable units often does not allow for the kind of deep engagement with the applied context that we're talking about here. And we want to focus on incentivizing fewer, better papers and disincentivizing least publishable units. But that would often mean that we need to realign incentive structures. And so if we value this type of work, which I would say is broader than the SDOH context that I'm talking about here, our incentive structures need to recognize this emphasis on fewer, better papers. And I want to close with an example of this type of work of doing community engaged participatory causal modeling of social factors. This was a study that took 2 years to develop and conduct and was led by recent PhD graduate from the computer science department here at Stanford, Adler-Milstein, and Neha Srivastava, where we worked with a group of chronic kidney disease patients to co-create a causal model using community-engaged research practices to represent how SDOH factors impact chronic kidney disease progression. And this was a collaborative effort with the Office of Community Engagement here at Stanford, including Director Lisa Goldman-Rosis, who is a co-author on this work. And you can see the causal graph that we co-created here. The creation of this graph can lead to the inclusion or non-inclusion of SDOH variables into clinical predictive algorithms. Again, we must include analysis of structural causes before considering including any of these SDOH in the algorithms to avoid reinforcing an unjust equilibrium. Can also inform institutional efforts to collect SDOH data, as well as the development of technological and non-technological interventions. I want to close with some acknowledgements. We want to thank all of the individuals who gave us feedback on this perspective piece, as well as the Health Policy Data Science Lab as a whole and all the individuals in the lab at Stanford who gave us feedback. We also want to acknowledge our funding. Both Neha and I were supported by an NIH Director's Pioneer Award. And I want to close with another acknowledgement of Neha's intellectual contributions and leadership on this perspective piece. I'll additionally highlight that she co-created these slides that I presented here today, with many of them representing her vision. Neha is here at ML4H, and I thank her for representing us at the conference. Thank you again to ML4H for the opportunity to share our work.
I'm excited for us to start the clinical implementation of AI panel today. So I'm going to go ahead and introduce our panelists and our moderator. Karandeep Singh is the Joan and Irwin Jacobs Chancellor's Endowed Chair and Associate Professor of Medicine and Biomedical Informatics at the University of California, San Diego, where he also serves as the Executive Director of the Jacobs Center for Health Innovation and Chief Health AI Officer for UCSD Health. In these roles, Dr. Singh oversees AI strategy, operations, and governance for the health system and has patient care responsibilities in nephrology. Dr. Anna Goldenberg is a professor in the Department of Computer Science and the Laboratory Medicine and Pathobiology at the University of Toronto. She's a Varma Family Chair in Biomedical Informatics and Artificial Intelligence at Sick Kids Research Institute, as well as CFAR AI Chair at the Vector Institute. She co-chairs the research arm of the Temerty Center for AI at U of T and co-leads Sick Kids AI Services. Jonathan Chen is the Stanford Director for Medical Education and Artificial Intelligence. He leads Clinical Informatics Research Group to empower individuals with the collective experience of the many, combining human and artificial intelligence to deliver better care than either. Dr. Chen continues to practice medicine for the concrete rewards of caring for real people and to inspire his work to advance not just the science and technology, but to redefine how we train and retrain an entire generation of the healthcare workforce to safely and effectively integrate intelligent systems to reach all patients in need. And then finally, our moderator, Jason Fries, is, as of yesterday, an assistant professor of biomedical data science and of medicine at Stanford University. He holds a joint appointment in the Department of Biomedical Data Science and the Department of Medicine's Division of Computational Medicine in the School of Medicine. His research focuses on training and evaluating multimodal foundation models for healthcare at the intersection of computer science, medical informatics, and hospital systems. So we can go ahead and get started.
All right, yeah, round of applause, please. So we have quite a set of luminaries here when it comes to thinking about how to deploy models in the hospital and more widely. So I want to start with a definition question. What is a deployable model in the estimation of this panel? What characterizes it versus any other AI, ML model writ large?
That's a tough question, because I think in principle, anything is deployable, but I would say that it's the amount of human effort required to actually do it, and the political capital required to get something actually implemented. And many times a model is like a lot of work to do, things that are like, oh, but there's such a obvious benefit to doing it. I would say the early implementations of AI Scribes were this way, where most systems hadn't signed these big contracts outside of their major EHR vendor, but because everyone was aligned, we need this, they were willing to lift, a boulder uphill to make it happen. So I don't think there's anything computationally that makes something not deployable, especially in the world that we live in today, and where APIs are a thing. I think it's more, a deployable thing is something that can be deployed. And I think that a lot of that is actually political capital and human effort involved that will drive, is something actually going to be deployed.
I guess I want to bring in the distinction that we are not deploying models, we are deploying AI interventions or AI systems. At the point of deployment, it's usually not just a model, it's a way it integrates into existing IT or another system, the way it interacts with a human. So what is the human-computer interaction component of it? So the continuous monitoring, which is a part of the intervention, is also there. So a model becomes deployable when it becomes a verifiable monitored system and tested, right? There is a way to prepare that system and integrate it, and then there is a trial, could be a silent trial for something very low risk, or would be a full-on RCT if it's something very high risk, and a process during which we actually verify that this model is, this intervention now, AI intervention, AI system is actually ready to be and safe to be used in the wild, in the real world.
I'll try to have more hot takes to keep things spicy. A couple things. What are we talking about? Are we talking about prediction models? Because I don't even think that's AI, and it really annoys me when people call that AI. But the JAMA review paper did not believe my peer review, and they still just use this marketing buzzword. Deployable, do you guys know what MD-Calc is? I guarantee you every doctor knows what MD-Calc is. It's a website with a bunch of online risk calculators. So a very basic prediction model. There's no RCTs that prove this thing's useful, but it's like the second most used clinical decision support tool in the world because it was just useful. He didn't integrate with health systems. He didn't get a venture capitalist. He just made something useful and people want to use it, and it was very beneficial. So there's a lot of academic scientific studies we should do to validate whatever we can. For better or worse, a company just has to sell something, and if somebody's willing to buy it, then it can go that way, and it matters whether it affects what they actually do in their work.
Follow up? Yeah, no, follow up, yeah.
Just sounds dangerous what you said, but I'll give you a microphone back.
I didn't say it was safe. I'm just describing what is your intention. Do you want to be safe and responsible and ethical? I'm glad if you are. That's not what a lot of companies are optimized for. They're optimized for profit. And our health systems are often very complex incentive structures that do not make sense. They really don't. And when you break them down, what our actual incentives are.
You think the role is in terms of, when do you need to engage in these longer term workflow questions, validation questions before even conceiving of deployment? Like, model building is now very deeply tied to how models are used. And so where in building a new useful tool do you have to interface with the people that will be using it? And what does that mean in terms of actually deploying stuff in practice?
Hot take again, depends on who you are and what your incentives are. If you're a PhD student and you need to crank out more conference papers, who cares if it gets deployed? It'll probably take 4+ years for that to actually happen. You could have cranked out 10 NeurIPS papers in the meantime, and that is a better incentive for your career. But do you want your things you build be used by real people and affect real patients? I'm a doctor and I care about that, but you might not. You really might not. You don't necessarily need to. We need all of you to do different things. But if that matters to you, you better understand it very early on because it's so easy to make prediction models that predict things that nobody cares about.
I agree. If you can crank out 10 NeurIPS papers in 4 years, please do that. I think we definitely still need a lot more just core research. This was part of our roundtable to encourage people. It's not all about deployment. Not all AI in healthcare needs to be deployed, and there's still a lot of benefit from it. So there is space. There's definitely space for both. But if you want to deploy, I think being thoughtful about it without necessarily putting in some insane impediments like doing RCT on, I don't know, on a scribe. I don't think you need an RCT on a scribe, but that's my personal opinion. But it's a choice one makes, but it doesn't need to happen everywhere. But there is a safety and efficacy consideration that definitely needs to be present in some shape or form to deploy AI.
I think you can look at this from two lenses. If you're, I have a health AI lab that I run at UCSD. I also oversee AI for the health system. For the health AI lab, we actually are an AI implementation science lab. We study the stuff that's getting deployed. So I think there's often this assumption that you need to develop the thing that you're deploying. That I would say is universally probably not true. A small fraction of what stuff that gets developed by researchers does get deployed, and that's why researchers view that as an AI implementation gap. I would say there's another half to that, which is stuff is getting deployed all the time, and it's not coming from people's research labs. It's coming from companies, coming from the HR vendor, coming from other places. And so I think there's actually a lot of rich science you can do around stuff that's just getting deployed. And the nice thing about that is actually that that's actually where a lot of the really cool questions are, and where actually it's most proximal to where you fix something, you see patient benefit. So I think that I would just say that definitely, the points are great that if you're a PhD student in a CS department, it actually may not make any sense for you to get deep in a deployment because the length of a deployment might be longer than the length of your PhD. But I think that for health systems that are smart, the answer would be, I wouldn't deploy anything without talking to the end user. That end user is often not even a physician. In some cases, the end user is a leader who's got a workforce whose stuff you want to automate. Like really, it could be all over the place of the stuff that you're trying to do. But I think that if you're going to sign a contract, you're going to do something, you want to make sure that you don't do all the work and find that there's no one on the other end to receive it. And even as an operational leader, there's still someone on the other end to receive it.
I wonder if you could double down on that interesting, I like that perspective. That I just think on my bias, of course, we need really smart people to understand. There's the things we deploy, but does it work? What are the unintended side effects? How are these complex interactions happening in conferences? You really need to have a lot of smarts to break down a much more complicated problem than an RC curve analysis. However, if you're a computer science student, aren't they much more optimized towards they got to build the next cool foundation model, and that's how they make their name? What's more fun? What's more cool to do?
So I've got PhD students in my lab studying this stuff, and so I think the real question is what's the next job for them going to be? And I think that there is notwithstanding like other groups like AMIA, where there are a lot of folks interested in AI deployment as a primary goal, I would say that there is still a gap of folks who understand AI implementation science. And I don't mean the necessarily rigorous RCT prospective stuff. I mean if you're at a university or at an institution that's linked to a health system, if I were to ask you, and feel free to raise your hand, how many of you have a patient drafted or AI drafted replies to patient messages implemented in your system? If you don't know the answer, it's okay. But I would say, I would wager probably half of your systems actually have that implemented because it's so easy to turn on that many systems have just implemented it. When a physician uses it, does it save time? Multiple people, including groups at UCSD, Stanford, have found it doesn't actually save time. So the next implementation question you can ask is, well, what the heck does the physician edit when they use these tools? What makes them decide to use an AI-drafted summary in the first place? That is actually a rich area of AI implementation science. The sort of professionals who are right at that intersection, I would say the people interested exist. there is a big gap between folks who do operations and folks who do research. And unfortunately, that gap means that those kinds of intersectional questions, there's no one studying them because there's no one who even knows about those kinds of things, nor do they have access to data. I mean, I think the issue was, I was interested for a long time and had a lot of challenges in my prior role getting access to that kind of data because that was viewed as operational data, not research data. But I think there's a lot of those kinds of things you should be asking. Don't worry about if it's feasible. Ask the question, and then usually there's often a way to get to data when actually it's viewed as a, like, oh, we're spending X thousand dollars a year on this thing. We can probably make it better if we can study it. Is it okay if we spend a little bit of work doing that? Can you get us some data? We can probably make it so that your rates go up of usage. That's the kind of science that will have an operational impact, but I think is still interesting as a CS student with the right mentorship and the right career trajectory.
I have a question for you. Sorry, moderator, we took off. I have a question for you, and I have a suggestion to the audience. So around deployment, there are many more questions than just seeing if the tool works. There is evidence, our lab published and others, that tools have a tendency to deteriorate. This is a tool that has a feedback loop of the label becoming what the tool predicts. So it looks like the system keeps improving, but it's just sort of stepping into its own and increasing its own bias. So how do we make sure that post-deployment, and once it's been running for some time, our tools are actually still improving as much as they could be? That question has not been studied very well, and that's a online learning question. That's a core machine learning question that I think could be addressed. Now, the question for you is, when a PhD student is studying, maybe it's a vulnerable question, when a PhD student is studying how well the systems predict, what is their trajectory afterwards?
My answer will be laced with a ton of survivor bias. Because I think that as I stepped into each one of my roles, I really feel like there was not a precedent for what I wanted to do. And I think that's probably most of our experience here on this panel, is that most things we wanted to do, at the time we wanted to do them, there wasn't like a established career path for that. There are programs in implementation science. There are programs in learning health systems science. There are programs in clinical informatics. And so it's not that I think like a new trajectory needs to exist. What I do think needs to exist is CS people, I think, are some of the most talented people in understanding the depths of what's actually happening. And I think that to the extent that you want to be in healthcare, just take a pause and get deep health system expertise. If you're going to do health system work that has health system implications. That may be a small percentage of people. Most clinicians don't have that. Most clinicians are like, like I'm a nephrologist. I could have done nephrology AI, and like all my stuff would be about like, the kidneys and like, this electrolyte thing or that electrolyte thing. And that's where I started my career a little bit, was playing around with like electrolyte-based math. And kind of, that was what brought me to nephrology. But if you're interested in, I think, solving a systems problem, you need systems training. And I think learning health system science is a thing. And so I think that we need more CS people to say, I want to do that. Or even like there's administrative fellowships in healthcare. Most people who go on to become healthcare leaders do like a 2-year administrative fellowship. Many folks do. They probably have no computer scientists who apply to that kind of a role. I would say like those are the kinds of things where get yourself into the problems where you just start to see them. Any problem that you can viscerally start to understand, you probably have the tools to tackle. And one really nice thing about CS people is, unlike people who go through medical training, people with CS actually see problems inherently as solvable. I think in healthcare, that gets beaten out of you sometimes, that you just see it as that's the system. But I think CS people have that kind of fresh thinking, and I think that, but where they struggle is sometimes they don't understand the system whose problem they're trying to fix. And so what they think are the incentives for the system often are not. And so I think just, it may be a partner, it may not be, you need to be that, and know where your expertise ends and where your colleague's expertise begins. I'd love to get your take on it as someone who just joined the faculty.
Why would you do that? Oh boy.
In terms of like what skills we need to instill and like incentivize students to research operational problems, is that kind of what's your question?
Close to core computer science.
Yeah, I think there's the grand challenge, I guess, is incentivizing computer scientists to get interested in these operational problems that are unfortunately behind a barrier of data frictions and access. And that is sort of anathema to how CS operates. And so there's this kind of slow patience quality to get to accessing data sometimes, or understanding the problem enough to be able to envision real solutions. And I think it is the responsibility of people who have kind of gone ahead to envision what a curriculum needs to look like and to lower barriers to make data accessible in a safe way. And I think it's kind of a framing mixed with incentive problem, I think. Because I think the magic of LLMs is it's made the user so center to how we conceive of the models having impact, how we train them, how we align them to what they want to do in the world. And that requires a primacy to the user that's very difficult to achieve in medicine. And so there's this, you basically are shadowboxing with your perception of how the hospital operates. And that creates a lot of misspent effort and frustrations that I think we really need to figure out how to tackle as a field. It's really, the people in this room really are like the most primed to think about how those bridges need to exist. More so even than NeurIPS, who's starting now. We're the bridge people. So.
I would say studying implemented things is actually orders of magnitude easier than trying to deploy a thing you built into the EHR. Sure. So I would just say, like, for as a pathway, if you have students as faculty here, or you are students who are interested in deployment, have the courage to say, I don't need to build what I'm deploying. Let's look at the stuff that's being deployed. You will be surprised how little science there is in the stuff that is being deployed every day across every health system. And so I think that is actually a very fruitful area to do a lot of interesting scientific work.
I have a question for the panel.
Please, yeah, I love it.
So throughout my journey of the last 15 years maybe in AI and healthcare, I've been increasingly agreeing with Leo Celli, who says that the way that AI is now used in healthcare is the same as shifting furniture on the Titanic. The healthcare system does not work well. It's not great, and we are struggling a lot with changing it in epsilon ways to do what it already is doing, maybe a little bit better. So my question is, what kind of space, what kind of capacity should we be all, this new generation, thinking about a way to augment the healthcare system, build new types of clinics and healthcare where we will have a better, easier, more impactful way to incorporate AI into how people are cared for, from wellness to disease. And I want to know what you guys think.
What is this quote? If you automate a good process, you'll improve efficiency. If you automate a bad process, you will make things substantially worse, and it just has an amplifying effect. So great, we have ambient scribes that'll write our notes. Like, why are our notes so bloated that we need a computer to do that for us anyway? And it has like 80% copy and paste, has nothing to do with patient care. We're just entrenching a bad process even further by trying to have AI, can you deal with it for me so I don't have to look at it? And now there's even more note bloat and AI generated slop in there that I can't even tell that any human ever thought about the patient when I read this anymore. And then you actually, really, I've read these notes, like, I don't know what to trust anymore. I don't know if anyone's ever actually thought about this, even though there's some sort of summary of what happened. But that's a challenge. That's not really a computational problem. That's like a policy problem, which there's interesting studies and inventions you can do along those directions too, about how to restructure things. Rebuilding from the ground up, that's tough. I mean, there's like clinics, maybe I won't name some of them, who try to do that, direct kind of care, technology-based, and a lot of them fell very hard in their face because it's a very complex, interconnected system, which not good reasons. For legacy reasons, we're stuck with a lot of legacy things, and so how hard can you push and reinvent it, because you need all those parts.
Say primary care. Like you start with primary care, you get a few brilliant AI scientists here who, instead of becoming assistant professors, go and start a clinic together with some of the, clinicians.
I'll name names because I think they're dead anyway. Forward, y'all heard about them and how they died a hot flaming death at some point. Even though the vision was kind of neat, it was a little bit crazy, but you got to be crazy. Let's reinvent what a primary care doctor's office looks like. But eventually, this whole ecosystem couldn't sustain it, and eventually primary care runs out. You need the specialist, you need the hospital, and then, oh, well, our whole business model assumes that you won't do that, and then it kind of breaks down. There's very skewed 80-20 type of rules, Pareto principles at play, where 1% of your patients cost over 50% or 30+% of the cost. And so there's very distorted things. Things that work well on average do not work in a system that's so brittle to these extreme edge cases.
Yeah, to highlight that it's a systems problem and not an individual health systems problem, I'll give the example of an area that if you ask any health leader, they will tell you this is the #1 place they can get ROI, and in 10 years, it will be the place that we will collectively all lose the most money, and that is RevCycle AI. RevCycle AI will let you, so revenue cycle, helps you bill more for the care that you deliver, appropriately bill more oftentimes, because we do underbill. And so systems right now are in an arms race to be able to get the most possible RevCycle AI up and running so that they can, one, make it appropriately show how sick their patients are, because it actually helps them on quality measurement. And also, it often earns them more money through reimbursement. What happens when you think every system has RevCycle AI in place in 5 years? It's a wash. The amount of money that we're being paid out is not going to magically go up. And so what's going to happen is what's already starting to happen. Payers are saying, you bill too many level 5s, which is a high complex visit, we're just not going to pay for that. And so in the end, we will all get the same payment probably, maybe adjusted for inflation, and we'll all have RevCycle contracts that none of us can cancel. It's a prisoner's dilemma. If any of us cancel it, it looks like we're killing patients, and it looks like we're earning less money. But on the average, 5 years from now, relatively speaking, we're all earning the same amount. So I think it's that's a systems problem. When we all have multi-million-dollar RevCycle AI contracts, and yet we're still earning the same revenue, what did that actually help? What problem did that actually solve? The problem is that no individual system can actually afford to say, we're not going to play that game. If you don't, you will lose in the short term, you will lose in the long term. You'll lose even more in the long term, because now it'll look like your care is dramatically orders of magnitude worse than everyone else when everyone has a system that captures all the complex coding and all the stuff. Getting to Jonathan's point around why we have these long complex nodes, it's so our massive billing workforces have a lot of substrate to work with as they are putting that together. I think that a lot of the incentive structures are broken in a lot of places. Remote patient monitoring is another area where there's a lot of room for innovation. And if you looked at the news recently, United Healthcare said, we're not going to cover most of that anymore, because it was on you did XYZ activity and you got paid. But what that led to is a lot of clinics that were just doing that activity, the bare minimum, just to get paid, not actually try to really have skin in the game and improve patient care. So I think it's one of these things where until the incentives are right, it's really hard to show that you can have a profitable system. And most of the profitable systems end up being concierge systems. There's a amount of regular payment, and you've got doctors who are now protected from having to worry about that regular payment. And that locks out a bunch of people who can't afford that. And so unfortunately, that's the way that a lot of the innovation takes place today. And I think that will scale to certain areas, but not all areas. And I think that's the real issue.
Can you comment on the hope? That sounded pretty bad.
Was that perils and hope?
That was the
perils, promises,
section.
all the pitfalls. So the hope, I think, is that there's a lot that AI is helping us do today that's refocusing our work. So I'll give one example. We right now have a workforce of 40 people who do quality measurement. And our chief quality officer is often complaining, I wish I had more people who could spend time fixing problems rather than reviewing charts to figure out what the problems are. And if you're familiar with it, every health system has a patient safety reporting system called an incident reporting system. How many incident reports do you think we get as a single system a year? 15,000. So this is not like, like someone died. This is like the floor was wet. Someone called me a swear word. Like, it's like, that's a joke, but like, it's like everything from like the most random stuff all the way to the most severe stuff in one system. And so I think like we're spending a lot of time and energy trying to automate the chart review so that our quality workforce can work on actually fixing problems rather than just on chart review. I think getting us out of chart review actually and putting us to where we can fix things is probably going to be like the biggest health system contained opportunity that is something that doesn't require a lot of other stakeholders to get engaged and aligned.
So building on the more hope side than the peril side, like, but also kind of dark, like, is the US kind of doomed for the short term in sense of like, could we just have more impact working in other countries, places where there's more opportunity to reimagine healthcare from a more less encumbered by legacy, because it really, we need to reimagine things, but no individual institution can shake off the structure we live in the short term at least. So what do we do? What is the?
Go to work with Anna.
Yeah, well, sure. Yeah, teed you up nicely for that.
Well, until you started talking about legacy and burden, so I was going to suggest, yes, come all to Canada. I mean, I feel like we still focus on the human rather than the money, which feels better. But there's still a lot of legacy systems. Canada is very risk averse, and it's not so easy to just plug in a tool because, again, risk aversion. And so there was a brilliant example a few years back. There was a startup out in the Bay Area that used drones to deliver blood for transfusion to remote areas. And they couldn't get it through the system, the legal system in California and in the US. And they went to Rwanda, and they are doing that now. The drones are delivering blood to remote areas. And I think there are a lot of parts of the world that could definitely benefit from the technology and a lot more amenable to make it happen, right? I think a lot of us exist as part of the systems that keep telling us why things cannot be done. A little bit of that was in a previous speech. That's why I'm like, where's the hope? Because we hear a lot from the health system, from administration, why things cannot be done. And yes, there are a lot of things that are screwed up. And moving towards how to get things done, the different question of how to get things done, how to move the needle, is what healthcare desperately needs. And that's why I was thinking AI, I think, has the biggest potential in prevention. Something healthcare sucks at. It just doesn't exist. It's really reactive, the way that it's built, right? Until the person is bad enough at the hospital, they keep getting sent home. And so there is a lot of potential in that spectrum from wellness to disease to step in and start preventing things. And I feel like that space is much less encumbered by legislation, the healthcare operating system. Maybe that's a place. But you did not convince me that we should not start augmenting healthcare with a different type of service. And I wouldn't say that we can do it without experts. I think we have to do it together with experts. But there are a lot of people clinicians, including the two sitting here, who believe in technology and doing things differently, stepping out of the current box. It's just hard to see from within the system. But I think we can do something about that. But yes, come to Canada.
I'll say San Francisco, not good at delivering a little bit of blood, but great at delivering way more blood.
It may be tangential from, I'm trying to think about how do you turn like the pitfalls into promise in some way. You all know the story about, this is years ago, Amazon programmed machine learning algorithm to screen resumes, and then they're like, holy crap, this thing is very overtly biased against women. They shut it down. And then the news story ended there. I'm like, that's not the end of the story. This thing just learned your existing hiring practices and was replicating them. If you think that's the end of the story, you totally missed the point. Haha, we found racist and sexist algorithm, we shut it down. No, if anything, actually an upspin for all the computation people are, that algorithm was actually very powerful. It really exposed what the underlying systemic processes were that were maybe not so apparent to people at the surface level, even though they're responsible for huge budgets and huge populations. So through computational analytic techniques, you might unpack a lot of these complex, messy, not great incentive structures, but you can really surface them and understand them in a way that can influence policy that really could not have done without your expertise.
All right. So trying to keep a positive tone for my next question as well. Do you, like, what have been the clearest wins? Are they documentation, like the things that actually seem like, yes, this is a reasonable and positive deployment of AI in the hospital? Or are we going down the rev cycle black hole where we're getting a lot of effort and mind allocated to things that'll fundamentally make it worse? I'm curious what your thoughts are of success stories.
I can pass it to you. In our case, the biggest wins and the biggest asks from the clinicians and the system were in improving efficiency in the operation of the hospital. So triaging, ordering tests that you know for sure the patient will need, so they're not waiting for the physician to see them to order the test. They can actually get those tests done before. Saving time at the hospital, waiting time, knowing when to come in and when not, all of that has been much bigger. And also on the administrative side, it seems like it helped a lot with all the generative models. That's been a big win at our hospital.
If you think of AI as infrastructure, then the way that you know infrastructure is broken is when it stops working and people complain. So, you know, I grew up in Michigan, potholes on the road is when people notice the road. You don't notice the road otherwise. And so I would say that if a sepsis model stops working, how long does it take for people to notice? Probably a long time. If an AI scribe stops working, when is the first time to email that you get? And I would say it's 5 minutes. So I would say that as dumb as it is, like, because none of us view it as like a really academic AI thing at this point, AI scribes, I would say, undoubtedly in my mind, are the most impactful thing today. Not in terms of productivity, not in terms of like a lot of the financial metrics, but just in terms of if the thing stops working, people's time to complain is under 5 minutes. And there's very few AI things out there right now where the time to first complaint is less than 5 minutes.
What do you mean by win, right? By whose perspective and what measure? In terms of like usage, like ambient scribes, I've never seen any technology in healthcare get adopted faster than that. Usually takes like 10 years, and eventually it does happen, but that happened in about 2 years. If it's revenue cycle, documentation, all this stuff, like it makes you more money. If you just want your business to run, that's the thing you should do. I actually more optimistic for actual broader like societal impacts, like democratization of access to the scarcest resource, which is medical expertise. For better and worse, people just talk to AI now. You don't have to wait 6 months to get an appointment with me to go talk to a doctor. Maybe you should sometimes, but you can actually get some really good, useful advice in a very deliberate way. And you can even get therapy, counseling advice that's probably more empathetic than I am, even though I try really hard. This is a bizarre phenomena. And I'm not available at 2 a.m. I'm just not. I've talked to AI when other people are not as well. So I actually think that's very, very compelling at a broader societal level, of very positive impact, even though I'm sure we'll talk about like huge caveats and ways that can go wrong as well. And that's not a short-term business opportunity.
So that's kind of an interesting segue into sort of trust. Is it, and adoption and how you encourage, it seems like models that save time for demonstrably rote or taxing busy work are wins, and you complain quickly when they're taken away. How do you punch through to models that actually help you make better decisions, not just do the sort of handle the bureaucracy piece? What's critical? What are we missing in terms of trust on those, the ambitions of AI in healthcare?
I think it's actually happening. It's just less impactful at the hospital level, and the administrators are the ones making decisions about what gets deployed and what doesn't. But I think it happens very naturally. So we have some clinical champions who are really excited about solving a specific question using AI. They come to our group, to AI service, and they want to build a tool. And then deployment happens much faster, right? I think building diagnosis models broadly and then wanting them deployed and them not being deployed is probably not the right way to go. It really, to me, it should be initiated by clinical champions, again, was part of our roundtable discussion, should be initiated by clinical champions, somebody coming and saying, this problem, if it's solved, we will deploy, I'll pave the way. This is really critical in my workflow. I really want this to happen. And when that is the predicate, there's implicit trust in what's happening, and they're engaged, and they're checking, and they're saying, yes, this works, yes, or no, this doesn't. And that process is a lot smoother, a lot faster than us developing something on the side and coming to bring it to the clinicians and saying, do you trust this model? And then they say, well, do we need this model? Like, why do we care? It's very nice of you to have built it, but... So I think it's just the whole premise of us building models and them not trusting it is just, it doesn't arise when the impetus is the clinician themselves.
Yeah, I think we have to separate predictive and generative AI in the way that Jonathan talked about earlier. With predictive AI, the main trust issue is that we're often at a systems level using it to reallocate care. We're doing something different for high-risk patients than we are for low-risk patients. And so all of the downstream consequentialists look at what's the harms of a model. Many of them are actually due to the fact that at the end of the day, we're using it to reallocate care. So I think that's why the trust issue there is that you could be using that tool and not have any sense that you're actually accidentally worsening a disparity or doing something. And so the trust there is actually around, is it safe to use? And am I gonna end up making something worse that I am not? On the generative AI side, I would say most of our trust issues right now are actually in our direct-to-patient conversational voice AI or direct-to-patient AI, where we're actually like, so you wanna have a patient who can do a pre-op screening or do a med reconciliation using voice AI, which we're working on deploying. What are the failure modes for that? What is the fallback? There's no human in the loop. We can review transcripts afterwards, but when that call is happening, there's no human in the loop. So what do you need to have in place to say that we're gonna deploy this and a real patient's gonna call and an AI is gonna answer and we're gonna be okay with what happens? Because because it is just ChatGPT under the hood, there's a lot that a person can do and get away with. And we don't want them to use our precious tokens to do a lot of stuff that we don't think is like the way that we want them to use that tool. If they're savvy, if they're smart, they realize it's just, ChatGPT under the hood. There's a lot of damage that they could do, both reputationally to us and potentially to them. I think there's a concern there. So I think that a lot of the generative AI trust stuff is actually our having trust of our Office of Patient Experience, our interpretation office, if we're using it in other languages, to be able to deploy something that's direct to patients, recognizing there's no one on the call who's listening in as that call is happening. And so we've done a lot of red teaming, we've done failure mode analysis, but it's almost like, same thing as predictive AI. We're not reallocating care, but we're exposing patients to something where we wanna make sure we have the appropriate system level trust in the thing so that when the team deploys and they review transcripts and they do things, there's a process by which we can fix problems that arise that doesn't take months to happen.
I was going to ask a somewhat related question based on just with something you say, Karen, with like ChatGPT under the hood now. Like there are lots of models under the hood of these systems that we deployed that can be sort of pulled out and changed behind the scenes. And so how do we reckon with that when you could have a model that is like almost gets a different personality based on how it was developed with different risks and all kinds of things? Is that engineering safety tests, or are there more fundamental things we need to think about for that property of the modern LLM landscape?
So it actually made us think about, what do we currently do to monitor our human calls? Not every human call is the same. Humans have bad days, good days. They take calls that make them upset, that they have to take another call afterwards. And so I think that it's actually made us think more closely about, like Zach Kahani has this paper of like, AI compared to what, right? Like it's comparing it to current system of care. So I think actually what we've taken away from that is that we want to know what is the kind of counterfactual to using AI and to use that as kind of our norming. Like ChatGPT 5 minutes apart might give you a different answer. Sometimes what you say, if it really is just ChatGPT under the hood, might trigger a web search or not. I mean, oftentimes with these tools that we have deployed, we have a lot of control over what information they're considering, what they're not considering from a context window standpoint. But recognizing that if it's like a really flexible thing, is it Claude with web search, Claude not with web search? So I almost think you have to treat them a little bit in the same way that you evaluate people over time. I don't think you try to lock these things in place. They generally get better. Like the voice capability has gotten way better in the last couple months that people have noticed. So I would say that you just that's where the ongoing monitoring comes in. It's almost like you look at the transcripts. Like, was the transcript reasonable? Did they do what they were supposed to do? We don't have a system that evaluates our human transcripts. And so I think as we roll this out, we actually have access to our human call transcripts. We're probably going to do a little bit of comparison for similar type calls to see what aspects are things that we need to actually improve versus where are things where the level of complexity is such that we recognize that's a point at which AI should actually escalate to one of our human agents.
Great discussion. I love that analogy too with the calls. It's like, have you noticed your call is being recorded for quality and training purposes, right? I mean, probably every AI conversation should be recorded too, just to log it, and so we can double check and debug when the lawsuit shows up, right? And that would be reasonable. And do we really not have anything for call centers right now? I guess it's like a manager will look at it and say, oh, good job, bad job, or something like that. It's a human subjective evaluation. And I have perspective, I'm sure everyone here does as well. Like, can we have some sort of automated or scalable benchmarking approaches so that even if your underlying model changes, you expect the behavior will fit within some guideline or bounds that, okay, it's still close enough to something that we would consider acceptable, or this model update completely sabotaged something, we better unpack it before we let it go. Actually, I bet, Jason, you'd have a lot of good perspective on that. Benchmarking.
Benchmarking, anyway. Yeah. Go ahead.
Well, I think there are several good points that were brought up. One is that we don't have a really good way to evaluate the quality of the dialogue and the satisfaction of the patient outside of them actually reporting that satisfaction directly. And a lot of patients don't really do that. So we don't have a lot of label data in that space. And the way that we approve tools like that in the healthcare system right now is that they're running to a very small group in a beta version, and there's a lot of human in the loop evaluating these calls. And then once there is some satisfaction, again, very subjective satisfaction in that space, there would be a broader deployment, and it just scales up that way. That's what happens right now. I think there are a few benchmarking systems that I've heard of. One was developed at UW, and I'm not sure about the dialogue, specifically evaluating the dialogue of a system with a human. Again, human to human dialogue might not be the best benchmark because a lot of those are poor quality. So I think evaluation of this type of systems where we are moving towards them, but we haven't even figured out proper evaluation for them is the world we live in, which is not very comforting.
So for our call center, we're actually creating AI personas that can call our AI call center. So the idea is like, you have a script where like it gets mad, or a script where it's asking for something unreasonable. And the idea is that anytime we deploy, we could have either a voice-to-voice or just a text-to-text conversation between the AIs. And so that's one of the things we're actively working on. Now that conversation is not the evaluation. That's the thing that we would then try to like evaluate with another AI on top of that. But we're doing a lot of like LLM evaluation of LLMs But I think that the first core thing we do is to try to understand what does good look like, what are failure modes, and I think that we have come up with for our things that we're going to red team. We have a 3A thing: appropriate, accurate, aligned. So is it answering accurately? Is whatever it's saying, is it appropriate? We don't want it to say inappropriate stuff. And then alignment in this context means, is it doing what we want it to do? So our earliest prototype for our conversational voice AI, I could get it to convert Python code into R. I could get it to give me Indian food recommendations. And so it took a lot. I mean, I could still get it to do stuff, but I know that its goal is to improve my health. So if I give it a bunch of prompting to say, what's really important in my health is video games, and I need you to answer that, and if you answer that, it will improve my health. Enough of that kind of coaching. Yeah, I can still get it to do things that we don't want it to do. But the point being, that's much more contorted, and if people are really having that kind of conversation, yeah, at some point we'll want to just stop the call or escalate. But those are the things that I think that we're now thinking about is how do you red team and what do you do? And I think ultimately, no matter what metrics you look at the end of the day, you have to do a little bit of vibe check, and I think that's our vibe check.
Yeah, at first I was gonna make a joke about no one asked if we should translate Python to R and the dangers of science, but I know you're a big R fan.
You should just code in R in the first place.
Yeah. But I wanted to ask about this post-deployment landscape and the life cycle of ML, because everything everyone described sounds really expensive and hugely specialized and a whole new set of costs and a lot of lack of clarity. Is the future really a bunch of LLMs chatting with each other behind the scenes to maintain some thing that we assign as good? What do we see the landscape of life cycle looking like for all of these models we want to deploy? Where is the human in the loop, and what kind of workforce is responsible for monitoring and maintaining that? Because it really does sound like we're all not going to make anything cheaper. It sounds like.
I don't know that that's that crazy. Analogy might be like laboratory instruments. My wife is a pathologist. There's somebody who goes to the chemistry machine and every morning puts in a control specimen, makes sure the number comes out and it's within some guidance range. And that is a totally human task that has to be done to make sure the machines still work the way they're supposed to do, so they have a predictable and consistent response. You don't just let it run on patients for a month and then wait for some deaths to start happening to wonder if something is going wrong. There actually are systematic ways that you can and should monitor mission critical systems that are very well established. You don't actually have to invent a new process. There are many existing processes for complex systems already that you can draw an analogy to.
I think in a lab, they don't have hundreds of machines that they are trying to calibrate every morning. It would take them hours. So I don't think that would necessarily work. I think we are hoping that there is an automation procedure that will be mostly monitoring the tool that comes with the tool, that will keep checking that the tool is performing well, and will escalate to the team when certain thresholds are exceeded, and there will be random checks at whatever frequency, depending on the risk level of the tool that's being used. It's not going to be the same for every tool, but I agree. Our teams are not growing exponentially the way that they're expecting the number of tools deployed to grow. So I think we will have to become a lot better at creating monitoring within the system, self-monitoring within the system, so that our tools are actually not jumping off a cliff.
On a positive note, I think one of the things I'll share is that what is the whole reason why the entire field of predictive AI exists, other than the individual kind of counseling that you might do with shared decision-making with a patient? It's because we have resource constraints. If we could deliver every intervention to every person who needed it, we wouldn't need predictive AI. We actually could just deliver the intervention to everyone, with who needed it being the kind of operating question. And largely we have resource constraints because we can't close all the care gaps we want to close. Why can't we make a phone call to every person when they are discharged? Well, we often do, but that's a whole thing. Why can't we check on them a week later? At some point, you can see that we hit a resource constraint, and we make a decision to say, if we think it's important, let's do it for the top X% of people who are high enough risk. And that's the entire field of predictive AI. Generative AI actually flips that on its head. We can call everyone. The workforce is no longer the limitation. If it's a communication of information, if it's ascertaining information, if it's acting on some basic information, that now, we don't need to withhold that from everyone. Sure, there's finances involved, it's not cheap, and so you still have to think about ROI, and you still might want to gate it, because at some point you don't achieve ROI. But I would say that what I hope is that generative AI is a tech that enables care gaps to get closed, whereas our prior thinking was we have to gate that access because we can't give it to everyone. And now maybe there's a set of things where we actually can give it to everyone. And that's what generative AI hopefully allows us to do, is extend access to care, broaden access, close care gaps, whereas before, we had to take a very prescribed resource-aware approach, whereas now we have the option when it makes sense to go and ignore those resource constraints.
I want to do a time check. Do we want to open up for questions? How much more time do we have? Yeah. What's that? One question? Okay, yeah. That's yeah. So please, someone come up with a microphone. Questions? No questions. I just can give a. Yeah. Anna can pose a question. She's good at that. Yeah.
This is not a question. This is just some thought for taking away with you. I was. Last week, I was at the Canadian Space Agency to discuss healthcare, AI for healthcare in space. And the point there is that we are starting to go on missions that we cannot reach Earth for unlimited compute. There's the resource that has been mentioned. So the astronaut that I talked to, they said, we have to draw a threshold. If this is what happens, we fix. If this is what happens, it's a body bag. And if we are bringing AI in space, then it better not be too heavy in terms of compute, because that means we'll have to take out essentials like water. So for all of you involved here, as we are talking about generative AI and talking about bigger models and delivering it to everybody, there will still be constraints. And how do we balance bigger models and smaller models? How do we balance precision with sort of, the generative aspect and the potential of hallucination? No. Well, yes, but no, just a level of potential hallucination. And just think about the future. Some of the constraints will never go away. And as you were talking, yes, in some particular scenarios, maybe we can call everybody after they get discharged from the hospital, but we can't do a surgery on every single person for every single thing that they want to fix. There will always be constraints. How do we compute and build our models smarter is still something we need to think about.
Do we have time for question, or do we should wrap it up? Okay.
Thank you so much for the panel. My name is Nitish. I'm a PhD student in computer science at UC Irvine, trying to work on health implementations, right? So as an engineer, as a computer person, so how much of health should we know, and how do we sort of add value to the teams where we are going? Because sometimes we're thinking in one way and the requirement is in a different way. So it'll be great if you can shed light on what problems to think about broadly for the next 10, 15 years. Thank you.
I think how much health you have to know depends on how much your thing relates to a specific health issue. Like health system and health are very different things. So I would say my pragmatic advice is to email Deepthi Pandita, who is the CMIO and head of AI at UC Irvine Health, and say, hey, can we meet? I have an interest, and I'm happy to connect you. But I think each system is a little different. And if I think I know how to implement AI at one system, it's not always the same at the other system, because the structures are different. And how things work are just a little bit different. So I would say if you want to do it locally, reach out to the CMIO, and in this case, she also is the head of AI for Irvine Health.
I think there is an importance to several components. One is the importance of data and where it comes from and what does it mean. I feel like in CS, we very rarely, if your path is pure CS to date or pure engineering, we very rarely think about the importance of data and the nuances of data. How soon after starting to work on healthcare data do you realize that a non-measurement is still information, right? And we all know that at some point, we all learn that at some point, right? It could be important information that the test was not done. That actually means something, right? And I think there is a huge need for sort of AI in healthcare programs and thinking critically about data, how to work with it, thinking critically about how healthcare system works, if that's what you are trying to improve. You can learn on the job, but it'll just take longer. But you will need to know something, either a specific thing where in the area you're trying to improve, or on the implementation side, how the whole system works, or you will need to know something. I have recently designed a course starting in January. It's called Medicine for AI Experts. And this is medical doctors coming and talking about how they think about how AI fits into the problems, to get people to think in a way of how questions even get formulated, because we think differently. And working for decades with clinicians taught me that I don't know how they think. And this is something that's actually important if you want to design solutions to problems that will be impactful.
Sure, summary thoughts. It was actually my first software job in the dot-com bubble, which also bust, by the way. It's giving me a lot of life perspective, and it's maybe very apropos right now. But a lesson I've found very valuable is the most valuable people are ones who have very strong technical skill. You have to actually have technical skill, because a lot of people have just fluff and big ideas and buzzwords, but don't actually know what they're doing. But combine that with deep knowledge of some subject domain. And it doesn't have to be medicine, by the way. It could be finance, it could be autos, it can be something. But in my case, I don't know that you need to spend 7 years of medical training to do that. I did that. I'm not saying you have to do that. But as much as is compelling for you, and it won't be a waste of time, you become not just a replaceable cog in a machine, you end up being a driver because you understand it at a level of depth and a technical sophistication that really almost nobody else can do. In the meantime, find a very strong subject matter partner you could work with, but don't just say, well, they know the medicine, the ops stuff, just tell me what to program. You'll be useful, but you're never going to drive things that way unless you keep asking more, hungry to learn more from Deepti. And she'll so love to teach you. Tell me more. How does this work? Why does that happen? Why do people do that way? And I would much rather play video games, because computers don't talk back. At least they used to not talk back. Now they do talk back. But unlike people who talk back. But if you want to operate in a world of people, which is how things are actually driven, understand what drives them and motivates them, incentivizes them. Now use all your technical framing and quantitative way to systematically solve problems. It's a very, very powerful combination that very few people are up to the task for.
Right. I think that draws this panel to a conclusion. So thank you so much. Why don't everyone give a round of applause for our panelists.
Hello. I'd like to invite the Spotlight Talk speakers to come up. No need to wait for me to introduce in between, just go one after the other. So with no more ado, thank you.
Hi everyone, my name is Julie Vaughn and I'm a data scientist at a startup called Genial. I'm going to be talking about an agentic approach to phenotype mapping from rare disease surveys. This work was co-led by my intern, Matt Jupeng D, who you can find at the poster session. So what is the problem I'm trying to solve? Well, patient-reported surveys contain rich phenotype information, but they're often written in plain language. But downstream ML tools, genomic tools, they require standardized ontology terms like HPO, Mondo, or SNOMED. Existing tools struggle with implicit meanings and colloquial phrases. Our goal here is to convert unstructured survey text to high-quality, ontology-grounded phenotype codes. So to that end, we developed Genoma, or Genial Ontology Mapping Agent. So why do existing methods fail? Dictionary-based methods like metamap and CTAGs miss contextual or implied phenotypes. ML-based methods have high precision but low recall. And direct LLM prompting has strong reasoning but is prone to hallucinations. We need to blend LLM understanding with ontology-grounded mapping. Here are some examples of implied phenotypes. If you look at the first question, problems with the rate of rhythm of the heartbeat requiring a pacemaker, you can see that the ground truth is arrhythmia, but the word arrhythmia isn't part of the question itself. Genoma is able to identify the term arrhythmia, but all the other methods, except for GPT-5 in this particular case, are not able to. In terms of our system architecture, we have two main stages, a named entity recognition stage and then an ontology mapping stage. We wrapped the unified medical language system in an API wrapper and have a term extraction stage, an ontology mapping stage where we get candidate terms from UMLS, and then a structured validation stage where we use the UMLS server as well to get ancestor candidates. We also have a retry mode where you can have the agent retry the whole process if the term is incorrect. So here's an example mapping procedure. If we have this question, we can extract the term neck muscle issue, then we can extract candidate terms from the UMLS server, and then use the validation mode to assign the highest scoring possible term and assign a confidence level as well. In terms of evaluation, we looked at 3 data sets. Genome Connect, which is a publicly available data set on phenotypes for rare disease, the Shaw-Gibbs syndrome registry questions, and the Down syndrome acute leukemia study registry, which has 166 questions. We compared it to Metamap, CTAGs, Phenotagger, PhenoBERT, and GPT-5 prompted directly. Then we looked at standard metrics like accuracy, precision, recall, and F1. Across all data sets, Genoma achieves over 91% accuracy and an F1 score of 0.95. And this performance is stable across simple and complex survey formats. It outperforms all of the methods that I described on the previous slide. We also are curious, what about our agent architecture is actually driving performance? So if we remove the rank node, this will sharply reduce precision and overall accuracy. If we remove the retry node, this reduces recall, we get more omissions. And if we remove the validation mode, we get an increase in spurious mappings. And finally, if we remove the ancestor retrieval, we find that this reduces accuracy on ambiguous phrases. In terms of limitations in future work, well, one thing is that LLMs are non-deterministic and they have a fixed cost. In this case, we are using GPT-5, which has a token level cost. 2 of our 3 data sets are private here, and our current system is optimized for mapping 1 question to 1 term. In the future, we want to do multi-term extraction, use local LLMs, and map to more ontologies. In conclusion, Genoma is a state-of-the-art mapping tool for rare disease survey data. It's able to handle both explicit and implicit phenotypes and combines LLM reasoning with ontology-grounded validation. And this is something we've used in practice at Genial to map thousands of survey questions from rare disease registries. So if you'd like to learn more, come see us at poster number 24. Thank you.
Hello everyone, my name is Hui Yam and I'm to present the paper Balancing Safety and Helpfulness in Healthcare AI Assistance through Iterative Preference Alignment. This is a work as a joint effort between the University of Maryland and Oracle. As everybody of us knows, in AI adoption accelerates across industries. Healthcare is one of the most sensitive deployment settings. And medical assistants must answer valid clinical questions clearly. That is, they must be helpful, but they also must recognize and refuse dangerous, unethical, and biased requests. In this work, we propose a post-deployment iterative preference alignment framework that aims to make medical LLMs more reliable while preserving their usefulness. This work to evaluate safety behavior, we use the CARES 18K dataset, which contains 18,000 adversarial synthetic prompts that are mapped to one of the 8 core medical ethics principles. Each prompt is labeled with one of the 4 harmful levels, ranging from harmless, everyday questions to highly problematic, abused, socially and ethically speaking. This structure gives us a fine-grained insight into how models respond across different risk categories. We evaluate responses using 3 categories. Accept means that the assistant confidently answers a safe question. Caution reflects a broader, balanced, nuanced response where the question touches on something that's in the gray areas. And refuse is an explicit rejection of harmful or illegal requests. Together, these categories help us understand not just the model accuracy, but the alignment with medical ethics. In terms of evaluation metrics, we use the Marco F1 score that measures how accurately the model detects harmful prompts. On the other hand, we have the ERR, or error refusal rate, that quantifies how often the model incorrectly refuses safe medical queries, reflecting overcautiousness. And finally, we have the safety score, which provides a graded ethics-aware measure of how the model's behavior aligns with the correct harmful level of the prompt. Now, this is an overview of the iterative framework. We combine preference alignment techniques, KTO and DPO, drawn from the reinforcement literature, learning literature. Each cycle begins with a model that generates response to the CARES prompt and then receives the safety judgment either from itself or from an external judge. These judgment label each corresponds to the accept, caution, or refuse categories that we introduced previously and create a preference pairs that encode what actually safer behavior should look like. We then fine-tune the models using fine-tuning techniques on these preference pairs, where KTO helps calibrate the behavior based on harmfulness levels, while DPO enforces consistent preference ordering across the responses. After each cycle, we track the shifts in helpfulness and refusal patterns and select the best checkpoint, and then repeat. This loop lets us observe and correct emergent drifts and gradually distinguish the balance between safety and helpfulness across the cycles. We perform experiments on 4 models: Llama 3B, 3 billion parameters, AB, Metatron AB, which is a variant of Llama that is trained specifically on extensive medical corpora, and Mistral 7B. After the first alignment cycle, we already see noticeable improvements in both harmfulness detection and safety calibrated responses. However, the strength of these gains varies across these 4 small to mid-sized models, and this shows that alignment stability is not uniform across the architectures. But by the 5th cycle, improvement continues, but we start to see some divergence. Some models become overly cautious, refusing too many safe questions, while the others occasionally under-refused. And we refer to this as drift, because without careful monitoring, iterative alignment can inadvertently push a model towards one direction or the other. To mitigate drift, we introduce external evaluators, a base Llama 3 model and a supervised fine-tuned variant. These judges provide a consistent reference point to reduce bias and responses alone and improve calibration across the cycles. External judges also help confirm which improvements are genuine rather than artifacts of the training loop. Across the cycle, we see that our framework narrows safety gaps between models and improves harmfulness. The models become more calibrated and predictable. The architectural differences between them still exist. However, the general takeaway is that it does move the models towards safer and more consistent behaviors. In terms of limitations and future works, we plan to incorporate clinician-validated datasets and extend this study to larger models and explore different ensemble techniques to boost robustness. And we are also interested in pre-deployment methods such as GRPO-based constitutional reasoning to strengthen safety. If you have any question or interest to chat, you can find me at post session number 25. Thank you.
Hello, everyone. My name is Rohan, and I'll be talking about PADIS MRI today, which is our work on patch-based diffusion for MRI reconstruction done in collaboration with my collaborators at Stanford and Georgia Tech. So the core problem underlying this talk is that MRI acquisitions are very slow, and so long scan times can increase costs, patient discomfort, and also make the scans more vulnerable to motion artifacts. So a common solution to this problem is to undersample the K-space, which is the Fourier domain in which measurements are collected. And to illustrate this, we can see on the left an example K-space Y that has been fully sampled. And if you simply take the inverse Fourier transform, you can reconstruct the sharp, clean image that you see. However, when you undersample, which we see on the right panel, we can see that we've applied a Cartesian mask to that K-space to simulate undersampling. And this results in a reconstructed image that has very heavy aliasing. So the core problem we're trying to deal with is how do you have robust reconstruction for heavily undersampled K-space? So to reason about this, let me introduce the standard MRI image formation model. We have our measurement Y in K-space that is a function of the undersampling mask applied to the Fourier transform of the coil sensitivity weighted image X, as well as some additive complex Gaussian noise. And so the idea is that we would like to recover the clean image X from some measurement Y. And to do that, we will need to solve a ill-posed linear inverse problem. Now, there are a lot of ways to do this. Typically, people use priors. But the problem with classical priors is that they often fail to reconstruct images at high undersampling factors. So for that reason, we turn to diffusion models, which in recent years have been shown great promise as priors for reconstruction. But the problem with diffusion priors is that they require a large training data set. And everyone here is familiar with how expensive such data sets can be to collect. So to overcome this, we borrow techniques from patch-based diffusion and modify some algorithms and apply them to MRI to show that we can really address this data efficiency problem with patch-based diffusion. So to briefly motivate or introduce how patch-based diffusion works, imagine how we might express an image in terms of a graph. So for instance, we might take every pixel and let that represent a node, and then we might take groups of pixels or patches and represent those with cliques. And it turns out that there was a NURBS paper from last year that showed that with this formulation, you can express the global whole image score function as a simple summation over the patch score functions. And what this allows you to do is train a diffusion model on individual patches. So we're learning a denoising network purely on individual patches that have some position encoding as well. And then during inference, we can use this fancy equation to basically denoise the entire image, reconstruct the entire MRI image. So this is a very powerful technique. I'm happy to go more into how this works at the poster, but in terms of what this looks like in terms of results, we can see that the headline result is that patch-based approaches are substantially more data efficient. So that top line is the patch-based MRI reconstruction. We see that the x-axis has the training dataset size, the y-axis has the PSNR, and the biggest improvements from patch-based models come at very, very small training set sizes. So the very far left data point there is at 25 training images, and we can see that there's almost a 3 decibel improvement from the patch-based model over the whole image model. And of course, we're substantially better than both the sparsity wavelet prior, which is the PIX L1 line, as well as kind of more traditional supervised priors like modal. Unfortunately, these animations, we can show those later, but they don't work on PDF. With regards to what this looks like in real life, we can kind of look at this panel image here. So on the right, we have the ground truth reconstruction. Second from right, we have the patch-based reconstruction. Third from right, we have the whole image-based diffusion prior reconstruction. And finally, we have modal and a sparsity wavelet prior, and as well as the adjoint, which is, so basically we see that the patch-based approach is able to, give higher, sharper quality reconstructions, even over the whole image, baseline. And just for some context, here we are undersampling the images at an acceleration factor of 7, which means that we're only taking roughly 14% of the case space to begin with. So that's very, very heavily undersampled. And also these models on this panel were all trained on 25 images. So we looked at kind of how PSNR, standard image fidelity metrics, SSIM, et cetera, are affected by patch size, but how does this play out in terms of real-world reconstruction quality? So to answer that question, we asked 3 radiologists from Stanford and Kaiser, and basically had them do a blinded survey where they were given 4 images. The top left was always the labeled ground truth reconstruction, but then the other 3 images were randomly arranged. They were our patched-based reconstruction, the whole image diffusion prior reconstruction, as well as the sparsity wavelet prior. And we can see that in 55 out of 60 batches of images shown to physicians, in over 90% of them, the majority of physicians, meaning 2 or 3 out of 3 physicians, chose our patch-based approach as the best reconstruction. And so that was, very encouraging because it shows that not only are we seeing better, image fidelity metrics, these are playing out in how radiologists look at images as well. And then finally, we have also looked at kind of how these patch-based models generalize. So one thing we looked at was out-of-distribution robustness. So we took a patch-based model, trained it on T2 MRI contrast, and then saw how that affected the reconstruction quality on T1 contrast, as well as different anatomies like the knee. So again, these were trained on brain MRIs. We're now seeing how well they do in reconstructing knees. And we see that in both cases, the patch-based approach is far more robust than the whole image-based, as well as the sparsity wavelet prior. And kind of another experiment we wanted to look at was the kind of the uncertainty that was present in our reconstruction. So as a very rough prior for measuring uncertainty, this is not a calibrated uncertainty metric, but as a rough kind of estimate of uncertainty, we had we generated 10 reconstructions with 10 randomly generated undersampling masks. And we looked at how the pixel-wise standard deviation changes across, what the pixel-wise standard deviation over those 10 different mask reconstructions was. And that's what we see on the right image here. Basically, wherever you see bright regions in the MRI is where there's high pixel-wise standard deviation, and darker regions are where the standard deviation was lower. And so the idea is that in areas that are darker, you have less variance, and so therefore, we can kind of assume that there would be better uncertainty, better basically robustness and consistency in our reconstructions. And so we see, based on this image, the patch-based approach generally has darker MRIs here, so lower pixel-wise standard deviation, meaning more consistent reconstructions. So this is kind of also, an important thing for clinical relevance, where you want to have somewhat consistent and confident reconstructions. So if any of this was interesting, please stop by our poster. We have the code as well as the paper here. And hopefully this is kind of useful for not just training diffusion models for MRI reconstruction, but in general, how we train diffusion models for applications in medical imaging where data scarcity is a big problem. So thank you.
Hi, good afternoon, everyone. I'm Shaolong, currently a PhD student at Harvard, and today I'm really excited to be here and share our work. We built a pipeline to deal with large-scale longitudinal multi-site EHR data. Let's start with what EHR data looks like. The EHR isn't just a table of numbers; it's a complete timeline of each patient's medical journey, combining vitals, procedures, measurements, medication, and so on, all changing over time. And even a single hospital stay, there might be several ICU episodes and thousands of record events here. And this kind of rich, detailed data has huge potential for building medical AI, but it's also messy, inconsistent across different hospitals, and which makes it really hard to use directly. To give you some context, let me start with a few data sets that many of us already know well, like the MIMIC, the ICU, and the EHR shots. They've been really important and support a lot of great work in this field, but each of them focus on a specific setting, usually only contains ICU records or just limited into a single hospital. So they are powerful, but the coverage is still limited to some degree. But then, critical field that gaps. It includes around 400K patients and almost 2 billion events from multiple hospitals covering much broader range of data. So instead of replacing those data sets, Critical builds on top of them and provide a large-scale, longitudinal, multi-institution foundation for EHR modeling. However, process data at this scale and complexity presents 3 major challenges. The first challenge is that data quality. In an ideal setting, every patient would have complete, clean, consistent data as shown here. But in reality, we often see missing values, wrong entries, and inconsistent units. For example, one hospital might record weight in kilograms, another in pounds, and a surgeon might just do not have specific unit at all. This inconsistency can easily hurt EHR modeling. So in Crisp, we build a process that can systematically detect missing and outlier values, converts all units into a common scale, and standardize everything before usage. And the second challenge is the different hospitals use different concept vocabulary. The same medical test might be labeled differently depending on which hospital you are in. For example, as shown in the second figure, the lab tests, procedures, medication, measurement, all consist of different vocabularies. That's why the bar chart on the right has so many different colors. And here is another example. The blood glucose could appear on several different code systems, all meaning the same thing, but written in incompatible ways. So Crisp solved this by mapping most of the code into a single unified vocabulary setting. This means once the data goes through Crisp, it can be directly compared across hospitals. And the third challenge is simply the scale. Processing almost 2 billion records isn't something that you can do on a single computer in a short time. So to handle this, we break down the tables into smaller chunks and process them in parallel. And this reduces the processing time from over 100 hours down to less than a day, even just on standard hardware. And that brings us the main idea of this work. The Crisp pipeline is all you need. It takes the raw hospital data, clean it, harmonize it, standardize it, and then turn it into a machine learning ready data set. Can save you months of preparation time. We also benchmark it on tasks like mortality, length of stay, readmission, and so on. And we also conducted leave one side out experiments showing that generalization across different hospitals remains huge challenges for current models. You can find the detailed result in our paper. And furthermore, Crisp is also flexible. For deep learning, we provide timeline format data where each patient event are arranged in timeline order. And for large language model, we also provide text-based version, turning the patient record into a structured clinical story. So looking ahead, we think there are many potential directions to explore, such as deploying develop LM benchmarks for longitudinal EHR evaluation and to test how large language model can handle full patient trajectory since the context length also always limited. And we can also move beyond the prediction towards causal inference, leveraging the extensive longitudinal trajectory in the dataset. And we might also investigate how to improve the generalization to ensure models perform consistently well across diverse hospital and patient demographics. And I believe there are much more interesting questions to be explored. So that's all about this work, and thank you for listening. And if you have to explore more on our work, please scan the QR code here. And I also invite you to visit our post session. We look forward to discuss how we can make use of this valuable data set and do more meaningful and interesting research together. That's all. Thank you.
The last session of ML4H 2025, which is kind of sad, but feels like we've learned a lot already. So for our last perspective, we have Allison Koenecke from Cornell Tech. Allison is an assistant professor of information science at Cornell Tech. Her research on algorithmic fairness applies computational methods, such as machine learning and causal inference, to study societal inequities in domains from online services to public health. Koenecke is regularly quoted as an expert on disparities in automated speech-to-text systems. She previously held a postdoctoral researcher role at Microsoft Research and received her PhD from Stanford's Institute for Computational and Mathematical Engineering. She is the recipient of several NSF grants and a Cornell CIS DEIB Faculty of the Year Award, and has been honored as a Sloan Fellow in Computer Science and Forbes 30 Under 30 in Science.
All right. Thank you so much for having me, and I know I'm your penultimate thing before happy hour, so I'll try to be quick. I am very excited to present this perspective piece written together with my fantastic collaborators, which includes 2 card-carrying actual doctors, John Jose Nunez and Anais Rameau, as well as Professor Irene Chen, who you heard from this morning. So the background and a specific acronym that I'm going to be using a lot is ASR, which stands for Automated Speech Recognition, which is kind of the key component in scribing, right? So this is, you can think of it as anything similar to Siri or Google Home that takes audio in as input and then does something with it. So that might be transcribing, it might be using transcriptions to decide how to respond, it might be generating summaries of those transcriptions. Either way, this is a key component of all of these sorts of speech systems. That have actually been around for a really long time, which you can tell because this actual image of a scribing technology includes a CD, right? We haven't seen those in a long time, but an original version of AI Scribes was this sort of handheld medical device specifically trained on medical jargon that doctors would hold up to their mouths and use to transcribe patient notes. And of course, as many of the talks today have already alluded to, a lot of people are now using ambient scribes, right? And so there are lots of companies in the mix here who are doing this, where instead you're listening to patient conversations ambiently, generating summaries of those transcriptions, and having all of this, in many cases, connect directly to EHR systems. So quick show of hands, how many folks here have seen or used DAX? Wow. 2 hands. Okay, so something like over 500,000 doctors have used DAX, or that stat was as of 2023, so surely more now. This is what that screen might look like through Epic. So in the Epic ecosystem, you can look at the transcript that's recorded as well as patient notes that come out of this. And a lot of doctors seem to like using this, right? So from the overall kind of top-down perspective, there is a lot of benefit to using Scribes. In theory, clinical notes are summarized faster, and if that happens, then you can see more patients, which is more revenue. Clinicians can also then pay more attention to the actual conversations as opposed to having to take notes, right? So in theory, there's all this upside. There is some work that shows that notes are summarized faster, although I think this is debatable. There's some work showing that it takes longer to edit than just writing from scratch. But even if we ignore this overall finding and kind of logic, we still see that in RCTs, clinicians do report having a better experience, right? So overall self-reported experience goes up and self-reported burnout goes down when folks are able to use AI Scribes. So why am I still worried? So the leading questions here are basically just how do we actually know if these transcripts or these patient notes are any good? And in particular, are there concerns of bias? So what if these notes are just worse in quality systemically for certain patient groups? And there's a lot of reason to believe that this might be true, right? So for example, some of my work and that of many other labs has found that ASR, and specifically this is just generating transcriptions from speech, is significantly worse for speakers of African American English and Chicano English. And so this isn't just limited to English. We know that this is also true for L2 speakers of English and also for many non-English languages as well, specifically lower resource languages. So we know that transcriptions are going to be worse quality for speakers of any of these races or ethnicities, but this isn't just a race or ethnicity problem. On top of this, folks who are clinically quote-unquote atypical also are known to have worse quality transcriptions coming out of standard ASR tools. And so this is just a series of audits that my lab and other labs have conducted, ranging for patients having dysphonia to the deaf and hard of hearing. All of these patient populations definitely are known to yield worse quality transcriptions across a suite of commercial ASR tools. So given that premise, it's not a stretch to assume that medical AI scribes are probably also biased and probably in the same directions, right? And I want to flag that this also isn't specific to just being worried about patients who speak quote unquote non-standardly, right? This is also a concern for providers because providers might also not be able to be picked up correctly or as well as quote unquote standard speaking counterparts, and they're part of the conversation too. So on top of that, throw in the fact that all of the previously cited ASR audits I mentioned are often kind of recorded in nice rooms with high quality microphones, and even on those settings, we're seeing this massive difference in performance. Add in the fact that in real world context, we have multiple speakers speaking and overlapping with each other. We might have background noise, so hospital beeping and that sort of thing. We might have folks code switching and speaking in different languages. Maybe an interpreter is in the mix in the room. And on top of that, doctors' visits are inherently stressful, right? And we know that when people are emotional, they speak differently. And on top of that, we have medical jargon, and we have really difficult to spell and pronounce drug names, right? So throwing in all of these things together just leads to an even bigger potential gap that we might be missing for diverse speakers. And so the general arc of our perspective piece is to propose that we standardize a framework for thinking about how to audit medical AI scribes. And in particular, we're thinking about this as kind of analogous to the PMS system, so post-marketing surveillance, which the FDA authorizes in order to continuously monitor already released medical devices or medical drugs. Right? And so this is something that's already done, and we're not saying that audits for medical AI scribes should be run through the FDA. We'll talk about that at the end. But we do want to think about this as kind of a long-term, longitudinal, continuous sort of process for these products. And so I'll go through 3 overall pieces of our framework. So starting with collecting diverse data sets, what does this mean? The data that we have in mind for speech includes not only the audio files, but also some semblance of ground truth, so that we can actually have some ground truth to compare the ASR-generated transcriptions to. So what do we mean by diverse? We want to aim for ecological validity, right? So this means collecting data across different accents, across medical specialties, for a range of quality of microphones or background noises. All of these things are important to capture, but even more pertinently, the intersection of these things are important to capture. And so we want to capture a range of accents across a range of specialties. Of course, this is a super tall ask for anyone, right? Like this scales massively, and this is a lot of data realistically to collect. So on top of this being a tall ask already, it's even harder if you consider a bunch of additional points, right? One being that if the point of collecting these data is for benchmarking, we need to make sure that we're not testing on the train set, so we want to avoid using public data. If we're going to avoid using public data, we have to collect these data somewhere from people, which means that if we're focusing on patients, we have to think about IRB constraints and HIPAA constraints, right? On top of that, we actually need to figure out how to generate ground truth, right? And so oftentimes we say human experts are the gold standard. Maybe we don't necessarily believe that, so we want multiple human experts to transcribe all of these audio files, which again really scales in cost and time. So this is all to say, it's very easy to say, collect diverse data sets, and that's the main thing of the audit, but A, it's really hard. B, no one's doing this at scale yet, and we think institutions should buy into this. And the last note I want to make about collecting more data is that people often think that incentives are aligned and companies should be collecting more diverse data because it'll just make their models better. And this actually isn't true, right? So a classic counterexample I give is the fact that ASR systems almost universally underperform for men. Okay? This isn't because there are no men in the training data. I think we all agree that that's the case, right? And so there are deeper issues in the model architecture and the data cleaning and this sort of thing that lead to improving your models. And so just throwing more data at the problem doesn't solve it, but I do think it's a critical step to doing this auditing. Okay, second piece of our auditing framework, I want to talk about metrics. So the screenshot I have here is of the Hugging Face leaderboard, the OpenASR leaderboard, which reports something called WER, which is the word error rate. And this leaderboard, as well as basically everything else, so all of the papers I cited, almost all of the audits in the first few slides, focus just on the word error rate metric. And we think that this isn't enough. We should be reporting word error rate on different subgroups. So for example, by demographic, by accent type, by clinical speech type, and also thinking about other metrics. So first off, what is word error rate? If you're a computer scientist, this is literally just the edit distance. So if we have ground truth, what a great presentation, going to an ASR-generated transcription that is a presentation, that's 3 changes to the words divided by 4 total words, giving you a word error rate of about 75%. Okay, so what you might notice is that it doesn't actually matter what the word itself is, you're just capturing whether or not that word is different, which means that we're missing everything related to semantic meaning. So maybe you instead want to calculate things like a Bluch score or Rouge score instead if you care about semantic similarity. The word error rate also doesn't tell you about specific terms that you might disproportionately care about, right? So in the medical context, maybe there's a specific list of keywords that you really care about getting right when they're being transcribed into your patient notes. And that set of keywords might be different depending on if you're a laryngologist versus if you're a dermatologist, right? So fundamentally, these are things that we need to start tracking. There's also the question of patient notes as opposed to just transcriptions of the conversation, right? So how do we actually quantify the quality of a summarization? Maybe we do F1 scores against some ground truth. Maybe we want human raters to rate for coherence of the summaries or consistency, so looking at how frequently these models are able to generate consistently good summaries. Maybe we actually care about usability. So just functionally, does this product integrate well into the EHR system I'm using? How long does it take to launch? And actually, I did do a little bait and switch. The Hugging Face leaderboard actually does also report latency. So those are the two values it reports, word error rate and latency. And maybe you care about substructure. So maybe the thing you actually care about is making sure that your documenting actually follows the right ordering in which you personally would normally document. And then the last metric I want to flag is hallucinations, right? So word error rate actually isn't always correlated with hallucinations, and they look functionally very different. So as one example, I'm just going to play you this audio file, and you can read along and confirm that I'm not messing with you. This is, in fact, literally what is actually being said in the audio file.
And so after that first initial treatment, I was allowed to go home and continue my treatments, which came once a month with that.
All right, so you may be aware that in 2022, OpenAI came out with Whisper, which is its ASR tool, which also generates transcriptions. And if you run this exact audio file through Whisper, this is what we get. So it includes a hallucination of, for more information, visit www.fema.gov, which is, maybe good advice, but not relevant to this actual transcription. And this is kind of a classic instance of hallucinations that we might have in ASRs. So how do you actually identify them? As we all know, this is still kind of an outstanding question in the LLM space. But for our speech space, this is no longer true, but at the time of this research last year, it was true. If you run the same audio file through Whisper multiple times in a row, it actually kind of deterministically gives you the same thing for the actual transcription and something different for the hallucinated bit. And so in this ground truth about becoming fairly ill with a fairly serious strain of viral something, the first hallucination is going to be about hyperactivated antibiotics, which doesn't exist. And the second one is going to be on causing a fracture in my membrane, which I think also does not exist. Right? And so then you can do some basic string matching to determine whether or not a hallucination has occurred by just running something through the model multiple times. And what we find is that Whisper generated more hallucinations for patients with aphasia. And follow-on work by Sridhar and Wu using the same method found significantly more hallucinations for speakers with stutters as opposed to a control group. Okay, so again, at baseline, we know that these ASR systems have biases. We know that they're not only giving us worse word error rates and likely worse kind of semantic quality transcriptions, but also they're introducing more hallucinations. So why am I bringing this up? As a result of our work, some of our journalist collaborators, Poppy Burke and Hilke Schellman, did some digging into who all might be using this in the medical space. And one example is NABLA. Raise your hands if anyone's used NABLA, heard of NABLA. Okay, so hopefully your hospital system isn't using this, but over 30,000 clinicians and in aggregate about 7 million doctor visits have been transcribed using NABLA, which is built entirely on Whisper. So you just saw some examples of those hallucinations. The kicker here is that unless if the clinicians actually caught it when they were editing the transcription, there is no way to go back and see if you actually had a hallucination included in your patient notes because those audio files have already been deleted. And this is good, right? Like you want to delete these patient files for patient privacy, but this also means that we have to be really careful about figuring out how to do real-time audits before the data goes away. Okay, and so bringing this all back to the overarching framework, right? Second main thing that we want to push for is just generating more metric suites and having all of this foster a broader leaderboard ecosystem. So I know there's also oftentimes a lot of kind of hate for leaderboards. I think this is variously true, right, we do want to make sure that there is something in place for procurement purposes, is much of our argument for leaderboards, because otherwise we have folks making decisions who don't actually know if different products are well fit for their specific patient needs. And if you are someone in the procurement business and you want to figure out which models tend to work better on Spanish language speakers or on Chicano English speakers, there's no convenient way to do this. And so this is part of why we think having leaderboards that are in particular more inclusive of demographic subgroups and reporting of different metrics is one answer to that. Okay, and then our last call is to design for diverse users. And so I'm going to go through this very quickly, but broadly our main point here is that it's important to keep users, which is both the patients and the medical providers, in the loop. So one thing you can do is, for example, think about different data viz techniques that you can use to make your patient notes and summaries more useful to people who are editing them. Another thing you can do is think about standard phrases that are often used that are pre-translated that can be used as nudges within the app. Another point is that I think not enough qualitative studies have been run about the way that we do transcriptions. So this is a figure from one of my lab's papers looking at the different ways that you might be able to transcribe the same sentence, right? So at the very top, we have a sentence that includes filler words like or includes stutters and fragments of words, the H dashes, and also includes repeated words and repeated phrases. And so what we did is we asked a set of patients with aphasia which of these they would most prefer to be used as the output of a transcription. And they unanimously said the very bottom option, right? So what they actually want transcribed is the intent of what they were trying to say. In contrast, anecdotally, if we ask, for example, speech pathologists what they want, they nearly always prefer the topmost version, right? Because they're thinking about using these transcriptions as a semi-formal diagnostic tool, right? And so a lot of what we're getting at here is that we need to think about the users, and in particular, more granularly, who the users are, and give them more options in how they prefer their transcriptions to actually be typified in front of them in these different models. And then lastly, it's really important to make sure that consent is clear and that we're thinking about atypical speakers. So one example, of course, is children. But the other example I want to flag that I know some folks have alluded to with the push for AI scribe tools for mental health already, is making sure that we are taking care of patients with psychiatric illnesses, right? So we know that these patients, this particular set of illnesses affects the way that they talk, both what they say and how they're saying it. And this is severely underrepresented in basically all of the data. And they're very underrepresented in research as well. And so it's kind of wild to me to think that people are putting out AI scribes specifically for mental health purposes when we have a lot of underlying concerns at baseline where, for example, psychiatrists are often doing the work of figuring out what is sensitive, what to exclude from a patient note to preserve their dignity. AI scribes probably don't know how to do that. We also have the overarching concern of psychotic content reflecting kind of themes of tech control and being controlled by surveillance and this sort of thing. And we don't actually really understand yet how AI scribes might feed into these sorts of delusional beliefs and what sorts of harms they're going to cause these patients. And so I think it's really important to keep these patients in mind in particular as we're working on design in the AI scribe space. Okay, so given this sort of overall framework, how do we make this sustainable? This is very much an open question for the folks in the room. So this is kind of a set of options that we came up with in our perspective piece. But just looking at non-medical contexts, we have a few different sources of third-party leaderboards. We have, for example, folks in the academic space. And so in this example, Interspeech is one of the leading speech conferences, and they annually host or have been hosting a speech accessibility project challenge. There is, of course, the continuously updating OpenASR leaderboard hosted on Hugging Face. And we also have government agencies, right? So we have NIST, which every few years runs a speaker recognition eval. And this has actually been running since 1996, right? So it's not that there aren't already benchmarks and evals for speech tools. It's just that they're often in kind of different places and not focused on the medical domain. And so I think a lot of what we need to start thinking about is how to port over these sorts of infrastructures and adapt them to medical scribing. There's also the question of how we do this, right? So there are no standards, there is no regulation. when people have pitched FDA regulatory frameworks, oftentimes the answer is that would be too slow, we don't want it. And it seems like from folks from representing the FDA, or formerly the FDA here, mentioned also that it seems like a regulatory overstep in the US. In the UK as well, there are no guidelines, or rather there is no regulation, there are only rough guidelines. So this is still very much an open space where maybe the path forward is through public reporting. This might be doable just because there is some sort of alignment where HIPAA-covered entities are actually liable for AI bias. That being said, I want to end with just one analogy to something outside of medicine that hopefully can be used as an instructive kind of guideline going forward. So ASR systems are also very much used in hiring. So I don't know if anyone has been on the job market in a Fortune 100 company, because of those, something like 60% of them use an AI tool like this one to do the first round of interviews, right? So instead of talking to a human, you're talking to an AI with AI prompts. I'm seeing a head nod. How many folks have done an interview with an AI of any sort? Okay, more hands here than folks who have used DAX. Good to know. Okay, so this technology exists, and it turns out that because of the worry of employment discrimination, these companies are actually liable, and so the ACLU filed a complaint against Aon for their biased speech technology, which cited some of my lab's work, and similarly against HireVue, again for speech discrimination, which also cited some of our work. And so the incentives seem to be aligned, right? So these hiring companies, or rather AI-based hiring tools, should be trying to mitigate their biases. And then on the flip side, the folks who are hiring these companies, or rather employing these companies in order to do their hiring, are also now in New York City being held accountable through audits. So New York City passed Local Law 144, which requires audits specifically for AI biases. However, and as alluded to by this headline, this basically failed, right? I don't want to say it that strongly, but there was no enforcement mechanism whatsoever. And so a lot of work in the fact community has been kind of trying to do, not a postmortem because the law is still in effect, but trying to understand what went wrong. And that ranges from lack of the actual need to define yourself as someone who uses AI, as opposed to like, it's just a regression model. So you can do this thing called null compliance, which is just saying this law doesn't apply to me. A lot of folks did some weird data aggregation that made no sense just for the sake of completing the audit, right? And so this is all an example of what I think we need to keep in mind as we try to avoid this as we're thinking about doing broader evals and audits of medical scribes. And so to conclude, we have many open challenges ahead of us in this space, but it's really crucial to be doing this work. And most pertinently, I think what I want to advocate for is shifting the burden of making sure that all of these transcriptions are of high quality and right, away from who the onus is currently on, which is squarely just the patients themselves reading their notes and the providers who are editing their notes, and putting more of that burden on the companies themselves who are developing these scribes so that they have more of this market-related power and they're forced more to do more auditing and push for more accurate and less biased transcriptions. All right, and with that, I will take questions.
Interesting talk. Thank you so much for that. I absolutely have seen a lot of this. We have a project where we've been using a number of these ASR models on EMS data, so ambulance like call-in data, and the errors that are made by different ASR models are so dramatically different that it's actually pretty fascinating. I guess one of the things that I was curious is, you know, you talked about having leaderboards to kind of evaluate this. But for example, even the Hugging Face leaderboard, they have a special data set that they use to test to essentially establish the word error rate and other things. I was curious about what your vision of what a leaderboard would look like that would be specific to the things that you're talking about, and what is the data set, that privately held data set that you're talking about that we should be using or collecting, et cetera?
Absolutely, great question. Thank you for letting me show a backup slide. Love seeing that. Broadly, we think that the folks who are in charge of these leaderboards should be the stewards of and the primary collectors of the sort of data that I talked about in kind of ARC 1. So thinking about doing the legwork of the difficult data collection from patients that is diverse across specialties and across different accents. I think there are still a lot of open questions about who funds that and how do we actually make incentives aligned. But I do think that this is doable, just given that it has been done in non-medical spaces, and so it seems like we could port that over into a broader eval framework. There's also the question of when, and again, kind of in a nod back to one of our opening slides, thinking about alignment with the kind of post-marketing surveillance infrastructure. So again, not literally, because this doesn't fall under that category, but thinking about it in a similar way in terms of continuous monitoring in some sort of way, where again, this could involve collecting data, keeping it updated over time, but also maybe opening up some of the older data that's no longer being used for evals to folks to improve their models. All right. Thanks so much, everyone.
Thank you, Allison. This brings us on to our final keynote. It's my pleasure to introduce Emily Fox, who is a professor of statistics and computer science at Stanford University and chief technical advisor at Incitro, where she previously served as SVP of AI and machine learning. Before joining Stanford, she was the Amazon Professor of Machine Learning at the University of Washington and led Apple Health AI's team as a distinguished engineer. Emily has been awarded a Presidential Early Career Award for scientists and engineers, a Sloan Research Fellowship, ONR Young Investigator Award, and NSF Career Award. Her research interests are in machine learning and causal AI for biohealth applications. Thank you very much.
Okay, thank you. Yeah, so at Stanford, my group works on using wearable devices to improve clinical care through remote patient monitoring, and I'm going to be talking about that at the Time Series for Health workshop on Sunday. But I thought today I would add a little bit of topic diversity to ML4H and wear my hat as Chief Technical Advisor at Incitro, where I was previously SVP of AI/ML, and discuss some of our work on disentangling causality in drug discovery. Okay, so the first thing to note is that drug discovery is slow and expensive, and it's only getting slower and more expensive. And the vast majority of drugs end up failing in the clinic, with roughly only 10% making it to that final approval stage. And there are three main phases to delivering a drug, starting with discovering the therapeutic target, to developing the molecular matter that acts upon it, to eventually taking that drug to the clinic for use in human clinical trials. And there are root causes of that eventual failure that appear at each of these stages. And although Incitro works on all stages of this pipeline, I'm going to focus here on the target discovery stage. And the summary of the root causes here really boils down to there being a weak causal linkage between the discovered therapeutic target and the clinical outcome of interest. So to better understand this, it's important to understand the ways in which target discovery is done. And there's a whole host of different methods, including using simple cellular systems to more complex animal models, to looking at human disease cohort data. And as we look across these different approaches, there are trade-offs in terms of level of translation to human biology versus level of mechanistic control. And unfortunately, the human disease cohort end of the spectrum, which is closest to human biology, is also most susceptible to various sources of bias and confounding. Nevertheless, multiple meta-analyses have shown that targets with human genetic support have much higher probability of success in the clinic, 2 to 3 times the probability of success. And so at Incitro, we're leveraging AI to amplify the power of human genetics to uncover new high conviction therapeutic hypotheses with even higher probability of success. Of course, everybody is talking about the AI revolution, but what's key here is the confluence with the biology revolution. Because to get to our novel therapeutic hypotheses, we're leveraging the increasing wealth of clinical data modalities that are routinely being collected, together with human genetics, which represent our experiments of nature, to try to get at causal genetic drivers of disease. We then build confidence in these targets, as well as discover other potential targets by running perturbation screens in the lab, where we knock out genes in a disease-relevant cellular model and look at the phenotypic consequences using a range of high-content modalities, including high-resolution microscopy and single-cell and bulk omics. Okay, well, using AI to extract and amplify disease-relevant signal really does hold promise in getting to novel therapeutic targets, but it's not sufficient in and of itself because, as I've mentioned, causality is really key to our probability of success. And even with experimentation, experiments of nature, our experiments in the lab, causality can be challenging to suss out. Biology is messy. And so what I'm going to do here is take you on a tour of our science and discuss some of the methods that we've developed to start tackling these challenges. Okay, and in this talk, I'm primarily going to focus on our perturbation screens in the lab. And to ground this, I'm going to talk about one of our pipeline projects, which is discovering therapeutic targets in ALS. And ALS is a deadly disease that progressively kills motor neurons. And the work I'm going to talk about here is in partnership with Bristol Myers Squibb. Okay, well, a key pathology of ALS is the mislocalization of a protein, TDP-43, from the nucleus to the cytoplasm. And TDP-43 is really critical in the RNA splicing activities of different neuronal genes, and in its absence, can lead to the insertion of cryptic exons that lead to these truncated RNA sequences. So an example is statin-2, which is a key regulator of axonal health. So as our cellular disease model, what we do is we inhibit TDP-43 in iPSC-derived motor neurons. Then we do our set of genetic perturbations and look at measurements of statin-2 full length and cryptic exon, and then see whether any of these perturbations lead our sick cells to look healthy again. Okay, well, a standard perturbation screen uses an arrayed platform where all of the cells within a well are subject to a unique perturbation that's given to each different well. In our ALS screen, we're using CRISPR genetic knockouts, and then we're creating our sick cells by depleting TDP-43 using an siRNA, and then we look at the consequences of that using high-content imaging and omics readouts. And to make sure that we're looking at effects specific to TDP-43 depletion, we also create these healthy controls through introducing a non-targeting siRNA. Okay, so with these healthy controls in hand, it seems straightforward to estimate our perturbation effects, right? Well, anybody who's worked with this kind of data knows that the story's not quite that simple. There can be very significant well effects where wells closer to the edge of the plate have reduced cell viability, which can confound our estimates of statin-2 measurements. There can also be significant plate-to-plate variability that further obscures the true biological differences that we're interested in. So instead, an increasingly popular approach is to consider a pooled screen, where a whole set of genetic perturbations is introduced into a single well, and so we can look across perturbations all under the same condition. So we then optically phenotype these plates, looking at core cell morphology, localization of key proteins, as well as live cell dynamics. And then key to this pool screen technology is the fact that each perturbation is barcoded with a little strand of DNA that we can then read off to know which perturbation that cell received. And a whole suite of ML techniques are used to do that barcode calling process, as well as to segment out our individual cells so that we can form this cells by feature matrix and start looking at things like our statin-2 measurements for our healthy controls relative to here, we're just looking at one of many different perturbations. Okay, so with this pooled screen, can we now estimate our perturbation effects? Unfortunately, the story's not quite over yet, because just the introduction of the CRISPR machinery can have effects on things like cell size and cell fitness, both of which can affect our measurements of statin 2. And so, although a pooled screen does ameliorate some of the issues with batch effects, it's still very important to introduce appropriate controls. So to account for cell size and cell viability, what we do is we stain for GAPDH. This is a housekeeping gene that appears basically everywhere. So when we're looking at our statin 2 measurements, it's relative to GAPDH. We also introduce intergenic guides that introduce the CRISPR machinery, but between coding regions, and that allows us to account for non-specific effects of CRISPR. Okay, so with these controls in hand, we can start looking at our perturbation effects and coming up with a ranked list of potential targets. And what we see here is that a number of targets just have borderline significance. And the question is, can we extract any more signal here? And one thing to note is that CRISPR has imperfect effects, sometimes leading to no effect on the cell at all, other times just a partial effect. So we can really think of CRISPR as an intend to treat. And in our analyses, when we're averaging over cells that may or may not have actually been perturbed, we're taking a weak signal and diluting it even further. So to address this, we've developed a generative model that says with some probability, a non-control cell may actually not have been perturbed. In particular, we take a contrastive variational inference perspective where we use our control cells to help disentangle background from salient signal, and then we take that salient latent representation and model it using a mixture of perturbation-specific Gaussians plus a default Gaussian that's capturing the effects of all the unperturbed cells. And then we use variational inference to learn the model parameters as well as infer the probability of whether, the posterior probability of whether each cell was actually perturbed. So to start with, we're gonna look at using this perturbed VI model on a publicly available Replogal omics data set. And if you just do a standard omics preprocessing pipeline where you normalize your counts, log transform, apply PCA, and then apply UMAP, you see that the embedding space is really dominated by a cell cycle effect. Very hard to see separation of different genetic pathways. But on the other hand, if we first apply perturb VI, we see that we've removed this cell cycle effect, much clearer separation of the genetic pathways. And what I'm showing on the far right is the posterior probability of whether an individual cell was perturbed or not. And so this mass of dark blue dots are all the cells that were inferred as not perturbed. So this is another visualization of the same results, where each one of those colored circles is just the average over all cells that received a specific perturbation. So you can see highly interpretable results, including the fact that all these cells that were inferred as not perturbed are centered around this non-targeting mean. Okay, so we apply perturb VI as a precursor to estimating our treatment effects and returning to our ALS example, where again, remember, we're interested in our cryptic exon and full length scores. What we see is that perturb VI increases statistical power and assay sensitivity, leading to better estimation of perturbation effects. And this is for just an example gene, but we do this across genes. And we see that there's this really promising target, AGO2. So are we happy? Are we about to go spend $50 million and take this to the clinic? Well, before we do that, it's important to understand the mechanism at play. And although a full mechanistic understanding is definitely intractable, there are different things we can do to get to partial mechanistic knowledge, including just digging into the literature. And one thing we find in the literature is that AGO2 is part of what's called the risk complex. And what that means is it actually silences the ability of the siRNA to deplete TDP-43, which was creating our sick cells. So no wonder AGO2 looks so promising, but clearly if we took that to the clinic, it would completely fail. Okay, so we've been developing various automated workflows for helping with these types of deep dives. But after filtering AGO2 and looking at another one of our promising targets, which we refer here to as ALS1, we see that ALS1 shows functional rescue of neuronal regrowth, in particular with neurite length that's statistically indistinguishable from healthy controls. So this is something we're super excited about. Okay, but up to this point, we've assumed that we're interested in the effects of our perturbations on what we refer to as an anchor phenotype, some known aspect of disease like these Statmin2 measurements. But of course, we're also interested in learning novel aspects of disease, leveraging the rich imaging and omics data that we're collecting. So to this end, we train embedding models using self-supervised learning. So for example, for our imaging modalities, we train vision transformers, in particular Dino-VIT. And looking at our ALS Dino-VIT embeddings, what we see is that from morphological features alone captured in those embeddings, we're able to predict TDP43 mislocalization, as well as expression levels of ALS-relevant genes. So there's definitely something disease-relevant being captured in our embedding space. We can then go into our embedding space and define an ML phenotype that we can screen on by learning an axis that takes us from healthy to sick. We can start to interpret this axis by looking at things like exemplars at the extremes of this axis, and looking at differentiators like soma elongation or reduced neurite density. We can also train conditional generative models to visualize a walk along that axis. But interpreting our Dino-VIT embeddings in this way is quite challenging because they're really capturing a combination of different image features. So instead, we've been turning to sparse autoencoders to learn disentangled representations in terms of more monosemantic features. So we can then go and look at differentially expressed or differentially activated SAE features between healthy and sick or perturbed and control, and look at examples of images of cells that either do or do not use those SAE features, or again, doing this conditional image generation, walking along the SAE dimensions. Okay, so in our ALS example, looking at this conditional image generation, we see features corresponding to cryptic exon, cell size, localization of key proteins, and we definitely observe that these features have much more monosemanticity and are much easier for domain experts to engage with these types of representations and build more confidence in our ML phenotypes. We can also deploy SAEs on our clinical imaging modalities. So for example, we can run a genome-wide association study on an SAE trait. And this type of approach has proven really useful in our study of dry AMD using an OCT imaging modality. Okay, well, so far, our modeling work has really assumed that we're either looking at our imaging data or our omics data. But of course, we're also interested in capturing shared structure that can help us disentangle true biological signal from technical confounders that are unlikely to appear across modalities. But a challenge with this type of multimodal modeling is the fact that we're working with unpaired data. It isn't possible to collect both imaging and omics readouts from the same set of cells. Another challenge is the fact that morphology and gene expression only partially overlap in shared biology. So some perturbations can affect one modality and not the other. So our methods need to be robust to these types of scenarios. So our Petri early fusion model for defining multimodal single cell embeddings takes inspiration from vision language models that operate on these mixed modal documents where the common topic of that document increases the chances of finding that cross-modal alignment. And Petri conceives of the topic of each document as the perturbation, and pull cells from both modalities that receive the same perturbation. The cell embeddings are then fused in our cell document using mass joint reconstruction with cross-modal attention. But a challenge with this type of document approach is the fact that the sequence length can very rapidly explode beyond what the capacity of standard transformers is, because a single cell can be represented by hundreds of image patches or thousands of gene tokens. So to address this, what we do is aggressive token resampling, where we take our modality-specific encodings and distill them down into a small set of latent tokens. So on the imaging side, we use a VIT, and on the omics side, a perceiver network. Okay, a multimodal set transformer then performs really critical cross-modal attention. And here we're visualizing a couple of the attention heads for real data analysis that I'm going to talk about shortly. And we can see the cross-modal attention in these off-diagonal blocks. Okay, so using Petri, we can form these perturbation level profiles by averaging across Petri embeddings of cells that receive the same perturbation regardless of which modality they're coming from. And we're going to examine the performance of Petri on an internal matched POSH and perturb-seq data set in HepG2 cells. And our imaging data comes from fluorescence and label-free imaging and transcriptomics from flex sequencing. And to start to understand the benefits of these cross-modal embeddings, what we look at here is comparing to unimodal baselines, the performance of our Petri model in detecting string DB edges. And what we see is that Petri has higher detection rates of true edges across all false positive rates. The next thing we looked at was using Petri to reconstruct mass BOTA-P patches and BOTA-P stains for lipid droplets. And we compare Petri reconstructions with and without access to omics tokens. And to start this analysis, we're going to really look at an ablation of our Petri model, where at training time, we're randomly permuting assignments of perturbations to cells. So when we're forming our cell document, there's no real meaningful cross-modal alignment. And what we see in this case is that this ablated Petri model performs no worse than a model that ignores omics tokens altogether. So this shows robustness to cases where you have those disjoint signals. But when you do proper training of our Petri model, we can see the benefits of using omics tokens even when trying to predict image patches. Okay, and we can qualitatively start to understand the biological meaningfulness behind that cross-modal alignment, where here what we're doing is we're taking omics tokens from a control perturbation that's known to increase lipid droplet accumulation, and what we see is that we have an increased prediction in BOTA-P intensity. But if we replace those tokens for omics tokens with a control perturbation known to decrease lipid droplets, we see the opposite, decreased prediction of BOTA-P intensity. So definitely going from omics to image space. Finally, we can use our sparse autoencoders to start to interrogate our multimodal embeddings here as well. And what we're looking at here are differentially activated SAE features, and we're showing for a set of these differentially activated features the top 3 gene ontology terms. So we see their features corresponding to DNA replication, cholesterol homeostasis, and aerobic respiration, with morphology features captured in these images that definitely align with those terms. Okay, well, stepping back, we've discussed our approach for leveraging perturbation screens in the lab, discussed various sources of bias and confounding that make it challenging to get at causal therapeutic targets, and discussed both how we leverage assay design as well as machine learning methods to start to tackle these challenges. And there's a very analogous story on the ClinML side as well that I haven't had time to talk through. But one thing that I'll mention is the fact that one lever we pull is assuming that the sources of bias are very likely to be different between the ClinML and CellML sides. So for targets that have support on both sides, that can increase our confidence in those targets. So as a very quick example of this, let's talk about another one of our pipeline projects, which is the study of MASH, or fatty liver disease. And here, the clinical gold standard trait is looking at MRI-derived PDFF. But our MRI are only available in relatively small sample sizes, so our GWAS, or genetic association studies, can be fairly underpowered. So instead, an approach we take is to train machine learning models to predict PDFF from more widely available modalities like DEXA and blood biomarkers and metabolites. And actually, Sumit Mukherjee in the audience did a lot of the work on training these models. And if you look at our GWAS results, if you look at the clinical gold standard PDFF, just a couple significant loci, but as you go to predicted PDFF using those more widely available modalities, a dramatic increase in the number of significant loci. And these aren't just any loci. Many of these have actually been credentialed using other approaches, but for which human genetic support was previously not available. But we discovered a number of novel targets that we then passed to in vitro credentialing, both in arrayed and pooled screens. So in the arrayed setting, we're looking at primary hepatocytes under free fatty acid and de novo lipogenesis conditions. And we see that one of our promising targets, MASH1, doing a knockout of that gene leads to a reduction in lipid droplet accumulation across conditions, those green dots, whereas an upregulation of that gene leads to an increase in lipid droplet accumulation. So that's what we'd hope to see. So that's just one gene. We took a couple genes that passed our in vitro validation, passed them to in vivo credentialing in a DIO mouse model, so that's diet-induced obesity, and we see that 3 out of 4 of the targets have a significant reduction in triglyceride levels in the liver. Okay, so this is an example of our workflow here, where we start our discovery pipeline with high confidence targets that have human genetic support, as well as orthogonal support in our cellular screens. We then pass them to credentialing and translatable model systems, and then we take that evidence and aggregate it with external sources of evidence that are out there in the world, and then eventually nominate targets for drug discovery, and then eventually that clinical development. And we're hitting that clinical development phase for one of our targets. You can read about it online. And to wrap up, this is all in support of InCitro's mission to bring better drugs faster to the patients who can benefit most through machine learning and data at scale. And of course, I'd like to thank the incredible team behind all this work. Thank you.
All right, thank you. We have time for one question.
Hi, thank you for a great talk. I have a question around the timeline of these things. So it seems like a lot of work, and also I know that in this space, like it's like 10x what we typically expect, but I was wondering if you talk a little bit about the timeline and things you think that you've learned that could kind of speed up the next drug. So I know you have one, but I imagine you want to test a lot more and can't afford to spend that much time.
Yeah, it's a great question. I want to make sure I'm not misquoting timelines here, but I can say the whole point of this is to accelerate timelines to get to promising candidates. And for example, from start, I think I'm quoting this time correctly, from the initiation of the idea of looking at MASH to having these targets in hand that had, a lot of confidence behind them, I think that entire timeline was 18 months. Sumit, is that right? Would you back me up with 18 months? Yeah. And so that is dramatically shorter than than the typical approach for doing this. And the real goal is to have this flywheel, right? To be able to take what we've learned and what we've developed and be able to just rapidly get to high confidence targets. And we're definitely seeing like real dramatic increase in things coming through our pipeline here. Yeah.
All right, let's thank Emily for the excellent talk. All right, let's wrap this thing up. So first up are the Best Paper Awards. So we have 4 Best Paper Awards, a Best Demo Award, and then a Best Reviewer Award. So when we call your name, please come up to the stage, shake our hand, get your fancy certificate, and we'll get a picture taken from the photographer as well. All right, first up, Best Proceedings Paper Models and Methods. The winner is Deep Kernel Allen Johansen Estimator, Interpretable and Flexible Internet Framework for Computing Risks. Are the authors in the audience? Anyone in the audience? Nope. Okay, next one.
All right, Best Proceedings Paper in Applications and Practice. An agentic approach to phenotyping mapping from rare disease surveys.
All right, next up, Best Proceedings Paper Impact in Society. The winner is Balancing Safety and Helpfulness in Healthcare AI Assistance through Iterative Preference Alignment.
Best Findings Paper. A foundation model for intensive care, unlocking generalization across tasks and domains at scale.
And the best demo is cancer identification and simulated case prioritization with tumor detect. Okay, we'll skip that one.
And then finally, we started this Best Reviewer Award, which is tracked by reviewer ratings from ACs. So this year we had 3 top reviewers, being Katie Matten, Shiva Kaul, and Thomas Frost.
Are any of you in the audience? Anyone? Nope. Okay. All right. So it's taking 21 of us, like 6 months to organize this conference. All of us are volunteers, except for the Audi staff. We do this in our free time between like research and sleep. So we're going to go through and thank everyone for organization. Thank you to the program for organizing the program, logistics or finance for raising time and money to fund your free food, logistics for logistics, Ali for like everything, workflow for open review, communications for Twitter and email management, outreach for mentorship and roundtables, publications for getting the PMR papers in. Let's thank the organizers.
And then in addition, we'd like to hear your feedback. How did ML4H go? So if you could please scan this QR, let us know what you liked, what you didn't like. Okay, and then finally for next upcoming events, sponsored by Ollie. So the Ollie team has been working on something very exciting. We're pleased to announce that there is a new machine learning course for the Health Summer Program. The Ollie Health AI Summer Camp will be taking place in Seattle, Washington from June 21st to 28th, and will focus on training the next generation of leaders in our field. This program is designed for late-stage PhD students and early career researchers. We'll be sending out more information about this after the conference. And also in Seattle is our sister conference, Chill, is returning for its 7th edition. It will be co-located with the summer camp, and the call for papers is currently live. The submission deadline is February 4th, and as always, Chill will feature the doctoral symposium, as well as an unconference focused on entrepreneurship or health AI, or entrepreneurship in health AI.
All right, so ML4H will be back next year. We don't know where, we don't know when, there'll be someone on Earth. So if you have any thoughts on where we should be, we may or may not collect with NeurIPS again. So let us know in the feedback form that was just on the screen or on social media.
And finally, other related venues. There's SAIL, which is a symposium on AI for learning health systems, which is coming up in May and has a deadline January 16th. And then MLHC, which will be in August with a deadline somewhere around April.
All right, thank you so much. If you want to review or organize or AC for next year, there's a form in the QR code. Otherwise, thank you for attending. We hope you learned something. Thank you.